For thousands, today we know that the Earth is a mere speck in space. In trying to learn about the universe in which he lived, man has always been far too ready to believe his own eyes. He found it extremely difficult to shake off his terrestrial perspectives when looking out at the vast distances and tremendous intervals of time that prevail in the universe. In this series of programs, we are going to try to tell you something about the wonder and mystery of space, about some of the strange and often magnificent objects that are out there in space, and something about the relationship of our Earth to these objects, for our Earth is itself a very tiny ball in space. We live on an Earth which is a planet, a member of the solar system, a system which consists of 9 planets revolving about a central star that we call the Sun. Here, in this little arrangement, we can see the 9 planets. There are 9 planets. There are 31 satellites which belong to several of these planets. And there are an unknown number of minor planets, the asteroids, and an unknown but still larger number of comets and meteors which thread their way in among these planets. Now, of course, this just shows the planets. It doesn't show these minor objects. And there is no attempt made in this little affair to give you any conception of a size or distance scale. You can't make a scale model of anything astronomical. Here, for instance, in this model is the Earth. And if this were to scale, the Sun here would have to be at least 110 times the size of the Earth, about so big. And as far as distance is concerned, the Earth couldn't even be in the room. Now, let's talk about these distances for a moment. Suppose we were to take the distances in the solar system and divide them by 1,000,000, and then take that reduced solar system, reduced to a scale of 1 in 1,000,000, and lay it over the United States. We'll put the Sun at New York. Then Mercury, the nearest planet to the Sun, would travel over a pleasant little suburban town in New Jersey, Morristown, 36 miles from New York, Mercury 36 million miles from the Sun. On that same scale, Venus would come over Camden, New Jersey. The Earth would be in the western suburbs of Philadelphia. Mars would be at about where Harrisburg is, and these minor planets, the asteroids, would travel in a path lying generally between Harrisburg and Pittsburgh. Jupiter would be outside of Pennsylvania for the first time. It would lie over Detroit. Saturn would be over St. Louis, Missouri. Uranus over El Paso, Texas. Neptune would be completely out of the United States, lying some 100 or so miles west of San Francisco in the Pacific Ocean, while Pluto, the most distant planet of the solar system, would be really out in the Pacific, at least 1,000 miles beyond Neptune. Now, remember, this is to scale. These distances are all divided by 1,000,000, and this is the relationship of it. Remember, too, that unlike the conditions in the United States where we have farms and cities and towns and villages and so on scattered all through that, there is really nothing out in space between the planets. To all intents and purposes, space is virtually empty. Now, the whole system is really rather flat. If we were to put it into a sort of a super hat box, 3 feet in diameter, that hat box need only be about 8 inches deep. Distances in the solar system are tremendous. There is only one object permanently in the system within 1,000,000 miles of the Earth, and that is our moon. The next nearest object, occasionally, is Venus, which can be within 26 million miles of the Earth. Now, as long as we stay in the solar system, we're going to be able to use miles as our unit of measurement. When we get outside of the system, we're going to have to find another means of measuring distance. Distances in astronomy are really overwhelming. Now, man's conception of the universe is based upon what he saw. He lived upon a tremendous Earth, obviously the biggest thing in space. Around it went a bright sun, probably made of very hot rock and about as big as a man's head, and a pale moon, less hot but about the same size. Then there were 5 strange, wandering stars that moved at varying speeds among the other stars, which were fixed to a sort of hollow shell inside of which was everything else. These wandering stars were the planets. The whole business moved about the Earth and was placed there solely for man's entertainment and admiration. As man grew up scientifically, he had to give up this rather grandiose conception of the Earth. But it's only been within the last 500 years that man has come to realize that the Earth was not the center of the universe or even the center of the solar system. That the Earth was just one of 9 planets that moved about the sun in orderly progression. And threaded in among these planets were these other small objects that we spoke of, the asteroids, the comets, and the meteors. Now here is a diagram of the solar system showing the objects in their proper order. Here's the sun, of course, in what we might call the middle, the focus of the whole thing. Now, as we go out from the sun, we meet the planets in this order. First Mercury, then Venus, then the Earth, and then Mars. And now even in this diagram, we've got to change our scale a little bit. Here, down below, is the inner circle, you see, with Mars as the outermost planet. Then, outside of Mars, come Jupiter, Saturn, Uranus, and Neptune, and finally, last of all, Pluto, way out at the edge of things. This is the distance relationship, or rather the order of these things. Size is something else again. The sun, of course, is the most tremendous object in the solar system. It has far more than 99% of all the material, all the mass of the solar system. Here is a diagram which shows this size relationship. Here's just a segment of the sun, just a little piece of it, you see. And on the same size scale, here are the planets. Here are the small ones, Mercury, Venus, the Earth, and Mars, and little Pluto way up at the other end. Then come the big planets, Jupiter, Saturn, Uranus, and Neptune. Now, there is, of course, a very obvious size division in this arrangement. And we're going to take advantage of that, and this morning we are going to talk about the small planets of the solar system. The smallest of all of these planets, and the first one out from the sun, is Mercury. Mercury is a little fellow, 3,100 miles in diameter, less than half of the diameter of the Earth. And Mercury moves about the sun at a mean distance of 36 million miles from the sun. Now, this term mean distance is made necessary by the fact that the orbits, the paths that the planets take as they go about the sun are not circles but ellipses. This is an ellipse. So that at one time in its journey about the sun, a planet, Mercury or any of the others, is much nearer to the sun than it is at another time. When Mercury is at the point in its orbit which brings it nearest to the sun, that point, incidentally, is called perihelion. It comes from 2 Greek words, peri meaning near to, and helios, the sun. Mercury is 28.5 million miles from the sun. Now, when Mercury, in its journey around the sun, reaches the opposite point in its orbit, where it is most distant from the sun, and that's aphelion, again from a couple of Greek words, apo meaning far from, and helios, the sun, it's 48.5 million miles from the sun. And the mean distance between these two extremes is 36 million miles. And that mean distance, incidentally, is the one always used in talking about the distance of Mercury or any of the other planets from the sun. Now, Mercury moves in this path about the sun at a speed of about 30 miles a second to make its journey about the sun in 88 of our days. That's Mercury's year. Now, notice this. As we talk about these planets in the solar system, those which are nearer to the sun are moving much faster than those which are farther away. Mercury is at 30 miles a second. Now, we can illustrate this. It's a principle of angular momentum. We have a governor here, simply 2 rather heavy spheres mounted on a couple of arms, and this governor is used to regulate the speed of machinery. We start it moving rather slowly. Now, without giving it another push, we just bring those 2 spheres closer together and see what happens. They immediately speed up, and we separate them, and they slow down. That illustrates the principle upon which the planets move about the sun. The nearer planets go faster, and those more distant go slower. Now, Mercury is much closer to the sun, of course, than we are, 36 million miles. That means that the angle between the sun and Mercury, as we see it, is rather small. And we can never see Mercury for, more than an hour at the most, either before sunrise in the east or after sunset in the west. It's very close to the sun. Now, twilight in this part of the world lasts about an hour and a half. So, you see, we never see Mercury in complete darkness. It's a very difficult thing to see. Mercury's rapid motion about the sun is translated, as we see it, by a series of swings, first to one side of the sun and then the other, so that we see Mercury at intervals and then it's hidden behind the sun and we don't see it at all. Now, here is a photograph of Mercury, a picture taken through one of the big telescopes. And you can see that Mercury is not very photogenic. We see Mercury in a phase formation here, in what is called a gibbous phase. That is something like the moon when it's a little bit more than quarter and less than full. That is because Mercury, of course, is nearer to the sun than we are. Its outline is rather hazy and vague. Well, that is the fault of the Earth's atmosphere. Because Mercury is always so close to the horizon as we see it, we have to look at Mercury through a vast length of the densest part of the Earth's atmosphere and do not see it very well. Now, Mercury's closeness to the sun and the sun's tremendous gravitational power have slowed down Mercury's ability to rotate upon its axis to such an extent that Mercury can make one spin upon its axis in the same length of time that it makes one revolution about the sun. This results in the strange condition that the same side of Mercury is always facing the sun. One side of Mercury is in eternal blinding daylight, the other side in bitter night. And Mercury is too close to the sun for comfort. For the temperature on that hot side of Mercury is about 750 degrees Fahrenheit. That's the mean temperature there. Now, think what that means. Next time you have a roast in your oven, open the door and feel the blast of heat that comes out at you. Most domestic ovens have a top temperature range of about 500 degrees Fahrenheit. Mercury's surface is half again as hot as that, the part that's under the sun. The dark side of Mercury, which as far as we know has never seen the sun, is just about as cold as anything can get, pretty nearly absolute zero. The temperature on the dark side of Mercury must be about 450 degrees Fahrenheit below zero. Mercury is at once the hottest and the coldest planet in the solar system. Now, Mercury's mass, that is the amount of material in it, is rather small. And since its surface gravity depends largely upon its mass, Mercury's surface gravity is only about half that of the Earth. In other words, a normal 150-pound man, if he could stand it on Mercury, would only weigh about 75 pounds. This surface gravity, too, is what holds an atmosphere upon the planet. And Mercury's surface gravity is not strong enough to hold any atmosphere there. So there is nothing up there to mitigate these terrible extremes of heat and cold. Mercury is a dead and dreadful world. Beyond Mercury, the next planet out is Venus. And here is a photograph, Venus, showing it in 5 different positions. Now, remember this, that this whole photograph, all these positions of Venus are on exactly the same size scale. And just what that means, we'll cover in a minute. Venus is almost a twin to the Earth in size. It's 7,700 miles in diameter. It goes about the sun in 225 of our days. That's Venus year. And Venus has sufficient surface gravity to hold an atmosphere upon its surface, a very dense, white atmosphere, an atmosphere which reflects sunlight beautifully, so much so that Venus can be very easily seen. Now, Venus, of course, is nearer to the sun than we are, and again, like Mercury, its motions are translated into wide swings to one side or the other, but they're a lot wider than the swings Mercury makes. And we can see Venus at times for as long as 4 hours before sunrise or 4 hours after sunset in the sky. And when Venus is most favorably situated, its nearness to us, it can be only 26 million miles from the Earth, and combined with its white reflective atmosphere, make it the 3rd brightest object in the sky. Now, let's see what happens as we watch Venus when it's going about the sun. As we see it from the Earth, Venus, of course, is at times directly beyond the sun from the Earth. Sometimes we can't see Venus at all. It's hidden behind the sun. At other times, because Venus' orbit is a little bit angled, we do see Venus above the sun or below it, and at such times we see it in its full phase. We see its completely lighted side. Now, as Venus goes around the sun, we can begin to see it, Venus itself, out beyond the sun. Then it is in what we call a gibbous phase, as we saw Mercury. A little further around, it would be in its quarter phase. Still further, it would reach the point where the angle between Venus and the sun as we see it is largest, and we'd see it as a rather stout crescent. And just beyond that, when the crescent is very thin, but nevertheless when Venus is near to us, is when it's brightest. Now, when we saw Venus full, it was 160 million miles away. When we're seeing it now, although we see very little of its lighted side, it's only 40 million miles away, and perspective makes it very, very bright. The atmosphere of Venus, this white atmosphere, is composed largely of carbon dioxide. We've never been able to find any oxygen or water vapor up there. Now, carbon dioxide is a very handy chemical. In solid form, it's dry ice. As a gas, it's a wonderful fire extinguisher, and it's the bubbles in our soft drinks, but we can't see through it. Now, the appearance of Venus, if we could get close enough to see it, might be very much like this, a dense, white, impenetrable cloud. But below that covering of carbon dioxide, almost anything can happen. You see, we've never seen the surface of Venus itself. We don't know what it's like. And there are two pretty wide opinions about what the possibility there. One of them is that Venus is a swamp, a very watery, terrestrial, a celestial rather, hothouse with a very lush growth of vegetation. The other one is almost diametrically opposed to that. They say that Venus is a completely waterless desert like this. Well, who knows? You pays your money and you takes your choice. The third planet out from the sun is the one we live on, the Earth. We are number 3. And because the Earth is rather important to us, it will have a program all of its own. Beyond the Earth, its nearest neighbor outside of the Earth from the sun is Mars. And Mars is, in many respects, the most interesting of the planets. Now, Mars is small. It is 4,120 miles in diameter, a little more than half the size of the Earth. It is at a mean distance from the sun of 141 million miles, and it goes around the sun in 687 of our days. That's Mars year. Now, Mars travels at about 15 miles a second. See, the slower planet, Mercury 30, Venus 22, the Earth 18.5, Mars 15 miles a second. The angular momentum idea. Mars also rotates upon its axis in almost the same time that the Earth does. Mars' day is 24 hours and 37 minutes long. Now, Mars' orbit is quite eccentric. It's very elliptical. And the Earth goes around the sun inside the orbit of Mars and much faster, so that the Earth overtakes and passes Mars every 2 years and 2 months. Now, when these chance meetings take place, if they happen, when Mars is nearer the sun at this perihelion point, it is also very near the Earth. And it is at such meetings that we can see Mars best, but they don't happen very often, about once every 15 or 17 years. And what we have learned about Mars has come to us in little bits and pieces accumulated at these fortuitous times through the years. If you look at Mars through a telescope, one of the telescopes best adapted for planetary work, it's still hard to see. You see a little pinkish ball, and it's bubbling, it's boiling. Now, that boiling is our atmosphere, is turbulence in our atmosphere. Occasionally, however, if you're patient, that'll clear up, and Mars can be clearly seen. Now, when Mars is seen, it has very definite surface characteristics. There are 3 colors which distinguish Mars. One is a sort of a background of brickish red. Then there are several irregularly shaped green areas and a rather dazzlingly white cap at the pole of Mars. You see, Mars has seasons, just very much as the Earth does, and for the same reason. Mars is tipped away from the vertical on its axis. And when it's winter at one end of Mars, it's summer at the other. And on the winter end of Mars, this cap gets quite large. Now, that is probably frozen water. I hesitate to call it ice, because there isn't enough body to the Martian atmosphere to produce ice. It's frost, frozen water, because it melts, it shrinks as the seasons change on Mars. And as it shrinks, its outline is marked by a rather broad brownish band, such as water might make soaking into sandy soil. There are other seasonal changes on Mars, too, which are extremely interesting. This greenish region here changes with the Martian seasons. In the Martian spring, it's a very pale, delicate green. In the summer, it ripens to a rich, almost bluish green. In the autumn, Martian autumn that is, it's yellow and brown, and in the winter it fades out to a rather lifeless gray. Now, we have that same color change here on the Earth. It's vegetation. And this may be vegetation on Mars, the only evidence we have of any kind of life outside of the Earth. If it is vegetation, it isn't trees or grass. It's a very primitive form of vegetation, moss or lichen, that can stand tremendous changes of temperature and so on. Now, the reddish area is mostly desert. About 70 years ago, a great Italian astronomer, G.V. Schiaparelli, spent a wonderful summer observing Mars. He had one of these favorable positions of Mars. He had beautiful weather. He had a wonderful telescope. And he wrote a voluminous report on what he saw. And he was able to see a number of things that nobody had seen before. Now, Schiaparelli in his report said he's going to try to identify the features he saw on the surface of Mars by comparing them to similar features on the Earth. There were capes and promontories and mountains and channels and so on. And Schiaparelli saw on the surface of Mars a network of fine lines crisscrossing almost the whole of the surface. He called these channels, and the word he used for channels was canali. Well, canali looks and sounds very much like the English word canal. And that's the way it came out when Schiaparelli's report was translated. And the fat has been in the fire ever since. Now, about half of the professional astronomers who devote their whole careers to the observing of Mars have seen these canals. The other half have not. And here is an artist's conception of what these canals might look like. Now, you can see that they are not regular and even like engineered jobs. They're natural channels, if they exist at all. We just don't know. They have never been successfully photographed. Pictures of Mars, and there have been many of them taken through the great cameras, just don't show the photographs. Now here we can see two very excellent pictures of Mars. They show the polar cap, they show the red areas and the green regions, but no canals. That may be the fault of the camera. The grain of a photographic emulsion is much coarser than these canal lines would be in the picture, and therefore they don't come out. In any event, to be seen at all from a planet at Mars distance, the canals would have to be 20 miles wide. And what on Earth, or rather what on Mars, anybody'd want with a 20-mile wide canal, we just don't know. The canals are still a moot point. We just don't know whether they're there or not. And the only way in which we will find out, probably, is when the first rocket ship gets up there, the intrepid crew will get out and they will either walk right over where a canal ought to be or fall into one. Mars has two very interesting little satellites, the most peculiar satellites of any planet. They were discovered in 1877 by an American astronomer named Asaph Hall. They are very small. The biggest one is 10 miles in diameter and the smallest about 5. The larger one, the outer one, named Deimos, goes around Mars in about 30 hours, in just a little more than one Martian day. But the inner one, Phobos, about 4,000 miles from Mars, whips around Mars 3 times a day. Now, like any well-educated satellite, it goes through all the phases of a moon each time it goes around, so that theoretically Mars could have 3 full moons a night. Well, astronomy hasn't figured out yet a practical use that you can make for 3 full moons a night. It might serve to speed up Martian romance a little bit, but there is a practical use for these things, really, in the future. They are built-in space satellites and will be used, I'm sure, in time for the observation of Mars. The last of the small planets, the most distant one in the solar system, is Pluto. And here is a photograph of Pluto. Pluto is so far away and so faint that we have to identify it in this picture by pointing an arrow to it. Now, Pluto was discovered mathematically before its presence was ever actually known. Neptune is the next planet nearer the Sun than Pluto. And Neptune had been going along its orbit for about 50 years after its discovery in 1846, before it was noticed that Neptune was not following its expected path. It wasn't going straight. It was, there were variations in its path. Now, these variations are called perturbations in the orbit of a planet. And they are evidence that there is some other body out there disturbing the normal course of a planet about the Sun. One of the great American astronomers, Percival Lowell, set himself the task of finding out whatever it was that was bothering Neptune and making it wander through space. He called it Planet X, and he started in by calculating its possible position mathematically, which was considerable of a job. Then Lowell died in 1905, and the task was taken over by a young American astronomer named Clyde Tombaugh, who took literally thousands of pictures of the region in which this planet was supposed to exist. Now, here are a couple of pictures of Pluto, taken in that same way. Here again is Pluto. It must be identified by an arrow. Notice its position in relation to the stars, one on either side of it. Now, the next night, another picture of Pluto was taken. Same arrow, same Pluto, same stars, but notice the change. That is what gave Pluto away, its motion among the stars. Pluto was discovered in February of 1930. Its discovery was not announced until March, however, on March 14th, which was Percival Lowell's birthday. Then it made the headlines. Here is a copy of the New York Times for March 14th, 1930, and up here in a prominent position is the headline announcing the discovery of Pluto. 9th planet discovered, on edge of solar system, first found in 84 years. That's Pluto. Out there, 3.5 billion miles from the sun, taking 248 of our years to make its weary journey around the sun. Now, Pluto, that 3.5 billion miles, incidentally, is, again, its mean distance. It can, at times, be closer to the sun than the planet Neptune. Here, for instance, is the orbit of Neptune. Here is the orbit of Pluto. And you can see that in 1989, Pluto will actually be nearer the sun than Neptune is. The two planets won't collide, however, because Pluto's orbit is tilted away from the horizontal, and the nearest they can possibly come is something more than 200 million miles. We don't know very much about Pluto. It's very faint, very far away, very hard to see. It's probably a little smaller than the Earth, somewhere between the Earth and Mars in size. It has no atmosphere. Its temperature, out there 3.5 billion miles from the sun, must be equally as cold as the dark side of Mercury, just about 450 below zero, almost absolute zero. It has no atmosphere. There are no traces of any satellites. Now, let's see what we have learned about the solar system today. We have it here, this little affair, which again is not a model, remember that. But the 9 planets are there. Now, we have talked about the smaller planets, 4 of them situated very close to the sun. The 5th one, the exception, at a vast distance from the sun. That's Pluto. Now, these 5 small planets all have a sort of a relationship. They're all small, about the same size, nearly the size of the Earth. And for that reason, they're called the terrestrial planets. They also have a very small proportion of the solar system satellites. Mercury has none, Venus has none, the Earth has just 1, our moon, Mars has 2, Pluto has none. They're not too rich in atmosphere either. Mercury doesn't have any atmosphere. Venus, of course, does have a rather thick one. The Earth has an atmosphere, we breathe it. Mars has a very, very thin one, Pluto has none at all. These are the little fellows. Now, we don't know whether there is any other planet out beyond Pluto. If there is, it is so vastly far away, at such a tremendous distance, that its possible discovery will surely be a matter of chance rather than any plan that man may make to find it.
This is National Educational Television.
"500 million miles from the sun, we enter the neighborhood of the giants. Great planets moving in a celestial deep freeze about a distant sun whose light and heat barely reaches them. Giant planets are among the most exciting things that we can see in the sky. You remember that the solar system is composed of a diverse number of objects moving in fairly regular progression about a central star, the sun. In this little model, which incidentally does not attempt to show the size scale at all, we can see the 5 small planets, 4 of them close to the sun, the notable exception Pluto, very distant from the sun. There are an unknown number of smaller objects in the solar system, the asteroids, meteors, and comets, and the 4 giant planets, which we are going to talk about today. Now, this little model doesn't attempt to show any size scale or distance scale. If that were the case, the sun here would have to be at least 10 times the diameter of Jupiter. Here we can see that size scale a little better represented. First of all, here is just a segment of the sun, that controlling star, which contains far more than 99% of all the matter in the solar system. Here are the small planets as we go outward from the sun: Mercury, Venus, the Earth, Mars, and the exception Pluto, most distant from the sun. Here are the giants: Jupiter, Saturn, Uranus, and Neptune. And it is Jupiter, the 5th planet from the sun and the first of the giant planets, that we are going to talk about today. Jupiter moves around the sun in an elliptical orbit. Now, the orbits of all the planets as they go about the sun are not circles, but ellipses. This is a rather exaggerated ellipse, but it gives us the idea. That means, as these planets go about the sun, that at times they are much closer to the sun than they are at other times. Jupiter, for example, when it is at the point in its orbit nearest the sun, the point which astronomy calls the perihelion, it is 460 million miles from the sun. When it reaches the other point in its orbit, its aphelion point, it is 507 million miles from the sun. Its mean distance, which is the halfway point between these two extremes, and which is the distance that we always use when we speak of Jupiter, is 488 million miles. At this distance, Jupiter receives only about 1/27th of the light and heat that we get from the sun. Jupiter is big. It is the biggest of all the planets and has a mass, that is the amount of material in it, which is more than twice the mass of all the other planets put together. Jupiter's equatorial diameter is 89,000 miles. In spite of this tremendous size, however, Jupiter rotates extremely rapidly upon its orbit. It makes a complete turn in 9 hours and 55 minutes, which give it an alternation of light and dark, for whatever it may be worth at Jupiter's distance from the sun, of less than 5 hours. A night, for example, scarcely long enough to really start sleeping. Jupiter has a very deep and very dense and very fluid atmosphere. And Jupiter's very rapid rotation upon its axis has a strange effect upon its form. I told you that Jupiter's equatorial diameter was 89,000 miles. Its polar diameter, however, is only 82,000 miles. And this is what happens. Now, here is a little flexible model of a sphere. You see, its shape can be changed. Now, as Jupiter spins so rapidly upon its axis, this is what happens. Watch. You see, that rapid spin has moved most of Jupiter's dense atmosphere into a belt around its equator and made its polar diameter much shorter. In other words, Jupiter is what we call oblate. It is an oblate spheroid. Now, that means something shaped like a sphere, but flat at the poles. This is the case with all of the giant planets, and even with some of the smaller ones. The Earth, for example, has a polar diameter which is smaller than its equatorial diameter. Jupiter moves about the sun at a velocity of about 8 miles a second and takes 11 years and 10 months to make its journey about the sun. That is Jupiter's year. Now, the Earth moves about the sun in 1 year. Jupiter in almost 12, so that we go about the sun much more rapidly than does Jupiter. And that, too, causes something very strange to take place. In this model, we can see the sun and the Earth and Jupiter. The Earth in an orbit much closer to the sun, Jupiter much farther out, and of course traveling much more slowly than the Earth travels. Now, as we watch Jupiter through the year, we see something very strange happen. But first, let's see what really does happen. Now, we can see, as the Earth goes around inside of Jupiter, they both move in a regular, steady pace through the skies from west to east as we see them in the sky. However, notice that the Earth overtakes and passes Jupiter. It actually does this at intervals of about 13 months. When that happens, what we see is vastly different from what really takes place. Now notice, in this little outer sphere here, this is what we see when we pass Jupiter. We're coming up, we overtake Jupiter, and Jupiter stops, goes backward for a little while, and then resumes its normal eastward course. This is due entirely to the fact that the Earth moves in an orbit nearer to the sun and more rapidly than Jupiter. You've had the same thing happen to you on an express train. You've been riding in the express train, there has been a local on the next track. You overtake and pass that local train, and perhaps you have looked out of the window and seen that, and the local train has apparently been going backwards. This is called retrograde motion. It is purely an apparent motion. It does not really exist. Jupiter knows nothing whatever about it and has been always continuing its normal eastward journey around the sun. Jupiter's tremendous mass, that is, the vast amount of material it contains, gives it sufficient gravitational authority to hold upon its surface a very deep and very dense and very complex atmosphere. An atmosphere that is made up of some rather undesirable elements. In Jupiter's atmosphere, we can recognize hydrogen, helium, methane, and ammonia. I'm sure all of you are familiar with ammonia. Methane, too, is something very common, for that is what comes out of your gas stove when you turn the tap on. Hydrogen is the most abundant element in the universe. Helium is what they call an inert gas. It doesn't catch fire, but it is extremely light, and we use it on Earth a great deal, particularly in our lighter-than-air balloons. There is an imaginary conception of what the surface of Jupiter might look like. Of course, we have no idea of what it really is like, but this does show the tremendously dense, cloudy atmosphere. Here is a model of Jupiter, which shows its cloud-streaked atmosphere. Now, what is underneath there, we do not know. There are several ideas. One of them is that Jupiter is made up of a dense, rocky core with a diameter of about 37,000 miles. Overlying that rocky core is a layer of ice 17,000 miles deep. And over that, of course, Jupiter's dense atmosphere, about 7,000 miles in depth. The other conception is that Jupiter does not have any rocky core at all, but is simply a sphere of hydrogen. Now, at the temperatures of about 150 below zero, which constantly are on Jupiter, and at the tremendous pressures in the interior of the planet, this hydrogen would be compressed almost to the solidity of metal inside there. As we see Jupiter in the sky, it is always far brighter than any of the stars around it. Here is a photograph of Jupiter taken through the telescope. And here we can see the cloudy bands in that dense atmosphere, lying almost parallel to Jupiter's equator, combed out in that way by Jupiter's tremendous rotational speed. The symmetry of these cloud bands is marred occasionally by spots which appear in the atmosphere of Jupiter. This is a very famous spot. It's the Great Red Spot, which was first seen a little less than 100 years ago and has been there ever since with varying degrees of intensity. This spot is about 30,000 miles long and about 8,000 miles from top to bottom. It would take 3 Earths, if they were placed up there, to adequately cover this spot. Jupiter has 12 satellites, rather more than its share. Now, the Earth has only one, our moon. Jupiter has 12. 4 of them are big, each of them far bigger than our moon, and 2 of these even bigger than the planet Mercury. These 4 were discovered at one fell swoop by Galileo, the first man ever to look at the sky, or indeed at anything else, through a telescope. The other 8, far smaller and far more distant from Jupiter than are these 4, have been picked up from time to time by other astronomers through the years. One modern astronomer, Dr. Seth Nicholson, has got a score which equals Galileo's. He has discovered 4 of these satellites of Jupiter's, but it took Dr. Nicholson a good many years, whereas Galileo found his all in one night. The 4 outermost satellites of Jupiter, tiny things 15 to 20 miles in diameter and millions of miles away from the planet, are moving around Jupiter in a direction contrary to that assumed by most of the planets. They are going in what we call east to west. This is, again, an example of retrograde motion, but this time the motion is real. We do not know why these planets are moving that way. It may be that they are asteroids, tiny minor planets captured by Jupiter's gravitational forces from the belt of asteroids which moves through about the sun close to Jupiter. The 4 major satellites of Jupiter have had a very important part to play in astronomy, for they were instrumental in the discovery of the velocity of light. Before the 17th century, light was assumed to travel instantaneously. In that century, a Danish astronomer, Olaus Rømer, was timing the appearance of the satellites about Jupiter, the moments when they vanished behind the planet as they went around. Now, Rømer noticed through the year that the interval between disappearances increased, which it should not do because they were running on a fairly regular schedule. And finally, Rømer figured it out. When the Earth is here in relation to the sun, and Jupiter here, as it might be, let us say, in June, the satellites were running on time. In December, when the Earth got around to this side of the sun, whereas Jupiter had only moved a short distance in its orbit, the satellites vanished behind Jupiter 16 minutes later. Rømer reasoned that this was because the light from the satellites had to travel an additional distance equal to the diameter of the Earth's orbit about the sun, about 186 million miles. Now, if you take 16 minutes and divide it into 186 million miles, you come up with a figure which is very, very close to what we accept as the velocity of light today. That is 186,000 miles a second. The next of the giant planets out from the sun, and the one second in size only to Jupiter, is Saturn. And if you ever get a chance to look at Saturn, even through a small telescope, don't pass it up. You'll see one of the most thrilling sights you ever saw. Saturn is the planet with the rings. Saturn is a giant. Second only to Jupiter in size, it has an equatorial diameter of about 75,000 miles, a polar diameter of 68,000 miles. It, too, is oblate, you see, and for the same reason that Jupiter is, because it spins very rapidly upon its axis. Saturn's day is 10 hours and 2 minutes long. Saturn travels about the sun at a velocity of about 6 miles a second. You see how that rule holds now? The nearer the planets are from the sun, the more rapidly they travel. The farther we get, the slower they go. Jupiter, 8 miles a second, Saturn, 6 miles a second. And it takes Saturn 29.5 years to make its journey about the sun. Saturn's atmosphere is very much like that of Jupiter, composed, we believe, of very much the same unpleasant substances, with a difference only due to the fact that Saturn is considerably colder than Jupiter. Saturn is about 200 below zero all the time. It must have very much the same interior construction as has Jupiter. Here, for example, are comparative charts of what Saturn and Jupiter might look like if we were able to saw them in half. Here is Jupiter with a fairly large rocky core, a very deep layer of ice, and a layer of atmosphere overall. Saturn, similarly, has a much smaller core, less ice, and rather more atmosphere. Saturn is very light for that reason. Indeed, it may be that Saturn, as may be the case with Jupiter, has no rocky core at all, but is a sphere of gas only. However, Saturn is so light that if we were able to find an ocean big enough, Saturn would float in it. Saturn has 9 satellites, which move about Saturn very much as the Jupiter satellites move about Jupiter, practically in the plane of Saturn's orbit. One of these satellites, the 6th one out from Saturn, is named Titan, and may very well be the largest satellite in the whole solar system. It is much bigger than Mercury and is the only satellite we know of which has an atmosphere, although this atmosphere is probably just frozen pools of methane lying in hollows upon the surface of the planet. The 9th satellite from Saturn, the most distant, is Phoebe, and Phoebe is going around Saturn in a direction opposite to that which is taken by the other satellites. Phoebe is a little retrograde satellite and may be a captured asteroid, as were the 4 outer satellites of Jupiter. The most beautiful thing about Saturn, and the most amazing thing, and a thing which is unique as far as we know among heavenly bodies, is of course its ring system. Here is a picture of Saturn and its rings taken through one of the great astronomical telescopes. The ring system measures 171,000 miles in diameter, although its depth, that is, its distance from top to bottom, is only about 10 miles. The inner edge of the ring is about 7,000 miles from the surface of Saturn. And the ring itself, the ring system, is in 3 concentric rings. The inner one, which is very faint and very difficult to see, is called the crepe ring. It has the appearance of that dress material that's called crepe. The center ring is the widest and the brightest. Then outside the center ring there is a gap, a space in which there is nothing. And outside of that, a much fainter outermost ring. Now these rings are made, we believe, of tiny particles, literally billions of them, moving around Saturn with all the authority that a single satellite might have. We do not know precisely the origin of these particles, but they are thought to be the debris from what was once a 10th satellite of Saturn, which came in some manner which we do not understand, too close to the great bulk of Saturn itself, and was torn to pieces by the force of Saturn's gravitational field. That will happen. We know that. If 2 bodies of equal density but unequal mass get too close to each other in space, the smaller of the 2, instead of being pulled solid into the bigger one, will be ripped apart, torn to pieces by the gravitational pull of the larger body. This could happen, and these tiny particles form themselves into this beautiful ring which moves about Saturn now. Saturn is a marvelous sight, even in a small telescope. You see the great golden globe of the planet. Then you see the dark black of empty space between the planet and the inner edge of its rings, and then the golden halo of the ring around it, several shades lighter in tone than the planet itself. One great astronomer has said that Saturn is one of the truly beautiful things in nature. Now, Saturn is the last of the planets that can be seen without a telescope, the last one known to prehistoric man, the last visible planet. Beyond it, of course, are 2 other giants, and the first of these giants is Uranus, beyond Saturn. Now, Uranus, of course, is not visible to us under ordinary circumstances. It was the first of the discovered planets. Uranus moves about the sun, of course, in an elliptical orbit, very much as the others do, but at a distance which is almost 1 billion miles beyond Saturn, 1,700,000,000 miles. Now, we know that most of the planets have their polar axes inclined to the plane of their orbits about the sun. The Earth is one of them. Our poles are tilted away from the vertical, so that at one time when we go about the sun, the relationship is this. This would be in the wintertime. We actually are nearer the sun then. Then, as a half a year goes by, because the axis does not change, you see, the direct rays of the sun fall upon the equator. That is in the spring. In the summer, the northern end of the Earth is getting the benefit of the sun. In the fall, the reverse of spring is true, and the direct rays are falling on the equator, and in the winter we are back to where we started. Now, Uranus has this same trouble, except that Uranus overdoes it a bit. The axis of Uranus is tipped over so far that Uranus is literally upside down. Its poles are pointing directly at the sun. So that as Uranus goes around the sun, at one point in its orbit, its one pole, we can't say whether we call it north or south, is pointing toward the sun. At the first quarter of its orbit around, Jupiter's equator is facing the sun. The next stage, opposite to where we were in the first place, another pole. The other pole is pointing toward the sun. And in the final stage of the cycle, again, the equator points toward the sun. Uranus is another planet with an extremely rapid period of rotation. It spins upon its axis in 10 hours and 45 minutes. Uranus, as I said before, cannot be seen without a telescope. It is the first in a celestial photograph, is not very photogenic. Here it is, a slightly fuzzy greenish disk. Uranus was discovered by one of the immortals of astronomy, Sir William Herschel. Herschel, in 1781, was engaged in making a massive survey of the skies with a telescope that he had built himself. He picked up this strange disc-like object in his telescope one night. A few nights later, he had confirmed the nature of his discovery by the motion of Uranus through the skies. Herschel desired very much to name his newfound planet Georgium Sidus, which is Latin for George's star. Herschel wanted to honor, in doing that, his king, George III. However, the name Georgium Sidus for a little while was called Herschel after its discovery. Now it bears the name of Uranus, which is more in keeping with the names of the other planets. Uranus, in mythology, was the ruler, the overlord of all the heavens. Uranus has 5 satellites. They are all going around in what to Uranus is a normal fashion, that is, in the same direction as Uranus rotates. But because Uranus is tipped over so far and is practically standing on its head, these satellites are all technically retrograde in motion. This is a sort of a guilt by association. Uranus had been going around its orbit for a period of about 50 years after its discovery, when it was found by careful, meticulous observation that Uranus was not following, as it should, the path which was laid out for it, the path which it should have followed when all the known factors affecting its motion were taken into consideration. It was wandering a little bit, deviating from that path. Now, these wanderings in astronomy are called perturbations. And the perturbations in the orbit of Uranus led to the suspicion that there was another body beyond Uranus, farther from the sun, that might be affecting Uranus. 2 young men, one an Englishman, John Couch Adams, and the other a Frenchman, Urbain J.J. Leverrier, set out to find out what this object could have been that was disturbing the orbit of Uranus. They were working independently. Neither one knew that the other was engaged on the same job. And of course, this involves a mathematical problem of the utmost difficulty. Adams, the Englishman, worked on it for 4 years and came up with what he thought might be the answer. That is, the place in the sky where such an object, if it existed, would be found. He sent his figures to the British astronomical authorities, and they weren't particularly interested. They took a few looks, cursory glances, and found nothing. Leverrier, at about the same time, this was in 1841, took his figures to Johann Galle, a very good German astronomer. Galle was not only good, but he had an excellent chart of the skies, he had a fine new telescope, and he had wonderful weather. He looked, and on the very night he got Leverrier's figures, he found Neptune, the 8th planet out from the sun, the last of the giant planets. Neptune is big. It has a diameter, an equatorial diameter of 27,000 miles. It is an oblate spheroid, too, like the others. It has 5 satellites. Neptune has 2 satellites. One of them, Triton, may be even bigger than Saturn's Titan, and hence the biggest satellite in the solar system. The other one near it is a small one. We don't know very much about them because they are very difficult to see and very small. We must assume that Neptune, because of its size, its tremendous size, has the same kind of an unpleasant atmosphere that afflicts the other giant planets. And it is probably very much the same sort of a thing in its construction. Neptune has a day, that is, it spins upon its axis, in about 15 of our hours. It takes Neptune 165 weary years to make one journey about the sun. To sum the whole thing up, and these are the 4 giant planets that we have been talking about today. Now let's consolidate what we have learned about these planets so far. We find that they are very much alike in that they have slow periods of revolution, long years. They have very rapid periods of rotation, short days. They are at incredible distances from the sun. They have large diameters, and in all but one case, they seem to have a surplus of satellites, and their temperatures are almost unbelievably low. These are the sullen giants of the solar system. They are dreadful places, but fortunately at such tremendous distances that as far as man's present efforts to reach them is concerned, they are beyond temptation.
This is National Educational Television.
Today we're going to talk about the Earth, not from a geographical standpoint, but treating it rather as a small, isolated object in space, which of course is just what it is. As such an object, the Earth has a number of motions and gyrations, which are important to the Earth, of course, and to all of us because we live on the Earth. Here are a couple of models which are going to tell us something about these motions. This one is precession. This one illustrates the Earth line, and we'll talk some more about both of those things later on. The Earth is one of a group of small objects in space that are moving about the sun under its control. It is the third of the planets in distance from the sun. There are 9 planets in this system called the solar system. Here they are. Here is the sun. Here are the smaller planets, Mercury, Venus, and the Earth, number 3. Then comes Mars. Then outside of Mars is a belt in which travel a great many minor planets, the asteroids. Then beginning at about 500 million miles from the sun, we come to the realm of the giant planets, Jupiter, Saturn, Uranus, and Neptune. And finally, last of all, there is another small planet, Pluto. Interspersed among these things are a great many other small objects, the meteors and comets. Now, there is a wide diversity of sizes in the objects in the solar system. The sun, the star that controls the motions of all the other bodies, is, of course, the largest. Here is a segment of the sun on the same size scale as the others. The sun has much more than 99% of all the material in the solar system. Here are the small planets, Mercury, Venus, the Earth, Mars, and, at the other end of the distance scale, Pluto. Then here are the giants, Jupiter, Saturn, Uranus, and Neptune. The Earth goes about the sun on a path or orbit which is not a circle but an ellipse, as is the case with the paths or orbits of all the planets. That means that at one time in its journey about the sun, the Earth is a great deal nearer the sun than at the other time. When the Earth is at the nearest point to the sun in its orbit, the point that astronomers call perihelion, it is 91.5 million miles from the sun. At the other end of the scale, when the Earth reaches the most distant point in its orbit from the sun, it is 94.5 million miles from the sun. The mean distance, that is the middle between these two extremes, is 93 million miles, and that's the distance we usually use in speaking about the Earth's distance from the sun. The Earth travels about the sun in a period of time that we call a year, which is 365 days, 5 hours, 48 minutes, and 46 seconds. And in order to make that trip on time and be ready to start all over again at midnight on December 31st every year, the Earth has to go 18.5 miles a second. Now, a little simple arithmetic will tell you that if the Earth travels 18.5 miles every second of a year, the year has a few more than 31 million seconds, the Earth takes a trip of 600 million miles a year, and you all go along. So don't let anybody call you a stay-at-home. You travel. Now, the Earth's orbit about the sun, while it is elliptical, is not an ellipse on one plane. In this model, you can see these lines. They are the apparent paths of the Earth about the sun. Actually, this part of the Earth's speed of 18.5 miles a second is contributed to by the sun's own speed of 12 miles a second traveling through space. And the sun's path is the straight line in the middle. Really, the Earth travels going along with the sun in a very much elongated spiral ellipse. You can see it here. This is the route that the Earth takes through 1 year, traveling with the sun. This is called the Earth line. The Earth weighs 6,600 million tons. That makes it pretty heavy. In fact, it weighs about 5¼ times as much as the same amount of water would weigh. If we were to take a piece of all the planets, the same size, and weigh it, that piece that we got from the Earth would be the heaviest of them all. Now, the part of the Earth that we're familiar with, that we can see, that we walk around on, is considerably less dense, less concentrated than the Earth as a whole. That makes us quite sure that the Earth must have a pretty heavy, pretty solid center. We have proved that to some extent by sending shock waves down through the Earth and recording the effects of these waves on seismograph machines. Now, here's the Earth. Let's take the top off and see what it looks like underneath. There it is, a core probably of iron or nickel iron. And at the temperatures that we know exist in there, about 5,000 degrees Fahrenheit, this must be molten. But at the same time, there's a tremendous pressure on it. The pressure, even as little as 25 miles in from the top of the Earth, is about 10,000 pounds per square foot. So while this is fluid and molten, it is still pretty heavily compressed. Around that center core, there is a rather thick layer of stony material. And above that, another layer, not so thick, of granite and volcanic rock. And of course, the surface of the Earth has been affected by the atmosphere around it, so that it is what we might call dirt. Now, this concentration of material in one small volume, this mass of the Earth, is responsible to some extent for the surface gravity of the Earth, that strange pulling power that keeps us on the surface of the Earth and, of course, everything else. It also makes it necessary for any projectile, any vehicle that is intended to escape entirely from the Earth out into space, to reach a velocity of about 7 miles a second. And that, of course, contributes to the difficulties of launching satellites. This same surface gravity of the Earth, combined with certain effects of the Earth's atmosphere, give us water on the surface of the Earth. And the Earth is the only planet in the solar system that we are sure has water upon it. We know that Mercury, nearest the Sun, is perfectly dry. We are not sure about Venus. We've never seen the surface of Venus. All we can see is a cloak of dense, white, impenetrable clouds. But we have never been able to isolate, to locate any water vapor or oxygen in that atmosphere of Venus. Mars has moisture, but not water. The giant planets, while they are supposed to have a very thick sheath of ice around their cores, are so far from the sun that the temperature never gets up high enough for that ice to melt. This same surface gravity that keeps water on the Earth also holds upon the Earth an envelope of gases that is our atmosphere. Now, the atmosphere is made up of about 78% of nitrogen, 21% of oxygen, and the remaining is composed of traces of several other elements, fortunately beneficial to us. Here are some of the things that happen in that layer of atmosphere which is closest to the Earth. This is called the troposphere. That means the sphere of change or turning, and it is where all our weather occurs. Now, this atmosphere of ours is often used as an example of lightness, lack of weight. Trifles light as air, Shakespeare said. But that isn't so. The atmosphere weighs upon every one of us with a weight of about 15 pounds for every square inch of surface. And most of us have enough square inches of surface in our makeups so that we are constantly supporting a weight of about 14 tons. Now, let's talk about that atmosphere of ours. Here is a picture of it. Here is the Earth, and here is the atmosphere. We believe that the atmosphere extends up to about 800 or 900 miles above the surface of the Earth. We believe that because we can see the aurora, the northern or southern lights at that height. And we know that the aurora is a phenomenon of the atmosphere. Of course, the atmosphere becomes increasingly dense, increasingly less dense as we leave the Earth and go up. Actually, the air is denser at our feet than it is at our head. And of course, that change in density makes projects like the climbing of Mount Everest, for example, very difficult. And it means that airplanes flying above 10,000 feet, which is not quite 2 miles, should have oxygen equipment. The lowest level of this atmosphere is that troposphere that we met a little while ago, the sphere of turning. And almost all of the motion of the atmosphere lies in this layer. As I said before, this is where our weather is. The temperature at the troposphere drops gradually up to a height of 8 or 10 miles, which is as far as that layer goes, until it gets about 50 below zero. Above that is the stratosphere, the sphere of levels, of layers. There, the temperature rises slowly until it gets about 70 above zero at the top of the stratosphere. And it is up in this level, near this level, that these jet streams travel, these strange winds that whip along at 200 miles an hour and that we didn't know anything about a few years ago. Above the stratosphere is a layer, unbelievably tenuous, thin, called the ionosphere. Now, that's a name that's going to need a little bit of explaining. What is an ionosphere and what does the name mean? Well, here is an atom, slightly enlarged, of course. This is an oxygen atom. All atoms are essentially similar in that they have a closely knit group of particles, protons and neutrons and others, which form the nucleus of the atom. Around that nucleus travel other particles, the electrons, which have no mass at all. All of the mass of the atom is here. When an atom is working properly, it looks something like this, with a haze of electrons traveling around the nucleus. Now, in the ionosphere, the atoms there are subjected to a continual, rather brutal bombardment of particles from the sun, which sometimes knock off one or more electrons from each atom. Now, an electron separated from the atom is an ion, and the rest of the atom without its electron is an ion. And this bombardment of those upper levels has caused the separation of many electrons from their atoms, and they and the remaining part of the atom are the ions. Layers in this sphere, in this level, the ionosphere, are responsible for example, the excellence of the reception of our radio programs. When the ionosphere is disrupted by this bombardment of the sun, its reflecting power is destroyed, and we don't get the radio programs, for example, that are reflected up from the broadcasting station down again to our receivers. We think that this same bombardment is also responsible for the aurora. Above the ionosphere, of course, is the exosphere, the border of outer space. In the troposphere, again, is our blue sky. Now, that blue sky is simply the result of impurities in the atmosphere, tiny particles of matter, little bubbles of water, which give us, by their action on the rays of the sun, a sort of a deceptive dazzle that we call the blue sky, and which hides the real sky from us. The real sky is black, with the blackness of space. And if you get up high enough, and you don't have to go very high, 10 or 12 miles, you can see that sky. Now, here are 4 frames from a motion picture film. Look at them closely. You can see the blue sky. See that level of light and where it ends? That is our blue sky. Blue because it is dirty. The Earth's rotation in space, the spinning of the Earth upon its axis, gives us that alternation of light and dark that we call day and night. Now, as the Earth spins, of course, it carries us, wherever we are on the Earth, alternately into and out of light and dark. And we have taken that period of time that it takes the Earth to make one complete spin upon its axis, and we call it a day, and we've divided it up into 24 of our hours. Now, while the Earth is making that one spin, the definite length of time it takes that, the Earth is also, as you see, moving around the sun a little bit in its journey around the sun. Now, that means that the Earth is also traveling on all during a day, and that has an effect upon the way we see the stars at night. For example, suppose we start the Earth here, and here is a star. Now, the Earth is spinning this way, in the way that we call, stars fall on other places beside Alabama, what we call west to east. The Earth is also moving around its orbit around the sun in the same direction, from west to east. Now, suppose we are standing here, just, you see, as we are passing from sunlight into starlight, and we see the star. And as the Earth turns through the night, it also moves around, and the next night we see the star again, but we get to that point earlier than we did the night before, about 4 minutes earlier. Now, that is the way we figure time by the stars. Time by the sun we have called 24 hours. Then we found that time by the stars was a little bit shorter because we overtook the star each day. That is sidereal time, from the Latin word sidus, one of the Latin words for star. And instead of being 24 hours, it's 23 hours and 56 minutes and a few seconds. That is sidereal time. Now, as it goes around the sun, notice that the Earth is not standing up straight. It's tipped away from the vertical. That is what we call the inclination of the Earth's axis. And that inclination, that tip, does not change materially during the year. Remember that word materially. That's an important one. Here we see the Earth during a winter year, and this is why. You see, the North Pole of the Earth points to a certain place in the sky. There is a fairly bright star standing in the sky right over the extension of the Earth's North Pole. That's the North Star, a star in the constellation of Ursa Minor, the Little Bear. Now, all of you know, I'm sure, that you can see the North Star over the extension of the Earth's pole every night in the year. It doesn't move around materially. This is what happens, though. The Earth does move around the sun, and because the axis of the Earth is always tipped in the same direction regarding the stars, it changes regarding the sun. Now watch. Here we are in December. The northern end of the Earth, because of that tilt, is then tipped slightly away from the sun. Up where we live, in the United States, in Europe, in Asia, it's winter. Because, you see, the sun's rays are striking that part of the Earth at a slant. Down here, in the southern half of the Earth, South Africa, Australia, South America, it's summer, because they are getting the rays directly at a point south of the equator. The year begins. We go on around. Now notice that the tilt of that axis will always be parallel to its position anywhere around. It doesn't change. And as we get around 3 months after we started here, we come to a place where the axis, still pointing at the North Star, this time is tipped neither toward nor away from the sun. That is the beginning of spring. The sun then is seen from the Earth overhead at the equator, and it's the 21st of March. So the year keeps on going. It doesn't pause there for us to look things over, but it keeps right on going. We have to catch that instant in passing, as it were. And we get around another quarter of a year. Now notice what's happening. The axis is still tipped in the same way it was. That hasn't changed materially. So at this time, we have the upper end of the Earth, the northern end, where we live, tipped toward the sun. It's summer up here, we're getting the direct rays. It's winter in the southern hemisphere, they're getting the slanting rays. And we keep on going around and we come to a point opposite to where we were in March, where again, that unchanging tilt, not changing materially, is neither toward nor away from the sun, and we have the beginning of autumn, the 22nd of September, and so on. The end of the cycle, of course, occurs when the Earth has completed one revolution about the sun. We get back to that point where the northern half is tilted away from the sun, and it's winter again where we are. Here is the diagram of that same effect. Here's the Earth in June. Here's the tilt of the axis. You see, it's not vertical. Here's the equator, here's the pole, and we live a little less than halfway between the equator and the pole. And you see, in June, we're getting the direct rays. They're hitting the Earth at right angles. Down here, below the equator, South America and so on, they're getting the rays at a long slant, and they don't do nearly as efficient a job of warming up the surface of the Earth. In December, you see the reverse is true. Notice the axis pointing precisely the same way that it was in June, but this time away from the sun. And here, down in South America, they're having summer. They're getting the rays at right angles to the surface of the Earth. We're getting them on a long slant, and it's much cooler. Now, as the Earth goes around the sun, of course, as we said, there are times when it is closer to the sun than the other. The time when the Earth is nearest the sun occurs in our winter time, usually early in January, about the 4th or 5th of January. You'd think that would make a difference. We're nearer the sun in winter, but it's colder. Well, the tip of the Earth, that seasonal tip, counterbalances that. But by the same token, it's summer down in the southern hemisphere. See? When it's winter in the southern hemisphere, the Earth is far from the sun. And again, that seasonal tip compensates us who live in the northern hemisphere for that. But it makes the southern winters colder. The coldest temperature we have ever found on the Earth is at the South Pole, where it's 120 degrees below zero. The northern temperatures are about 30 degrees warmer. Now, long ago, when the Earth was very young and a little softer than it is now, it was also rotating much more rapidly, making a complete turn in about 5 hours instead of 24. That whizzing around forced some of the soft material of the Earth into a belt around the Earth's equator. Here's what happens. Here is an outline of a sphere made of flexible metal strips, and it's very easy to bend, you see. But you can do that same thing by spinning it. Watch. See that? That makes the Earth oblate. This same distortion affects many of the larger planets because they are rotating very rapidly and fluid. That means that the Earth has acquired a belt of excess material around its equator, around its waist, which could happen to the best of us. Now, the sun and the moon, and principally the moon, are not lined up in space with the equator of the Earth. They are on a different plane. We've got a model over here. Remember that precession model, which will show you that. Here it is. And you see they've built a belt of excess material around this Earth. Now, this is the plane, the level at which the moon and the sun generally operate. Suppose we spin this Earth, tilting it just as it's tilted in reality. I'll just spin it, get it going well, and then let go of it. Now watch what happens. Do you see that motion of the pole of the Earth? That is the Earth's effort to counterbalance by spinning the gravitational pull of the sun and the moon upon the excess material around the equator of the Earth. This causes the poles to sweep out great slow circles against the sky, circles which take 28,500 years to complete, to go once around. That means that since the pole actually does very slowly point to a different part of the sky, we should see a different North Star from time to time. We do. We're working on the third of our North Stars now, within man's history, that is. This is called precession, and it affects our view of the stars constantly through the sky. Now, there is one arbitrary point in the sky, that point at which the sun seems to stand against the stars when it crosses the equator from south to north on the first day of spring. That is called the precession of the equinoxes, then, because it makes that equinox seem to slip westward through the skies very, very slowly. Here's what happens. Here's a diagram of it. Here you see the Earth with that same old familiar tip away from the vertical of its axis. Here is the equator with its excess material. Here is the moon, not on the plane of the equator, pulling the equator down when it's on this side, up when it's on that side, but in the same direction, trying to straighten that out, to bring the equator on the same level. The Earth's resistance to that pull gives it that slow oscillation, that wobble, which gives us the precession of the equinoxes. We have no idea what the Earth looks like in space, when it's really out in space. We do have some photographs taken from rockets, which definitely show the curvature of the Earth and show its tremendous cloud cover. And there are some films which have been taken from rockets which show that same thing, and also show the blue sky. See them? Now, we know that half of the Earth, but not the same half, fortunately, is constantly covered with clouds. That would make the Earth a white, hazy object with a tinge of blue, that same blue which is the blue sky, because blue sky works both ways. When you're underneath it, you look up and you see it. When you're outside of it, you look down and you see that blue haze around the Earth. Now, let's sum up a little bit and see what we have talked about today. First of all, we have found out that life can exist only under a rather narrow range of circumstances. It must have a certain range of temperature. It cannot exist below 40 degrees below zero or above 120 degrees above zero. Life must have oxygen and other nutritious gases to use. Life must have water, and life must have energy in the form of radiation. The Earth is the only one of the 9 planets which is situated at just the precise distance from its mother star, the sun, which has just the correct mass to hold these nourishing elements upon its surface to make life possible there. The source of the Earth's temperature is the sun, and if we were too close, it would be too little. If we were too far away, it would be too cold. The source of the Earth's atmosphere is the Earth's own mass, its power to attract these gases to its surface. And that, in a great measure, is the secret of the water on the Earth. The energy, that radiation, which contributes so much to life on the Earth, comes to us from the sun. This is the Earth, the abode of life. We do not know, certainly, whether there are any other planets anywhere that have life upon them. But we know that there are so many stars which are very much like the sun that it seems impossible that some, perhaps many of these stars should not have a family of planets very much like the sun has. And in these families there must be many planets which are at just those critical distances, which have just that mass, which have just the right circumstances to give them life. There must be somewhere out among other stars, perhaps one that we can see at night, other planets with life like the Earth.
This is National Educational Television.
The Earth has one natural satellite flung into its place by nature billions of years ago, and still moving serenely across the skies, lending beauty and mystery to many of our nights. The invasion of space near the Earth by man-made moons has diverted man's attention, perhaps, from the Earth's natural satellite, the moon, its nearest permanent neighbor in space. And obviously the first target for the exploration of space by man. Until a very short while ago, 350 years ago, the moon was regarded with some awe and superstition as a strange phosphorescent object in the sky. The first man ever to look at the moon, or indeed at anything else, through a telescope dispelled that illusion. That was Galileo. And in 1608, he saw the moon as you're seeing it now, through a telescope. Of course, not as clearly as that, for his telescope wasn't as good as the one that we're looking through now. The moon was seen by Galileo and by the other early astronomers to have strange dark areas upon it. And they assumed, by a sort of an analogy with the Earth, that these areas were covered with water and were like our oceans and seas and so on. We know now, however, that these dark areas are relatively smooth places. Here is an artist's idea, perhaps, of the surface of the moon. And we can see some of these smooth regions. We can see the mountains on the moon, perhaps not as weathered as these look, but a little more rugged. We can see the dusty surface of the moon, and we believe there is great dust there. Here is one of those strange craters that we are going to talk about, and the little isolated peaks that seem to rise above the surface of the moon. It's a very strange place. These dark areas on the moon were given by the early astronomers the names of oceans and seas. And we still call them that, although we know that there is no water there, that they are perfectly dry. Here is the moon's only ocean, on the left-hand side of the moon as we see it. And we must wait at least until full moon until we can see that. This is the ocean of storms. It is bordered in this direction by the Sea of Showers, a smaller dark area. And on this side, by the Sea of Clouds. The Bay of Rainbows juts out of that Sea of Clouds. There are 5 other smaller dark regions or seas on the right-hand side of the moon. We can see them here. The Sea of Serenity, the Sea of Tranquility, the Sea of Fertility, and the Nectar Sea, all very happily named. There is one exception, however, and that is the Sea of Crises. And above the moon, the upper side of it, is the moon's Arctic Ocean, if you will, the Sea of Cold. Now we can see a close-up of the Sea of Tranquility and the Sea of Serenity. That dark area, marked with smaller markings and craters, and with that curved mountain range just below it. For there are considerable mountains on the moon. Indeed, the mountains on the moon are relatively much higher above the surface of the moon than mountains on the Earth. Down here are the Leibniz Mountains, some of whose peaks rise above 30,000 feet from the surface of the moon, whereas the highest peak on the Earth is Mount Everest, about 29,000 feet. Here are two peaks which seem to spring abruptly from the general level of the plain, Pico and Piton, rising to heights of about 15,000 feet. And here is a close-up of Pico and Piton. See them casting their sharp shadows over the plane of the moon. And just to the right of them is the great range of mountains known as the Alps, for many of the mountain ranges on the moon have the same names as mountain ranges on the Earth. And you can see cutting through the Alps there like a chasm, the great Alpine Valley. Here are the Alps in relation to the rest of the moon. And here are the Caucasus Mountains. And here are the Apennines. And across here are the Carpathians. One of the strangest formations on the moon are these round depressions, which we call craters. Here is a typical crater. Now, craters is not perhaps the best name for these things. They are not craters as we picture them on Earth, rather steep cones with a small depression in the top. It might be better to call them walled plains, for they are big. The biggest walled plain on the moon is this one. Its name is Clavius, and it is 156 miles in diameter. There are several smaller plains, or craters indeed, inside of the moon. Two of the most prominent craters on the moon are Tycho here, and further up, Copernicus. They are each about the same size, about 54 miles in diameter. And here we can see a close-up of Tycho, of Copernicus rather. The mountains which ring this crater are about 8,000 feet above the level of the plane of the moon, and the center of the crater is depressed below that level. And in the center of this crater, as in the center of many of the large craters on the moon, there are central peaks, in this case a cluster of 7. And you can also see the system of rays, those light markings, which radiate out from the center of Copernicus, overlying the darker areas. These are strange and mysterious. They do not have any height, for they cast those shadows, and they look like lighter material cast out, perhaps, of that crater. There are about 30,000 of these craters on the side of the moon we can see, and most of them have been measured and named. Now, they are named, in most cases, for individuals who have made notable contributions to astronomy. In order to qualify for a crater on the moon, you must satisfy two requirements. You must be a first-rate astronomer, and you must be dead. The causes of these craters, we still don't know. There are many schools. Some say that they are volcanic, although their broad, rather shallow outline makes that a little difficult to believe. Others say that these are the scars left by the impact of tremendous meteors which smashed into the moon ages ago in the great turmoil that attended the birth of the solar system. Still another theory is that there was a sort of a sluggish volcanic action which lifted the crust of the moon up without breaking through it. And then as that action subsided, the material below, the pushing material, sank. And eventually the roof fell in and left these great hollows. There are still, well, some shapes that we believe to be domes on the surface of the moon. The apparent change in the shape and appearance of the moon, its phasing, which was such a mystery to people thousands of years ago, is due to two factors. One is the moon's slow rotation. It's turning upon its own axis, and the other is its revolution, its passage about the Earth. Now, we know this, that one side of the moon is always fully lighted by the Earth. In this little model, here is, of course, the lighted side, and here is the dark side. Now, the lighted side of the moon is that side which is looking toward the sun, for there is where the moon gets its light. It has no light of its own. At this time is the time of new moon, when the moon is generally between the Earth and the sun. And we can see that the side of the moon turned toward the sun gets all the light. The dark side of the moon is turned toward the Earth. At the technical, astronomical new moon, we cannot see anything. A few days later, however, when the moon is moved eastward around the Earth, we can begin to see just the edge of that lighted side. In a little while longer, we can see half of the lighted side. About 2 weeks after new, when the moon has gotten around to the side of the Earth opposite the sun, we can see the complete lighted side, and that is full moon. Of course, we're looking at this thing from an imaginary viewpoint in space, but this shows you what the Earth sees. After full moon, the moon keeps right on going, of course, and we begin to see a lessening of that lighted side. Then we see another half, and finally the cycle is complete when we get around to where the full moon, where the new moon started. Now, here's a diagram that explains that perhaps a little more clearly. Here is the direction in which the sun's rays are coming. This inner ring shows the moon as it is lighted by the sun. Always, you see, a complete half of the moon is lighted. The outer ring shows the moon as we see it from the Earth as it goes around. Here is the Earth, here is the moon as it is really lighted, and here's what we see. We see everything inside of this line. Here we see nothing because there is no light coming to us from the moon. The lighted side is turned away. This is new moon. Here is a very early crescent moon. You see, we are just seeing the edge of the lighted side. Here we are seeing half of the lighted half. Now, half of a half is a quarter, and this is called first quarter moon. Here we see a little bit more than half of the lighted half. This is the shape which we call the gibbous moon. It comes from an Italian word, gibboso, meaning hunchbacked, and this is the hunchbacked moon. Here is the full moon. Opposite the sun, the fully lighted side turned toward the Earth, and we see the full moon. Then another gibbous moon. Then the other half of the lighted half that we saw here last quarter, the other crescent of the moon, and finally completing the cycle around to new moon again. Now we have some excellent pictures of the moon, which are over here, which were taken at one of the great observatories, which show us these phases. Here is what we call the new moon, the early crescent. It shows us just the edge of the lighted side of the moon. And notice that the points of the crescent are turned away from the sun, and of course the curve of the crescent is in the direction of the sun. Here a few days later is the moon almost at its first quarter phase. Then we have the gibbous moon, more than first quarter but less than full. Here is the full moon. And it's at this time, incidentally, that the markings on the moon may seem to people with lively imaginations to resemble the full face of a man. Here is the man in the moon. Then we have another gibbous moon, a hunchbacked moon. Then the diminishing moon. Here is last quarter. The crescent gets a little bit smaller, and finally we have another crescent. But this crescent, you have to get up very early in the morning to see. This is the last crescent. Now, this crescent business may puzzle us. Crescent means growing, but in this case, we have taken the shape for the action. This is called the crescent before new, or the waning crescent, the decreasing crescent. The other crescent is the crescent after new, the waxing crescent, or the increasing crescent. The moon is not very big. It has a diameter of 2,100 miles. which is a little more than a quarter of the diameter of the Earth. Actually, however, the moon's size in relation to the size of the Earth makes it the biggest of the satellites in that relation in the solar system. Now, I don't mean that there are not satellites which are bigger than the moon. There are. But in each case, these satellites are smaller in relation to their mother planet, if you will, than the moon is to the Earth. You might almost call the Earth-Moon a dual planet system. The density of the moon is much less than that of the Earth, about 3 1/3 times that of water against the Earth's 5 1/2 times. And that makes us believe that there is no solid metallic crust to the moon as there is to the Earth. The moon is made up of material very much like that on the surface of the Earth. And that has given rise to one very interesting theory, is the origin of the moon. It is supposed that the moon was flung away from the Earth by the Earth's very rapid rotation in the early days, something like a piece of mud snapped away from the tire of a wheel. And some people have even gone so far as to say that the Pacific Ocean now fills the vast hollow which once contained the material of the moon. However, this is simply a theory and mustn't be accepted yet as fact. The moon moves around the Earth at a rate of 0.6 of a mile per second, or 2,160 miles an hour, and takes 29 1/2 days to make a complete circuit of the Earth, as we see it doing here, going once around. From new moon to new moon, from the one phase to the corresponding phase, takes 29 1/2 days. Now, there is another way of measuring the moon's revolution, and that is by the stars. Suppose we have a star here just lined up at this moment with the moon. Now, as the moon goes around the Earth also moves around the sun. And we shall see that that shortens up this time. Now watch what happens. We have lined up the moon and a star, any star. So we move, and the moon goes around the Earth. But when the moon is again lined up with that star, it has not had time to complete its revolution about the Earth. Now, the first passage of the moon around the Earth was called its synodical revolution. That is a Greek word and means traveling in the same road because the moon and the Earth are moving around together. This passage of the moon around the Earth is its sidereal revolution, or its revolution according to the stars. Sidereal comes from the Latin word sidus, which means a star. The moon moves about the Earth in an elliptical orbit, as do all of the planets about the sun and almost everything else that moves in space. And because of this, the moon is a great deal nearer to the Earth at one point in its orbit than it is at another. At this nearest point is called perigee. Now, you remember our old friends perihelion and aphelion. Well, this is related to it. It comes from the Greek peri meaning near and G meaning Earth. We use that same root for Earth in geography. The distance of the moon at perigee is 222,000 miles from the Earth. The distance when the moon is at the opposite point of its orbit, at apogee, apo meaning far and again G, is 253,000 miles. The mean distance of the moon from the Earth, the halfway point between these two, is 239,000 miles. And that is the distance that is usually used in speaking of the moon. Now, something very strange happens to the moon as it goes around the Earth. The moon is near the Earth. The Earth's attraction, gravitational attraction on it is very strong, and it has slowed down the moon's ability to spin upon its axis until the moon makes just one turn on its axis as it makes one revolution about the Earth. Now, here we have colored this so you can see which side is which. This is the side facing the Earth now, and this is the side away from the Earth. Now, as the moon revolves about the Earth, it turns just once. And the result of that turning is that the moon always keeps the same side of itself turned toward the Earth all the way around. And you can see that this side has gone around the moon. In other words, the moon has made a rotation. But we have never seen but one side of the moon. Now, an eclipse of the sun is one of the most vivid, most awe-inspiring sights that man can see. And, of course, it is the moon that is responsible for an eclipse. The success of the moon's work in this respect is due purely to an astronomical coincidence. The reason, that is, that the moon and the sun fit so neatly together at such times. Actually, of course, the sun is 400 times as big as the moon, but it is also 400 times as far away. So perspective makes them appear to be the same size. Or put it another way, the sun and the moon are both 110 times their own diameters away from your eye. And any round or spherical object, a dime or a soup plate or a basketball, if it is 110 times from its own diameter from your eye, will look to you just as big as the sun or the full moon. Try it with a dime sometime. You'll have to get a friend you can trust to hold the dime, because 110 times the diameter of a dime is about 70 inches and your arm isn't long enough. And take a bit of advice. Try it with the full moon and not with the sun. It's more comfortable that way. Now, an eclipse of the sun is caused by the passage of the moon directly between the Earth and the sun. And it must be new moon, because that is the time when the moon is between the Earth and the sun. At such times, the moon's cone of shadow, tapering down to a point, strikes the Earth. And at the Earth's distance from the moon, 239,000 miles on the average, there isn't very much left of that shadow. It makes a little dark spot on the Earth, about 160 miles in diameter. And because of the motion of the Earth, both rotation and revolution and the motion of the moon around the Earth, the shadow travels very rapidly across the face of the Earth. Here is a diagram of the shadow path of the eclipse of June 20th, 1955. That total eclipse began at sunrise in the Indian Ocean just east of the coast of Africa. It traveled across the island of Ceylon, across the Malay Peninsula, across the Philippines, and lost itself at sunset in the middle of the Pacific. Now, the length of time it took the shadow to go from Africa to the middle of the Pacific is about 3.5 hours. So you see, the shadow doesn't linger very long in any one place. The longest possible time that the moon will completely cover the sun during an eclipse is a few seconds more than 7 minutes, and several special circumstances have to be present to make that possible. The moon has to be at perigee, fairly near the Earth, so it looks big. The path of the shadow has to cross the equator, and the observer has to be on the equator to see the full 7 minutes of such a lunar eclipse. This one in Ceylon was one of those long eclipses, and people came from miles around, astronomers, with their complicated instruments to see it. And what happened? It was so cloudy that very little was gained from the observation of that eclipse. That fate seems to pursue such astronomical events. Now, there are times when the moon does not completely cover the sun during an eclipse. That would have to be when the moon was at apogee, rather far from the Earth, so that perspective made it look smaller. Then, if the observer stood in the shadow, he would see a thin edge of sun around the edge of the moon. This is called an annular eclipse, from the Latin word annulus, meaning a ring, because there is a ring of sun visible around the edge of the moon. Now, here is a film of an annular eclipse, which shows just that effect. There you see the sun and the moon beginning to cover it, beginning to come in. The eclipse always begins from the right, from the west. Generally, this is coming down from the upper right. See the moon creeping over? Now watch. In just a few seconds, the centers of the moon and the sun will coincide. And you'll see. That jerky movement, by the way, means that the man didn't have a machine-operated telescope. There it is. There's the annular eclipse. See that ring around? That is of no scientific value, frankly, because that ring still makes so much light that the wonders that you can see at a total eclipse aren't available. Now, here is a total eclipse. The moon is near the Earth. The observer is in the center of the shadow, and he sees the sun completely covered by the moon, but he can also see one of the phenomena of the sun, the corona, which up till a few years ago could only be seen at the times of total eclipses of the sun. To see a partial eclipse, the observer would have to be out of the main shadow of the moon and in the partial shadow. Then the angle at which he looked at the moon and the sun would leave a bit of the sun still visible all the time. It would never be completely covered up. Now we have some films of several eclipses which have been put together to make a very interesting sequence. But before we go into that, here are some of the reasons, the additional factors that must be present during an eclipse. The orbit of the moon around the Earth does not lie in the same plane, doesn't coincide with the orbit of the Earth around the sun. If it did, we'd have an eclipse every month. As it is, the moon in many cases passes above or below the center line connecting the sun and the moon, and we don't have an eclipse. The moon, however, crosses the path of the Earth's orbit, the plane of it, twice each month. Once from above to below, and again from below to above. And when this crossing of this node, that's what these crossings are called, occurs at the time of the new moon, there will be an eclipse. Now, these circumstances don't get together very often. There can be no more than 5 total eclipses of the sun in any one year, and there are rarely that many. There may be as few as 2, and there are usually 3 or 4. Now, here is that film of the eclipse. This is the eclipse that we just saw on Ceylon. And you can see some of the elaborate and heavy equipment which had to be brought from miles around to see that eclipse. They set it up here, and they drill, and they practice, and they rehearse for weeks to get every bit out of the eclipse, to take full advantage of that 7 minutes. Now, this is an excellent picture, but unfortunately, the eclipse was marred, of course, by cloudiness, as I said. And here we can see those clouds. And the eclipse is almost at total. You can just see the edge of the sun before the moon slides in front of it. See how it's getting darker? And then the light of the sun is almost cut off. And you can begin to see some of these things which are visible around the edge of the sun. These are the great hydrogen prominences that show around there. You can just see them faintly through the murk, through the clouds that were overhead. This was a wonderful job of picture taking, even to get this much of it. And now, in a few seconds, you'll see them on the other side of the moon as the moon slides on across the surface of the sun. There they are. See them down below. There, now it comes out, and watch the light grow. See it spread out. Now, here is another eclipse when the clouds weren't in the way. Now, watch. This is the diamond ring. See that diamond ring? Now, that is the last vestige of moonlight shining through a great gorge or valley up on the moon. And what you're looking at now is the corona, the sun's outermost atmosphere. And this is the corona during a time of very small sunspot activity. It's characteristic then, close to the sun at the poles of rotation, above and below, spread rather wide at the equator. And watch for another diamond ring now coming in from the lower right as you look at this. There must be other mountain gorges down there, and you can see the light of the sun first appearing there. Here it comes. Watch now. The diamond ring will appear at the other side. There, see it? Now we'll see a speeded up motion picture of the moon moving away from in front of the sun. That is the story of the solar eclipse. Comes to the last contact when the moon vanishes from the sun. Now, there can also be eclipses of the moon, but these are caused not by the passage of the anything in front of the moon, but by the passage of the moon through the shadow of the Earth. The Earth has a cone of shadow 865,000 miles in length, and where the moon passes through at 239,000 miles, it takes about 4 minutes to go through. At that time, the moon doesn't disappear. It takes on a strange, weird, reddish color, which is caused by the action of the Earth's atmosphere on the sunlight shining on the other side of the Earth. The bending effect of the atmosphere fills that cone with this weird red light, which we see then. Such are the varying aspects of the changing and changeless moon. It is obviously man's first goal in space, although why he should want to go there very badly is more than I can understand. Perhaps for the same reason that the great British mountain climber Mallory gave when asked why he wanted so badly to climb Mount Everest. Mallory said, "Because it is there."
This is NET, National Educational Television.
In all construction jobs, there will always be large quantities of odds and ends left over. The solar system is no exception. It, too, is full of this debris. On the first night of the 19th century, January 1st, 1801, an Italian astronomer, Giovanni Piazzi, was looking for something in the skies. It was a rather needle-in-a-haystack job for Piazzi, too. He didn't know exactly what he was looking for, and he had to explore a region of the sky which was about 300 million miles wide and which began about 250 million miles from the sun. Now, here is a diagram of the solar system, and we'll find out just where Piazzi was looking. Here is the sun, the controlling factor, and very close to the center of the arrangement. And here are the planets near the sun, the small planets, Mercury, Venus, the Earth, and Mars. Now, to go on out, we have to change our scale to get the rest of them in. Here's where we were at Mars. And outside of Mars is the giant planet Jupiter. And it was in this region between Mars and Jupiter that Piazzi was looking. He found something. He found a tiny planet, 480 miles in diameter, an asteroid. For that is what these miniature planets are called. Piazzi's asteroid he named Ceres, for Ceres was the ancient pagan goddess of his native island, Sicily. In the 150-odd years that have gone by since Piazzi's discovery, several thousand of these asteroids have been discovered, some of them visually, most of them photographically. For an asteroid, because of the motion of its own, will leave a faint trail on an astronomical photograph. Here is such a photograph, and in the center of it you can see a little streak. That streak is an asteroid. The camera, which was regulated to follow the stars, of course, moves past the asteroid, and the asteroid also moves and betrays itself by that tiny streak in space. Thousands of these have been discovered. About 2,000 of them have been duly elected to membership in the solar system by having their orbits verified and confirmed. But there is still a considerable waiting list of asteroids which are standing by, waiting to be officially admitted. Now, Piazzi had what he thought was a pretty good reason for looking in the part of the solar system in which he did. About 25-odd years before Piazzi was searching, there was a German astronomer, Johann Elert Bode, who, with an assist from an earlier German astronomer named Titius, had tried to lay out the plan under which the solar system operated. He did work out an arrangement which is called Bode's law, and under this arrangement of Bode's, there seems to be a gap between Mars and Jupiter in which possibly another planet ought to be. Well, there isn't another planet there. There are a great many tiny planets there. This is the asteroid belt. Now, here is Mars, and here is Jupiter, well outside of Mars, 350 million miles farther away. And in that belt, at an average distance of 250 million miles from the sun, travel these asteroids. We don't know how many of them there are. Estimates run from 30,000 to 50,000 of them, and we probably never know when the last one has been discovered. They're small. Piazzi's discovery, Ceres, is still the biggest of the lot with a diameter of 480 miles. From that size, they range downward to good-sized mountains, a mile or two across. And there isn't very much material in the whole lot of them. We can judge that by the very small gravitational effect they have upon Mars and Jupiter, which are the closest permanent bodies to them. If we were to put all of the asteroids into one lump, that lump would have only 1,000th as much material as there is in the Earth. So you see there is not very much there. Now, most of the asteroids travel in that belt between Mars and Jupiter. Here's a diagram that shows that. Here's the Sun again, here's the Earth, here is Mars, and here is Jupiter. And here you can see some typical asteroid paths. Here's Ceres, for example. Most of them conform. There are a few rugged individualists who go on their own and travel farther away than Jupiter and even farther, and some of them that come pretty close to the Sun and incidentally to the Earth. The closest one of these that has ever come to the Earth, the one that's come closest rather, is Hermes, a very small fellow. And here is, well, this is an artist's idea of what might happen. Hermes is here, less than a mile in diameter, and this, of course, is Manhattan Island. And small though Hermes is, believe me, it would make considerable impression upon Manhattan Island. The asteroids are the last of the members of the solar system to have a personality of their own, you might say. What we have left to talk about today is dust. Dust either clumped together or in individual grains. In the spring of 1910, the world was looking up at the sky with considerable expectancy, for Halley's Comet was due to appear. It did appear, and it was magnificent. I saw it, and I can remember it, or at least I think I can remember what it looked like. My chief memory is of a faint, tapering, greenish tail which stretched halfway across the sky, for the tail of Halley's Comet was over 50 million miles long. Halley's Comet was expected in April, and during that month, astronomers of all kinds, amateur and professional, were looking at the sky. Halley's Comet was picked up the last few days of April as a very faint object by a German amateur astronomer in his telescope. From that time into May, it grew considerably in size and in brightness as it drew near the Sun, reaching its climax about the first week in May. From that point on, it began to diminish in its appearance as it made its way around the Sun and started back to the other end of its orbit, some 2.5 billion miles at the other end of the solar system. Now here is a diagram showing the very elongated orbit of Halley's Comet. When Halley's Comet was here and had that magnificent tail, considerable consternation was felt by many people on Earth because it was known that the Earth was going to pass through the tail of Halley's Comet. And it was also known that there were some pretty harmful substances in that tail. And the general perturbation of the people was not soothed by several enterprising gentlemen who went around selling comet insurance. The Earth did pass through the tail of Halley's Comet. But our atmosphere is so tremendously more dense than the gases in the tail of Halley's Comet that it was a perfect shield, and of course, no harm whatever resulted from it. Now, notice several things about this diagram. Here is the comet coming in from the reaches of space out somewhat beyond the orbit of the planet Neptune. Notice that as it comes in, it develops this tail. Notice the direction in which the tail points. And here, incidentally, is the Earth. This is the Earth passing right through the tail of Halley's Comet. And the comet goes back to the very remote and very cold regions, some 2.5 billion miles from the Sun. Now, comets are just about 99% mystery. We don't know their origin. We don't know where they come from. One modern astronomer, John Oort, says that there is probably a great reservoir of comets somewhere in the outer reaches of the solar system, and that a comet is drawn out of this reservoir by one of the giant planets, gravitationally, of course, and started on an orbit about the Sun. When a comet is out in space, it is rather small and frozen because it's cold out there. The comet is a sphere of frozen gases, and embedded in this frozen gas are a great many tiny, stony, metallic particles, ranging from dust size up to pretty substantial objects. When a comet in its orbit comes near the Sun's radiation goes to work on this frozen sphere of gas, vaporizes. The comet grows tremendously, is distended. Comet diameters may run 30,000 to 50,000 miles, and even in some cases as big as the sun, almost 1,000,000 miles across. But remember, they have no more material than they did when they were tiny little spheres of frozen gas. And a comet comes near the sun's radiation, having vaporized this gas, then works on it and drives some of the gas away from the head of a comet to make a comet's tail. Some of the gas and some of these particles are blown off into space by the forces of the sun. And because the force that makes a comet's tail comes from the sun, the tail of a comet always points away from the sun. When the comet is on its way in from the outer regions of the solar system, the tail is streaming out behind it. When it has rounded the sun and is gone its way out, the tail is pushing on ahead of it. And incidentally, it is the tail of a comet that gives it its name. In the old days, before telescopes, comets, of course, weren't visible until they were close to the sun and had developed considerable tails. These tails looked to the ancients like hair streaming out, blown away. And the word comet comes from the Latin word coma, which means hair. A comet, to the peoples of the olden times, was a hairy star. Now, comets do travel in elongated orbits about the sun, but coming in at all angles, not like the other members of the solar system, almost in the one plane. Here is the central part of the solar system again. And here, in relative size and distance, is a diagram of many of the orbits of the well-known comets. And you can see how far they go. Now, what we see of a comet, the head of the comet, is called the coma. And here is a diagram of that. The very tenuous gases make the head of a comet. And there is, inside of that, a rather condensed, bright region that is called the nucleus. And it is from this comet's head that the material of the tail is blown away, as it were, by the radiation and light pressure of the sun. Comets are terrifically distended, and yet there is very little to them. Perhaps some of you in your younger days have cleaned erasers in a schoolroom and seen the sun shining through the cloud of chalk dust. Well, that's a comet. Sun shining through dust, that's what it is. Very little else. One great astronomer called comets bags full of nothing. Now, as long as a comet stays in an elliptical orbit, it will continue to make repeated journeys around the sun as long as it can stand the trip. Because this radiant action of the sun, this blowing away of gases, is a kind of an erosion, and it wears a comet down a bit. Sometimes a comet will go into an orbit whose curve is called a hyperbole, and then there's trouble. Now, an ellipse and a hyperbole are both called conic sections. They're that kind of curves. This is a cone. Now, if we make a section, a cut through that cone from side to side on a line parallel to the base, the result is a circle. And a circle is a special kind of an ellipse in itself. Now, if we make another cut, not parallel to the base, but again from side to side, completely through, the resulting circle, the resulting figure, rather, the curve, is an ellipse. There is an ellipse. If, again, we cut the cone, this time through the base, in a line which is parallel to the opposite side, the curve that we get is a parabola. It's a little difficult to find sometimes, but there it is. There's the parabola. If we make a fourth cut, again through the base, but this time not parallel to either side, we have a hyperbola. These curves are always a little more difficult than the circles and ellipses. But there is the parabola, you see. Now, a comet drawn out of this reservoir of Oerths by the gravitational force of a planet starts out in an elliptical orbit about the sun. When a comet gets to about the Earth's distance from the sun, say 93 million miles, it is generally traveling at about 23 miles a second. As it gets closer to the sun, the sun's gravitational pull speeds up the comet tremendously. And comets have been known to travel at 300 miles a second when nearest the sun. This is dangerous, though, for that vast speed throws the comet from an elliptical orbit into a hyperbolic orbit like this and whips it off into space in a sort of a celestial crack the whip. It's gone, lost. Now, about 12 comets come into our ken every year. Most of them are far too faint for anything but telescopes. And here is a photograph of a typical faint comet. Never could be seen without a telescope, but about a dozen of these appear each year. We have had an average of 6 big, bright, naked-eye comets every century. We had 5 so far this century. In 1910, of course, we had Halley's, and we had another one. In 1927, there was one, and in 1957, there were 2. One of them, which appeared in our northwestern sunset skies in the spring of that year, was the Aaron-Rowland comet. Another one appearing in the same part of the sky in the fall, in the northwest at sunset, was the Merkos comet. We don't know how many comets there are, really. They come and they go. There are probably about 70 of them whose orbits take them from 3 to 9 years to travel and appear thus regularly in our skies. There are about 40 more whose orbits require a travel that takes from 9 to 1,000 years. And they, too, appear with more or less regularity. But we have seen comets destroyed by the gravitational turmoil of the sun, pulled apart. New ones are coming in, the old ones are going. We just don't know how many of them there are. Comets are usually named for the men who discovered them. Here is Donati's comet, discovered in 1858. This is a drawing necessarily because cameras weren't good enough at that time to take pictures. It must have been quite a job. Donati's comet, after it had been accepted and confirmed, was given a more prosaic designation, the year and a number. You may sometimes see a comet with a hyphenated name, such as the Aaron-Rowland comet here. That means that 2 men discovered it in collaboration, or that one of them discovered it and the other saw it first on its first predicted return. Halley's comet, of course, is the big exception to this system of naming comets. Halley didn't discover Halley's comet. That great comet has been known to return to the Earth with a few gaps in history since 240 BC. Before Halley's time, before the 17th century, comets were thought to be possibly a phenomenon of the atmosphere or some sort of emanation from the sun. Halley became interested in comets from the appearance of the great comet of 1682. And like a scientific man, he began to list and put down every known fact that he could find in history about comets. That got him into some pretty severe mathematical difficulties, which he was unable to cope with, so he went to a friend of his for help, and he couldn't have gone to a better source. For this friend that Halley consulted was Sir Isaac Newton, the Einstein of his day and one of the greatest mathematical minds the world has ever known. Now, Newton was familiar with a work that had been published about 50 years before by an Austrian astronomer, Johannes Kepler, in which Kepler formulated a series of laws which governed the motions of 2 bodies in space about each other. The motion of a planet, for example, about the sun. The motions of 2 stars in place about each other. And, of course, the motion of a comet about the sun. The result of this collaboration was that Halley was able to predict that the great comet of 1682 would return in 1758 and was a member of the solar system. Now, Halley died in 1705. The comet did come back in 1758 and was named for Halley. Probably the most magnificent memorial that any man ever had. Comets do leave a sort of a legacy for us as they pass through sky. Now, we seem to be moving, that is the Earth at least, in its journey about the sun, in a sort of a celestial dust cloud. And comets add to that dust cloud. You remember what a comet goes through when it gets close to the sun, how it's vaporized and the tiny particles in it are free and may be left loose around the sun. Well, those particles are very often scattered back along the path which the comet takes around the sun, as we see here. Here's the comet. And here, behind it, is the debris which it is scattering through the sky. Our Earth, in its journey about the sun, regularly passes through these celestial gravel pits, if you will. And they make what we call meteor showers. Now, a meteor. Well, I know all of you have seen a meteor. You can't stay out very long on any nice clear night without seeing one. It's that little bright streak that cuts across the sky among the stars, and they're commonly called shooting stars. Well, of course, they're not stars, not by billions of miles. For when you see a meteor, it is probably about 20 miles away from it. Meteor is a Greek word that means something in the air. And it is compounded of hot air and a tiny particle, this celestial dust cloud that I spoke of. These tiny particles of stony and metallic material are everywhere in space, and the Earth encounters them frequently. They plunge into the atmosphere of the Earth at speeds that range from 10 to 40 miles a second. At that speed, the friction created by the dive that the meteor takes into our atmosphere heats it up to incandescence and, more often than not, destroys it. But it also heats the air through which that meteor passes, and we see both the glow of the air and the meteor itself. Now, it only takes a meteor about as big as the end of your little finger to make a very noticeable streak in the sky. However, millions, literally, between 80 and 100 million meteors plunge into our atmosphere every 24 hours. Most of them are dust size, far too small to attract any attention. A few of them we do see as these streaks. And indeed, many astronomical photographs have a sort of a bonus in the shape of a meteor streak. The astronomer here is taking something else entirely. And a meteor plunged through the field of his camera and left this streak. This was quite a big fellow, too. Quite a sizable one. Meteors range in size, as I say, from dust size up to pretty considerable fragments, and their composition is practically 99% nickel iron. There are some with more stony material and some with a sort of a glass-like texture, which are known as tektites. The particle, the little bit of material that causes a meteor is a meteoroid. Now, if a meteoroid has enough bulk, enough mass to it, to last through, it is a meteorite. A meteorite is a meteoroid which has arrived. Now, you remember I talked about meteor showers when we were speaking of the debris that a comet left behind us. About 20 times a year, the Earth does pass through one of these old trails, and we see an unusual number of meteors. Now, don't let the word shower fool you. A meteor shower means an incidence of maybe 10 times as many as normal. Now, if you go out on a night and see one meteor in a shower, you may see 10 if you have the patience. There are a couple of notable ones which are really worth waiting up for. One is the Perseid meteor shower, which occurs on the nights of the 11th and 12th of August. It's called the Perseid shower because the meteors are posed, as it were, before the far more distant stars of the constellation of Perseus. And these stars, believe me, have nothing whatever to do with the shower. They just give it a name. Another one is in October, when we have the Orionid shower. These meteors are seen against the splendid backdrop of the winter constellation of Orion. There have been some pretty notable showers in the past. One of them occurred in November of 1833. Now, that, too, was before cameras, and we have to take the artist's word for this. This was terrific. Actual records indicate that the meteors did appear many thousands to the minute and probably frightened the poor people of that day into a state of reform. When a meteoroid, that particle, is big and robust enough to stand this plunge, it becomes, as I said, a meteorite. There are some pretty considerable meteorites. Here is the biggest one in captivity, as it were. This is the Onegito meteorite in the American Museum Hayden Planetarium in New York. It weighs 34 tons, 85 pounds. It's about 12 feet long and about 8 feet high. It was brought back from Greenland, where it was found by Admiral Peary about 50 years ago. Now, here's another one. Not as big as the Onegito, I'm glad to say, but this is considerable of a chunk. It weighs 24.5 pounds. Now, to put it in terms of water, 8 quarts of water would weigh as much as this little fellow does. We hope very sincerely that most of these big fellows have been swept out of space in the ages that have gone by. But there is evidence upon the Earth that the Earth has been struck repeatedly by big meteors. Fortunately, in most cases, in times gone by. There are a few modern instances. These collisions, this celestial bombardment, has left its scars on the Earth. And one of the best known and most easily accessible of these scars is the meteor crater in Arizona, near the town of Winslow. This is a pit about a mile in diameter and about 2,500 feet deep. No big piece of meteor has ever been found there, but a great many tons in the aggregate of smaller chunks have been picked up around the edge of this hole. This one we just saw, incidentally, is a meteor crater meteor. With all this incessant bombardment, the luck of the human race still holds, for there are no cases at all of anyone ever being killed by a meteor. And the most recent case of a person ever being struck occurred in 1954, when a woman in Silacoga, Alabama, who was dozing on her couch, was hit a glancing blow by a small meteorite whose progress was slowed by coming through the atmosphere and through the roof of her house and the ceiling of the room, and it bounced away from her. It bruised her, but the biggest trouble was who owned the meteorite. And finally, it was awarded to her, which was only fitting since she caught it. These are the minor members of the system, the asteroids, these tiny planets, comets, dust, meteors, more dust. Now, where did the whole thing begin? There have been many theories of the origin of the solar system which haven't stood up against physical laws. The most modern one is that by von Weizsäcker, who postulates a great disk of gas, dust, and debris with a diameter equal to the diameter of the present solar system, a center of the sun, which is spinning around at varying speeds. These varying speeds, according to the laws of angular momentum, decrease as we go out from the sun. Rapid here, slow here. And in between, these circles are vortices. This is the vortex theory. And like tiny ball bearings, in between these circles are the little accumulations of this dust and gas that became the planets. Now, the problem is not to find a nice, convincing way that the solar system was formed, but to find a good reason why it was formed at all.
This is National Educational Television.
Great glowing clouds are blown thousands of miles into space from the seething, turbulent surface of the sun. This same terrible energy, subdued by distance, gives life to the Earth. Our sun is a star moving through space and carrying with it all the train of tiny objects which make up our solar system. The path which our sun takes into space is represented in this model by this straight line that you see going right straight through it. It's moving along that line at a speed of about 12 miles a second. And as the planets move with the sun but pass in orbits about it, their paths are represented by a rather elongated spiral which goes continually around and around the sun, following it as it moves. This motion, of course, is continuous. It doesn't stop. It keeps right on going. Now, the direction in space toward which the sun is moving is a point in the eastern edge of the constellation of Hercules. It is just about here. And here you can see the constellation of Hercules represented by the conventional gigantic figure of a giant kneeling upside down. Now, don't let that constellation figure worry you. If you were to go out on some fine, clear night and look up and see a giant upside down kneeling in space, you'd better go back in and lie down again because something is wrong. This is just to identify the figure. And here is the place toward which the sun is moving. This is called the apex of the sun's way. And it was discovered by one of the astronomical greats, Sir William Herschel. He found it by observing that the stars in that direction seemed to be moving apart from each other in a motion which was independent and separate from any motions they may have had of their own, just as the trees in a forest move apart as you approach them and come to them. There have been some slight alterations to the first point which Herschel selected, but it is generally very close to this point in the eastern edge, as I said, of Hercules. There is a corresponding point on the other side of the great celestial sphere, which can be seen only from the southern part of the Earth, which is called the antepex of the sun's way, because there the stars seem to be pulling together as the sun moves away from them. Of course, this motion, too, is continuous. It never ceases. The sun keeps right on going. And in billions and billions of years, when the sun finally does arrive at this point in space, there will be new vistas opened, a new apex of the sun's way, and undoubtedly new star formations or constellations which we can see then. To us who live upon the Earth, the sun is an extremely important star. It is bright and it is hot. So bright, in fact, that none of us can look at it, even though the sun is 93 million miles away from us. And it is hot. The surface of the sun has a temperature of about 10,000 degrees Fahrenheit. Now think what that means. If it were possible, for example, for you to bring your oven up to a temperature of 10,000 degrees, this is what would happen to your stove. It would melt everything in it, every metal, become for an instant a little pool, a little puddle of glowing metal, and then vanish in a bright cloud of gas. For there isn't any element that we know of that would not instantly become a gas at a temperature of 10,000 degrees. Temperatures in the interior of the sun, however, must literally be measured in the millions of degrees. The inside of the sun has a temperature of somewhere between 30 million and 50 million degrees Fahrenheit. As we see the sun, it is most impressive. Here is a bit of the sky, and it would take 720 suns to make a complete circle of suns edge to edge going right around the sky. The diameter of the sun is 364,000 miles. It would require 345 Earths placed edge to make a belt completely around the sun. And if we were to hollow out the sun, make a sort of a super bowl out of it up there and fill it up with Earths, we'd need 1,300,000 Earths to fill that bowl. The light of the sun, measured in terms of the full moon, is equal to 400,000 full moons. Now, there isn't room for that many full moons in the sky, but that's what there'd have to be if we were to equal the sun's light in that way. And if we took all the stars that we can see and put them all together into one gigantic superstar, It would take 6 million of those to equal the light of the sun. The sun is a gas. At those temperatures it has to be. It's not solid. So it is not as dense as a solid body of the same size would be. Still, there is enough material in the sun to give it a tremendous gravitational pull. It has a surface gravity which is about 28 times the surface gravity of the Earth. If a normal man weighing about 150 pounds could possibly walk around on the sun, he'd weigh 2 tons. And unless he had considerably more strength than he had on Earth, he couldn't even stand up. He couldn't support himself. It is this tremendous gravitational pull of the sun toward the center that gives the sun the very clean outline that we see when we look at the sun. And you can see it here, how sharp that edge is, even for a ball of gas. And speaking of seeing the sun, I think this is a good time for me to give you all a word of caution, which I hope you will take seriously. Never, under any circumstances, look at the sun through a telescope or any other magnifying instrument. I'm sure all of you have taken an ordinary desk magnifying glass out into the yard and focused the sun's rays through it upon a piece of paper and watched that paper burst into flame. Well, don't put your eye in the place of that paper, for a telescope is simply an elaborate magnifying glass. If you have a telescope or have a chance to use one and want to look at the sun, do it this way. Point the telescope at the sun. Then take a white card and hold it at the proper distance from the eyepiece. You can tell, just move it back and forth a little bit. And the image of the sun will be projected through the eyepiece on that card with all its details. And you can look at it and your neighbors can look at it at the same time. This is very much the most friendly way to use a telescope. The part of the sun that we can see, the great central glowing sphere of the sun, is called the photosphere, the sphere of light. And it is the part of the sun that we see in photographs of the sun, as you see it here. Now, the surface of that photosphere, barring these incidental little blotches, which we'll talk about later on, looks to be fairly evenly brilliant. Actually, it is not. The surface of the sun is really made up of innumerable tiny islands of glowing gas, little bright islands. They're very short-lived, only 3 or 4 seconds at the most. They are anywhere from 300 to 500 miles long and elongated oval in shape. They look very much like grains of rice, and in astronomy they are called rice grains. Now, here is an excellent close-up of the surface of the sun showing these rice grains, these little islands of brilliant glowing gas which make up the general surface of the sun. You can see them here, and they come and they go. They're not stable at all, and the surface of the sun is actually a seething, turbulent bed of these light islands. In between these islands and surrounding them are lanes of darkness, comparative darkness. These are actually bright. They look dark because they're not quite as bright as the islands themselves. These lanes change too as the little rice grains change and sometimes develop into dark areas which are called pores, and these pores occasionally grow into what we know as sunspots. In addition to these rice grains of brilliance on the sun, there are other more brilliant appearances which are called faculae, which is Latin for torches. Now, here are 2 pictures of these bright faculae. You can see how much brighter they are, indeed, than the general surface of the sun. And these faculae are usually associated with those dark areas which are sunspots. Now, sunspots were not known at all until the advent of telescopes. Galileo, who was the first man ever to look at the sun or indeed at anything else with a telescope, first saw these spots. And Galileo paid for his observation of the sun, for he died blind. Sunspots come in all sizes. They may be tiny, so tiny that we can't see them by any means, or they may be enormous. There have been spots known to reach an area of 250,000 square miles, similar to the one that you can see here now. They are tremendous things. And they are rather complicated, too. Here is a picture of a sunspot group. Now, sunspots are generally composed of two definite areas. There is a dark area, a central area, which is called the umbra, which means the shadow. And surrounding that dark area, there's an area which is not quite so dark, which is the penumbra, or the almost shadow. And in many sunspot groups, the penumbra forms a continuous region around several very much darker groups. Now, in another picture of a sunspot group, we have a very interesting size comparison for you. Here we can see another sunspot group with its umbra and the penumbra. And down in the very corner of this picture is a little round dot. Now, that is artificial. That is drawn there, and it is the size that the Earth would be, about 8,000 miles in diameter. Now, see how many times that Earth could be dropped into one of these sunspots without even touching the sides. These sunspots are often likened to storms on the surface of the sun, but they are not. They don't move of their own accord through the gases of the sun. They are centers of terrific turbulence, however, of tremendous magnetic strength. And they have a tornado-like whirling quality which causes them to bore holes into the bright surface of the sun. The sunspots have, however, given us some very important information about the sun. Sunspots are carried around the sun by the rotational motion of the sun itself. Now, here is a series of pictures taken at intervals of a day or two. And we can begin from the top. We can see the travel of this sunspot group from left to right as we look at it. The sunspot is not moving of itself through the sun. It is being carried across our sight by the motion of the sun. And this rotation of the sun has been divulged to us through sunspots. And it tells us that, contrary to anything which is a solid sphere, the sun does not rotate evenly. The equatorial regions of the sun rotate completely around the axis of the sun in about 25 days, the most rapid part of the sun's surface. Then, the polar regions of the sun, at its poles of rotation, take about 35 days to travel completely around the sun. Sunspots have been observed for a long time, and in about 1825, it was discovered that there was a cycle of the coming and going of spots. There are periods when there are few, if any, spots on the sun. It seems completely clean and bare. And it has been found that the length of time between these two low points of sunspot activity is, on the average, 11.5 years. Now, in between those low points, there are peak periods of activity when there are a great number of spots on the sun. But the peak periods can come at any time between the low periods. They may follow a low point very closely, or they may just precede the next low point. In October of 1957, we passed through a peak of sunspot activity such as had never been recorded before. Now, that was known to be coming, and that is the reason why the period from June 1957 to December 1958 was selected for the International Geophysical Year. The activity of the sun are a very important part of that great study of the Earth and its surroundings, and it was chosen so that we could get the benefit of this activity of the sun. Now, this boring effect of these sunspots into the sun forms apertures out of which some of the terrible energy of the sun can escape and drive ahead of it invariably a great many minute particles from the sun, drive them out millions of miles into space. And we, very often, we on the Earth, are in the path of this blast of particles from the sun driven out. And here is a diagram which shows that happening. Here is the sunspot. The energy forces these particles out until they reach our Earth with its atmosphere and its magnetic fields. These spots are guided toward the Earth by the magnetic currents of the Earth. And when these spots strike the uppermost level of the Earth's atmosphere that we call the ionosphere. They have a very definite effect upon us in our daily lives. It is this ionosphere which contains the reflecting layers by means of which we can receive radio transmissions and by which we can accomplish radio telephone conversations. Now, this impact of particles from the sun very often disturbs this ionosphere to such extent, and such an extent that this reflective ability is lost, and our radio transmission is poor, and transatlantic wireless telephone conversations often go dead right in the middle of a word. By way of compensation for that, however, it is this same bombardment of the Earth by particles from the sun that give us that beautiful flickering light that we call the aurora. The particles in our atmosphere are excited by this bombardment and produce the aurora for us. Sunspots usually come in pairs. We don't know just why this is, but there is a theory, and it is still very much of a theory, that there may be a tunneling effect in sunspot pairs, that we are looking at the two ends of a shallow tunnel that goes below the surface of the sun and emerges in another spot. One strange thing about these pairs of sunspots is that as they go along, the leading sunspot of a pair, leading that is in the direction of the sun's rotation, seems to retain its identity and remain a spot, while the following sunspot is usually broken up and disintegrates. Just why that should be, we do not know, but there is a great deal that we do not know about sunspots yet. Now, the central glowing body of the sun, the photosphere, is surrounded by several layers of almost transparent material, gases of course, which might well be called the sun's atmosphere. And the effect of that atmosphere, as we see the sun, is to dull the edge of the sun. Now you can see very easily in this picture that the central part of the sun seems far brighter than the edge of it. This is called a darkening of the limb, and is the effect of the light of the sun passing through a fairly shallow layer of gas, the single layer that we see here directly over the center of the sun, or having to pass through a great many thousands of miles of this gas as it comes from the edges of the sun, very much as we look at a sunset through the layer of dense atmosphere which lies directly above the surface of the Earth. Now, this atmosphere of the sun is rather complicated and has some very interesting effects upon the sun. Here is a diagram of it, and here we can see the glowing central sphere of the sun, the photosphere. Now, if we were able to get that light from the photosphere and pass it directly through an instrument built around a prism, the effect would be that we would see a number of very bright lines parallel to each other. Above this photosphere, however, lies the first of the sun's layer of atmosphere, which is called the chromosphere. It is named that way because of its color. It is a very bright pinkish color. And the lower level of this chromosphere, which is considerably cooler than the surface of the photosphere, absorbs some of the terrible energy that comes out of the photosphere, and absorbs it to such an extent that it makes the bright lines which would be produced by the photosphere look dimmer and fainter and darker to us through a prism. The upper regions of the chromosphere are where we can see the sunspots as we see them, and which have those magnificent fountains, those geysers of glowing gas, which are called prominences. Now, these prominences cannot be seen, indeed the whole chromosphere cannot be seen on the sun except at times of a solar eclipse. But here are films of those prominences, those geysers of gas. Now, we are looking at about 400,000 miles of the edge of the sun. And you can see that those prominences are going out sometimes 50, 100,000 miles away from the sun. These pictures are time-lag pictures. In other words, the action that takes place takes considerably longer, about 100 times longer than you actually see it. But this tremendous activity is fascinating. Here are what they call coronal prominences. They start high up above the sun, apparently, and are not seen until they appear there and seem to stream downward. These are flares. We are now looking directly down at the sun. And these are these tremendous bright focuses of that activity of the sun that I spoke about when the sun is pouring out its particles into space and bombarding the Earth. Now, above the chromosphere is the outermost level of the sun's atmosphere, the corona, that pale, beautiful halo of light that we can see, again, at times of total eclipse, and only very recently by means of special instruments. And again, we can see a film, a photograph of that solar corona here. Here it is. You can see that. That is taken at an eclipse, and you can see those glowing streamers of gas coming out from all sides of the sun around the dark bulk of the moon. Now, the corona changes shape according to the sunspot condition of the sun. At periods when there is very little sunspot activity, the corona looks very much like this. And as you can see, the polar regions of the sun have the corona very close to the surface of the sun. And these little sharp rays called spicules give the sun an appearance as though it had just had a crew cut, while the corona in the equatorial regions extends out considerably farther from the sun than it does at the poles. Now, this whole picture is shown here at an actual film of an eclipse. You can see just what is happening there. This is a corona taken at a minimum sunspot activity. And if you watch it, you can see that it seems to move, it pulsates. Actually, that is not a motion of the corona. That is a variation in the intensity of the light that you see. It's growing brighter and fainter and brighter and fainter. And frankly, some of this apparent motion of the corona is partly due to the camera and the way that light registers on camera film. But this pulsation, it does exist and is a pulsation in intensity rather than an actual motion in the corona itself. This corona gives about half as much light as the full moon at times of eclipse. Now, if we take another picture of the sun, this time during a period of tremendous sunspot activity, see what a different aspect the corona has. As a whole, it is much more evenly distributed and evenly spread out around the sun. But the distances in every case are greater. And it is possible that these gases are forced out from the surface of the sun farther by the tremendous activity going on there, which escapes in some manner from the center of the sun through these sunspots. There may be times at periods like this when these streamers, these coronal streamers, reach millions of miles into space and may extend even as far as the Earth. Of course, no possible harm can come to us then because this is very tenuous gas, very, very thin, and the Earth's atmosphere is so much more dense that it effectively bars us from any activity or whatever might result from that contact. There is a tremendous mystery hidden in the corona here, too. Measurements of the temperature in the outer regions of the corona, sometimes as far as 1,000,000 miles from the surface of the sun, a whole solar diameter away, show that the atoms there are behaving as though they were at a temperature of about 1,000,000 degrees Fahrenheit. Now remember that the surface of the sun has a temperature of about 10,000 degrees, and yet sometimes as much as 1,000,000 miles away from that surface, the temperature is 1,000,000 degrees. The smoke of the bonfire seems hotter than the fire, but we don't know why. Now, when I spoke of fire there, I didn't want to mislead you. There isn't anything burning on the sun at all. There is no consumption. In fact, if the sun were made completely of the finest coal, it would have consumed itself in 5,000 years, and where would we be? What is going on there is a series of 6 very complicated thermonuclear reactions. And the whole result of this chain of reactions is to transform 564 million tons of hydrogen into 560 million tons of helium every second of the sun's existence. Now, this means that the sun is losing 4 million tons of its mass every second. That loss, that matter, is transformed into energy. And that energy is the light and heat that we get from the sun. The sun produces 5 million trillion tons of energy every second. Now, the Earth doesn't occupy very much of space. And the proportion of that energy we get is just 1 part in 2 billion. But at that, it is 70,000 horsepower per square foot of the Earth's surface, or about 5 million horsepower per square mile. Now, that is more energy than man has been able to manufacture in all the time he has lived upon the Earth. This is our sun as a sun, the magnificent sun that gives us life and heat. And since our sun is a star, it is extremely important to us because it is the only star near enough to us for us to be able to see its surface. And remembering that the sun is a star, how does the sun compare with other stars? Frankly, it is an average star. If we were able to put our sun as far away from us as most of the bright stars are that we can see every night, we wouldn't even be able to see the sun. Now, there is a star seen from the southern part of the world, which is almost a twin of the sun, a counterpart of it. And it happens to be the sun's next-door neighbor, the nearest of all the stars to the sun. It is in the southern constellation of the Centaur, and it lies not far from the Southern Cross. Now, here is the Southern Cross, right in the center of this picture. And here you can see 2 bright stars near it. The farthest of those stars from the Southern Cross is the star Alpha Centauri, the nearest star in space to the sun, and this is what our sun would look like if it were 26 trillion miles away, for that is a star very much like our sun in every respect, size, brilliance, and so on. Here is the sun, a small, average star, but important to us. And man has had to descend a little from the high position he once occupied in the center of the universe and is guided now by an average star.
This is National Educational Television.
In this program, we are going to talk about time and distance. Distance has always been one of the major problems of astronomy, as we shall find out when we talk about it in the second part of the program. And timekeeping have always been functions of astronomy. For we get our time from the motions of some object in space. In most cases, that object is the Earth. You see, we live on our clock. Now, primitive man must have watched the sun rise and set and move across his sky for thousands of times before he had any conception that here was a cycle which he could use to measure an interval of time. It gave him that alternation of light and dark that we call the day. Now, we know that the sun does not actually move across the sky. We know that what we see is really a motion of the Earth. that the Earth is rotating from west to east with the sun fixed out here, and that as we ride around on the surface of the Earth, our horizon really falls away and lets us see the sun rising, and the horizon as we leave it comes up and makes the sun set. The motion is one of the Earth and not of the sun. And the day was undoubtedly the first natural divisions of time of which man became aware at all. Now, the day is a very convenient measure of time, but it has its limitations. How many days till your birthday? Well, you probably won't know unless your birthday is next week. But there is a need, and always has been, for a longer division of time, and that longer division, again, due to some motion of an object in space, was waiting there for man to discover. And that is the month. Now again, man in those far-off times must have watched the moon, thousands and thousands of nights, moving across the sky, and he must have been awestruck by its apparent change in shape as he watched it go. And it took him a long time, I'm quite sure, to realize that here again was another regular, constantly recurring cycle by which he could measure an interval of time. This month, this moon month, you see, moon and month must come from the same word root. This natural month is only 29 and a half days long. Now, 12 times 29 and a half is only 354. So the moon doesn't fit evenly into the year. And man tried to adjust himself to that condition by having an extra month every third year for a long, long time in order to make things come out right. And this year that we're talking about was surely the third natural division of time that man discovered, and that, again, is due to the motion of an object in space. This time, to the motion of the Earth around the sun, the Earth's revolution. Now, we know that the Earth is tipped from the vertical on its axis. And as we see it here, the tilt of that axis is such that the northern half of the Earth, on which we and on which our primitive ancestor lived, is tilted toward the sun. And that means that it's summertime up there. Now, in the spring and in the summer, things are growing. And primitive man ate, and so do we. But we have means of storing things up for the seasons in which things do not grow. And that happens 6 months later, when the motion of the Earth has brought it around until this time, the tilt of the Earth's axis brings its northern half away from the sun. And it's winter and cold, and things aren't growing, and primitive man went hungry. Now, the year to him was the year of the seasons that we have just seen. The year of the stomach, if you will, the year between hungers. And it probably wasn't until a great many of these years of the seasons had gone by that primitive man realized that there were, as he thought, 365 days between two successive hungry periods. Now, we know from our ability to measure more accurately that the length of time it takes the Earth to make precisely one trip around the sun is 365 days, 5 hours, 48 minutes, and 46 seconds. But for thousands of years, man believed that it was an even 365 days. And of course, that belief soon threw the calendar and the seasons out of step. And I suppose people began to celebrate spring holidays on the previous winter or something like that. Until at last there was a man who had the knowledge and the authority to set things straight, and that man was Julius Caesar. Julius Caesar, with the help of some Roman astronomers, found that the year was 365 and a quarter days, as he thought. So, in order to set things right and bring the calendar back into step with the seasons, Caesar decreed, as he had the power to do, that the year that we call 46 BC should have 430 days. And it did, and it was known thereafter as the year of confusion. Now, that put the calendar back in its place again. And in order to keep it there, and because Caesar believed that the year was 365 and a quarter days long, He said we can't add a quarter of a day to each year, but every 4 years we can pick up those quarters and have an extra day, which we will do. And Caesar invented leap year. Now, that was fine, except that we know from our knowledge that the year is actually 365 days, 5 hours, 48 minutes, and 46 seconds, as we said, that Caesar was 11 minutes and 14 seconds out of the way. By the year 1582, the situation had gotten so far astray the other way that Pope Gregory, one of the very influential men of the time, suggested another reform. He said, Caesar has given us too many leap years. We're falling behind. We have to eliminate some of these. And Pope Gregory produced a plan for eliminating 3 leap years in every 4 centuries. Gregory said, if the century year is divisible by 400, it shall be a leap year, but not otherwise. Now, that means that the year 1200 is a leap year. You can divide it evenly by 400. 1300, 1400, 1500 are not leap years. 1600 is a leap year, but 1700, 1800, and 1900 were not leap years. And the next century year that we have that is a leap year will be the year 2000. Now, that is the calendar which we use today, the Gregorian calendar named after Gregory. But there are still 28 seconds a year that remain to be accounted for. Now, that doesn't sound like very much, but you know, by 4500 AD, that will have added up to another day. And I suppose that 4500 will be a leap year, although normally it should not be one. Now, there are the 3 natural units of time. We have talked about the day, which is the Earth, making one complete spin upon its axis. We have talked about the month, which is the moon, making one complete revolution about the Earth. We have talked about the year, which is the Earth, making one complete revolution about the sun. Now, man has taken these natural divisions of time and divided them up into smaller artificial time measures, hours and minutes and seconds. And here are some of the instruments that man used long ago to measure these smaller artificial time divisions. Here is a King Alfred candle whose alternating rings of white and black were supposed to burn each an hour, and which helped him keep track of the time. Here is an oil lamp whose reservoir held just enough oil to burn for 12 hours, and the passage of time could be gauged by the level of the oil remaining after a certain period of burning in that reservoir, as measured off on this metal band. And here, of course, is an hourglass, a sand glass, whose sand falls through it in a certain stated period of time. Now, we know that time is measured by the rotation of the Earth upon which we live. And we know that the Earth rotates in the direction that we call from west to east. Again, remember that the sun, to all intents and purposes, standing still out here, while the Earth is rotating around before it. So that our time comes to this part first, and then progressively moves westward. Time moves from west to east because the Earth moves from east to west. We know that the Earth's equator is a great circle. And we know, too, that all circles are measured off in degrees, and that every circle, no matter what its size, has 360 degrees. Now, if it takes the Earth 24 hours to make one complete turn, that carries us through 360 degrees, so that we move at the rate of 15 degrees an hour. And every hour, the Earth turns through 15 degrees of its own circumference. Knowing that, man has arbitrarily divided up the Earth into time zones, which are 15 degrees wide. And time is the same, simply by custom and agreement, all through one of these standard time zones. Actually, it isn't, because, of course, time must reach the eastern edge of a certain zone before it reaches the western one. But it's much more convenient to consider it that way. There are 5 of these time zones crossing the United States. And, of course, in these time zones, in different time zones, time is different. Here is a clock, which is set so that it registers 12 midnight at New York. Now, let's go around a little way, and we see that it is 5 o'clock the next morning in London. London has already had 5 hours time that we have not yet had. Astronomers have to use still another variety of time. Time relating to the stars, for that is where the main interest of astronomers lies. And again, that is caused by a motion of the Earth. Now here is the Earth, and this little marker on it gives us an indication of how it turns, and let's say that you are the star. Now as the Earth turns from west to east, it also moves in the same direction along its orbit around the sun. And as you can see, here comes our little marker again, facing you, the star, but this is before the Earth has made a complete rotation, a complete spin on its axis. So that the sidereal day is a little shorter than the civil day, the regular time day. There is a need for scientists, navigators and the like, to have a universal Earth time, and universal time is just what this is called. Universal time is time at the Greenwich meridian, the beginning of the point of measurement of distance east and west upon the Earth is also universal time, and all other time is related to that. Now let us take a quick review of the 3 varieties of time that we have been talking about. Civil time, universal time, sidereal time. Here are their hours. The sidereal hour, as you see, is a little shorter than the other 2. Here are their days. And again, the sidereal day is a little shorter than the civil day or the universal time day. Here are their years. But this time, the sidereal year is 1 day longer because of that little makeup of time each day that it picked up. Now, we've talked about the 3 natural measures of time: the day, motion of the Earth; the month, motion of the moon; the year, again, motion of the Earth. And time has overtaken us now, and we must consider that major problem of astronomy that we spoke about a little while ago, distance. It was all right for us to use the mile as long as we remained inside the solar system. It was a very convenient unit of measurement. But once we begin to leave that, we're in trouble if we still use the mile. For the very next object in space, beyond the sun, the nearest star to the sun, is 26 trillion miles away. And I don't think anybody outside of the Treasury Department has any idea what a trillion of anything is. So, in order to encompass these vast distances, we've got to use another measure. And we get that measure from the speed of light as light travels. Now, we know that light travels at the rate of 186,000 miles every second. That's about 7 times around the Earth at the equator every second. There are more than 31 million seconds in a year, so that the distance that light travels in a year is 5,880,000,000,000 miles. Now, at that distance, I think astronomy can be a little bit flexible. Call it around 6 trillion miles. That is a light year, the distance that light travels in a year at the rate of 186,000 miles a second. Now, on that same time scale, with that same speed of light, which is invariable, it takes light 1 1/3 seconds to reach us on the Earth from the moon. It takes light 8 1/3 minutes to reach us from the sun. It takes light 6 hours to reach us from Pluto, the most distant planet in the solar system. And it takes light 4 1/3 years to reach us from that nearest star I spoke of, Alpha Centauri. Now, how is man ever going to measure these tremendous distances, 4 1/3 light years? Well, the surveyors have taught us how to do that. A surveyor can measure the distance across a river or a lake without getting his feet wet. He does it this way. He sets up a marker on one side of the river across which he wishes to measure. Then he crosses the river again by any convenient bridge, doesn't matter where, and measures off a line whose distance he knows accurately. Then he sights back at his marker from first one end of the line and then at the other end, so that he has the angles from this end of the line to his marker and from this end of the line to his marker. Now, by trigonometry, if you have the length of one side and the angles at each end of that side of a triangle, you've got the triangle, and your surveyor has his distance that he wanted. The same thing can be done in astronomy. And we have set up a little experiment here in the studio to show you. Here are two spheres, this one and this one, and they represent two stars, this one far in the background, and this is the star in which we are interested and whose distance we want to measure. Now, we have arranged two television cameras standing side by side, focused upon these spheres. Now, we are going to see them first through the right-hand camera and see what happens. Now, do you see that the sphere, the front sphere, the one which is a plain color, is a little bit to the left of the rear sphere and against a different part of the studio background? Now let's look at them through the left-hand camera. Do you see how the plain sphere seems to be to the right and against a different part of the studio background? Now, we haven't moved these spheres. They are just seeming to move because we are looking at them from different angles. This is not real motion. This is a apparent motion. And again, our friends the Greeks had a wonderful word for this apparent motion. That is parallax, which means exactly that and nothing more, apparent motion. Now, how do we do this from the Earth with a star? Over here, we have a diagram which shows just what happens. We have to have a very long baseline on this triangle of ours because of the tremendous distances involved. So we start in by taking a picture of a star in the spring when the Earth is on this side of its orbit. 6 months later, in the fall, when the Earth is on the other side of its orbit, we take a picture of the same star. Now, in the first picture we took of this star, it seems to be against the background of these stars. In the second picture we took of this star, it has moved, apparently, to a background of these stars. There is your parallax. That star seemed to give a little jump in relation to the background stars. And the smaller that jump, the farther away the star is. Look at this one. Do you see, if we take a picture of this star first from this side of the Earth, it's here, apparently. If we take it again 6 months later, this star, it has only moved to here, and so on with one still farther away. Now, that parallax is measured in angles. And an angle, of course, is a division of a circle. You know what a right angle is. That measures 90 degrees in the circumference of a circle. And each degree of a circle is divided into smaller units of minutes, 60 minutes to a degree, and 60 seconds to a minute. Now, that means that there are well over 1 million seconds in the circumference of any circle, be it big or little. And the angle with which we are involved is on the circumference of an imaginary circle whose center is at this star and whose circumference passes through the two positions of the Earth. These angles are considerably less than 1 second of arc, considerably less than 1/1,000,000th of the circumference of a circle. The very nearest star, that one we were speaking about, whose light takes 4 years and 4 months to reach us, has a displacement, a parallax of 3/4 of 1 second of arc. So you can see how our neighboring stars can be the only ones involved in this kind of mechanical, mathematical measurement. Now, there is another quality of the stars which we can use to make measurements, and that is the star's brightness. Now, the word which astronomy uses for the brightness of a star is its magnitude. And in magnitudes, it's very much like a race. The brightest star is first. the next brightest second, and so on. There are 6 degrees of magnitudes, of course, with 5 intervals between. And they probably came from the old way of speaking of the brightness of stars. A star was very bright, the first magnitude. Bright, the second magnitude. Bright medium, third magnitude. Faint medium, fourth magnitude. Faint, fifth magnitude, and very faint, sixth magnitude. And the original astronomers said that there were 6 degrees of brightness which could be discerned by the naked eye. The 6th magnitude was the faintest star that could be seen without an instrument. There is an interval of about 2.5 steps between each magnitude. In other words, first magnitude is 2.5 times as bright as second, which is 2.5 times as bright as third, and so on. So that one first magnitude star, as you will see if you work it out, is equal to about 100 sixth magnitude stars. Now, what has this got to do with distance? Well, we know exactly how distance is affected, light rather, is affected by distance. Light diminishes by what we call the law of the inverse squares. In other words, if you get twice as far away from a light, that light will not look half as brilliant, but a quarter as brilliant. Here is a little experiment that we have to show you what happens. Inside this box, as you can see, is a light source right here. Now that is movable, you see. We can move it back and forth. And we have calibrated the lid of this box, which we shall have to put down now to shut out the studio light. Now right here, at this first line, is our photoelectric cell. And here is the photometer that measures the light. Now I'll turn the light on. Now see, that measures at this point 16. Now suppose I move this bulb, as you can see by the index here, twice as far away down to this line. What happens? It doesn't drop to 8, not to half of 16, but to 4. Do you see? A quarter of the way. Now suppose we move it twice as far away again, way down to this one. Watch what happens. It shouldn't be 2. It should be 1, and 1 it is. There you see it. That is the law of inverse squares. So, that if we know how bright a star is, we can tell its distance by how bright it looks to us. Now, how do we know how bright the stars are? Well, we can analyze the light of a star, and that will tell us just what elements are in that star and at what temperatures they are burning. So, by laboratory comparisons, we can tell pretty closely just how bright a star really is. Then the difference between how bright it really is and how bright it looks to us will give us a very good measure of its distance. And in order to facilitate this kind of comparison, astronomy has set all the stars at the same distance from the Earth, a distance of 32.6 light years. And the brightness of the stars, as they appear all at that distance, lined up in an imaginary fashion together, is called their absolute magnitude. Now, some of the more distant stars, which look very faint to us, would be brilliant giants at that distance, while our sun, which looks bright only because it is very near to us, would fade back to a kind of obscurity. The sun has an absolute magnitude which falls between 4 and 5. That means that it would just about be seen on a nice, clear, dark night if you had good eyes. There is still another way in which we must measure distance when we get out beyond the stars in our own star family, our local galaxy. Now, there are certain stars whose light is not constant. These are called variable stars. And one particular class of these stars whose light changes from time to time pulsate as they vary. They get big and bright and hot and small and faint and cool. And they do this with extreme regularity. There are many of these stars with different periods of variation, but each star sticks to his own time schedule. And the important thing about it is that we have found that the longer such a variable star takes to change from bright through faint and back to bright again, the brighter that star really is. There is a relation between the length of time the star takes and its real brightness. And we know that real brightness. So that when we see these pulsating stars, and we do see many of them, in the most distant aggregations of stars, in clusters, and in distant galaxies far beyond our own star family in space, we can tell quite accurately the distance to these objects. Now, distance under these terms and at that scale can at best be an approximation. If we have come within 10% of the absolute accuracy, that's fine. If we get within 25%, that is acceptable. Time and distance are both overwhelming. And as one astronomer says, all science is simply an approximation of the truth. All man can do is to strive constantly to get closer and closer to the absolute truth.
This is National Educational Television.
That are untold millions of miles away in space can be identified by their fingerprints, analyzed by man's ingenuity. This is the starting point of what we are going to talk about today. This is the key to the second great era of astronomy. Man has been looking at the stars for thousands of years, and his conceptions of what they were, of their real nature, were colored, of course, largely by his fancy and by his imagination. And it is only within the last few hundred years that man's mechanical and scientific ingenuity has devised ways and means for him to find out their true nature. Now, we know that every incandescent body in space is producing radiation which streams out from that body in all directions. That radiation travels in a wave motion. The waves are all of the same shape. They differ only in length, and they travel at a constant speed. Some of them are short, as you see here. That shortness, of course, is measured horizontally. Some of them were long ones. Their speed and their shape remain unchanged. They travel at about 186,000 miles a second. They are energy waves. Now, the atmosphere of our Earth absorbs or blocks out many of these waves of various lengths. But there are two windows, you might say, in our atmosphere through which waves of different lengths may pass. Here is one small window which admits waves whose length is between 200,000 and 300,000 to the inch. This wavelength gives us what we call light. This is what we can see, these energy waves between 200,000 and 300,000 to the inch. That is light. That is everything that we see. All color, everything visual comes through this little window. Now, the shorter wavelengths look violet to us. the longer wavelengths look red to us. And the intermediate wavelengths produce all the intermediate colors between red and violet. The colors run red, orange, yellow, green, blue, indigo, and violet, and they all come through this very narrow window. The whole band of radiation which these objects in space produce is called the electromagnetic spectrum, and we shall talk a great deal about it as we go on. There is another window where longer waves of radiation of energy come through, and that again we will discuss later on. Now, man had in the beginning only his two eyes to see stars with, and he did unbelievable work with just these natural instruments. Then about 350 years ago, a Dutch telescope maker named Johannes Lippershey, purely by accident, chanced upon the effect which two lenses, one placed behind the other, have upon light which passes through them. This accident of Lippershey's was heard of by a great Italian scientist, Galileo Galilei, who in a matter of hours had built the first telescope. And this is a replica, a model of one of the very earliest telescopes that man ever constructed. This is a model of one of Galileo's telescopes, and Galileo was the first human being ever to look through a telescope at the sky or at anything else. This is a very simple type of telescope. It has a large lens at one end, a lens for admitting the light from an object. It has a small lens at the other ends, a lens for viewing that light and the image that is formed by it as it comes through the telescope. Now, this type of telescope is called a refractor, and here is a diagram which shows how the refractor works. Here is the object whose light we are observing. That light comes to us and is admitted to the telescope by a large lens at the outer end of the telescope. That lens bends the light. Now, the scientific word for bending is refracting, and that is why this telescope is called a refractor. It bends the light and brings all the different wavelengths of that light, red, orange, yellow, green, blue, indigo, and violet, remember, to a single point, the focus, where the image is formed of what the telescope is pointed at. Then that image is examined and magnified by a smaller lens placed behind it. And here is the eye of the observer looking through the small lens, the eyepiece, at the image formed inside of the telescope tube. After Galileo's great discovery, man tried to work with lenses. Now, the large lens in the outer end of a refracting telescope has only one function. It is to gather light, to admit light to the telescope. And here is the first type of lens that was used. This is a double convex lens. And you can see its outline there, but here is a cross-section of such a lens, showing its shape, the two outward curves. Now, this lens was not very satisfactory. In larger sizes, it produced beautiful but disturbing lines of colors all around the objects that were viewed. Colors very much such as we get when light is passed through a prism. So man's worked with these things and finally developed a combination of lenses. This double convex lens that we saw, and then a double concave lens. It's difficult to see its shape as I hold it here, but look on your screen. That is a double concave lens, and the combination of these two plus several improvements, finally made a lens which was fairly free from these rather annoying and unscientific color outlines. Now, a lens must be made of the finest quality of glass, without bubbles, without flaws, without anything to disturb the passage of the light through it. And because light has to pass through such a lens, it can be supported only around its perimeter, around its edges. So that gives an automatic limit to the size which such lenses and consequently telescopes using such lenses may be made. The size limit is 40 inches, 1 yard and 4 inches. And the biggest telescope of this kind which has ever been built and which ever will be built is the telescope, the great refractor in the Yerkes Observatory in Williams Bay, Wisconsin. This has an objective lens, a lens for admitting light, 40 inches in diameter in its upper end. Its tube is about 60 feet, and of course the viewing and observing apparatus are in the lower end of the telescope. Now, while man was struggling with the problem of these little lenses, another method of gathering light and observing it was discovered. This time with the combination of one of the greatest geniuses the world has ever known, Isaac Newton, and an English scientist, James Gregory. They thought that light could be gathered and focused just as well by means of a mirror. And Newton built the first telescope using a mirror as its main component. That is a reflecting telescope. And here is a diagram showing the basic principles of such a telescope. In this case, a mirror is built and placed at the bottom of the telescope, at this end of it. Now, this mirror is the all-important factor, and the whole secret is the curve into which the upper surface of the mirror is ground. This must be a parabolic curve. Newton's mirror was spherical and didn't work. We've learned since that a spherical mirror has its limitations. A parabolic mirror, which is simply a spherical mirror slightly deepened at the center, is what does the trick. That admits the light through the tube of the telescope, reflects it to a focus high up in the telescope, right back along the path at which it enters. In most reflectors, that cone of reflection is intercepted by a flat mirror set at an angle of 45 degrees, which reflects the cone of light out through a hole in the side of the telescope tube where the eyepiece is put and where this image can then be observed. In the larger reflecting telescopes, other systems are also made available, some of them involving the drilling of a hole through this big mirror, and other auxiliary mirrors set up in there to give different optical arrangements for various different purposes. Now, of course, man immediately put his ingenuity to work on this type of telescope. And the culmination of years of experiment, of trial and error, of building these telescopes has resulted in the biggest telescope in all the world. Now, here we can see the figure of an average man, say a 6 feet tall man. And towering above this figure and on the same size scale is this model of the greatest telescope that man has ever built, the great Hale 200-inch reflector at Mount Palomar. This is really a magnificent scientific instrument, one of the greatest scientific instruments this man has ever built. It has a mirror working on the same basic principle that Newton discovered. This mirror is 200 inches in diameter. Now, that is 16 feet 8 inches, an enormous thing. The mirror itself weighs 14.5 tons. It is made of Pyrex, a very common household material, and Pyrex was selected for the same reason that Pyrex can be used for cooking, because it is not too much affected by changes of temperature. The expansion and contraction of such a mirror must be rigidly controlled because its surface must be perfect to about 1/millionth of an inch. The tube which supports this mirror at the bottom and which holds up here the chamber in which the observer works. Incidentally, this is one of the two telescopes which are big enough so that the observer rides in the telescope while he works, is 55 feet long, this lattice-work tube. This is the telescope itself. It is supported by a great metal mounting, and the mounting weighs and the telescope weigh 530 tons, over 1 million pounds. Now, the chief function of a telescope, of course, is that it may be pointed at any part of the sky. And in astronomical work, the telescope must be kept pointed at any individual star for hours at a time sometimes. How can you do that with 530 tons of machinery? Well, that's a problem of engineering and design. And it was solved in this telescope to such an extent that the great Hale telescope at Mount Palomar can be swung through its arc against the motion of the Earth so that it can keep a single star or other object always in view as that star seems to move across the sky. It only takes a motor as big as the motor that runs your sewing machine at home, 1/12 of a horsepower. Now, here is a photograph of that great telescope. Here you can see the mirror, the lattice-work tube, and the vast, ponderous mounting, which nevertheless is so beautifully designed that very little effort is required to move it. Now, not every man can have a 200-inch reflector in his possession. This is a 6-inch telescope. That is to say, the mirror at the base of this is 6 inches in diameter. Now, here is a mirror which is smaller, which is 4 inches in diameter. It's a parabolic mirror. The parabola, of course, is so delicate you can't possibly see the curve. But that is the basic unit of this telescope, a 6-inch mirror. The light from that mirror, because of the shape of its surface, is reflected back up the tube of the telescope till it comes to a focus up here. But before it reaches that focal point, it is picked up again by a flat mirror set at an angle and sent out through this aperture where the eyepiece is put so that it can be observed. This is a finding telescope, a sort of an aiming device to enable the astronomer to pick up more easily these faint, distant objects in the sky. Now, what have we got? We have man looking at them with these 2 telescopes, the only 2 he had. Then telescopes came into being and pushed back his horizon of space. And then in 1850, something else happened. The first photograph was taken through a telescope. From that time on, the bigger telescopes are used for photography. No one looks through them. This telescope and others comparable in scope are now cameras. And most modern astronomy is done from photographs. You see, the eye can never see more than it sees when it first looks through a telescope. But a photographic plate, the longer it is left exposed to the light from these objects, the more detail it builds up upon it. And man's memory, well, it can't last anything like as long as a photograph can last. There you've got it. You've got the picture. You can see it. And let me show you here. Here is a photograph of a star. In fact, 4 photographs of the same star taken through an astronomical telescope. In this first picture, this is just about what the eye would see, an exposure of just a second or 2, and it shows a very faint star, so faint that we have to outline it with lines to identify it. Another picture with a slightly longer exposure. This star seems a great deal brighter, but look what has happened to the background. Here are more stars which were invisible in the first picture because their light has had a chance to build up on the plate. A longer exposure, perhaps half an hour, shows our original star, the same one, terribly bright, and a great many more stars appearing in the background. They were there all the time, but their light had to have a chance to build itself up. And here is one of some hours. The main star is overexposed out of all recognition, but the background stars, they were there. They're there all the time. No one had ever seen them before, but here they come on this picture, discovered for the first time. So we can see that the camera is one of the most valuable instruments that astronomers can use. But there is another instrument, perhaps equal or in some cases even more valuable than the camera. And this instrument is built around the qualities that a prism has and the way a prism will affect light that passes through it. This effect, again, was first seen and discovered by that incredible genius, Isaac Newton. Here is a diagram of what happens to light when it passes through a prism. Here is the prism. Here is a little beam of light going through it. The other side, not the beam of light, but a beautiful band of colors. This is the spectrum. And that word comes from the same root word as our word specter, a ghost. This is the ghost of this little beam of light after it has passed through the prism. All the colors are here, all the colors of the rainbow. In fact, the rainbow is a series of little light passing through the little prisms of raindrops. Red, orange, yellow, green, blue, indigo, and violet. The red light waves are the long ones, the violet are the short, remember. And that this principle has been adopted to an instrument called a spectroscope, which admits light through one tube, where the light passes through a prism. Here you can see the prism, the central, the heart of this instrument, and it is viewed through a small telescope here. A similar instrument to this attached to astronomical telescopes opened a whole new field, a world of wonders in the stars. Let us have a look now at the great electromagnetic spectrum that we spoke about very early in the program. Here it is spread out for us to see. This is the energy spectrum, all the waves of all the lengths occupy this. Now this very narrow little segment here is visible light. This is what we see. This is light. Let's expand that a little bit. And here we have the band, enlarged, you see. Red, orange, yellow, green, blue, indigo, and violet. These waves running from 200,000 to the inch, 200,000 to the inch to 300,000 to the inch. The long waves are red, the short ones are the violet. And to the short side of the violet, we have ultraviolet, a word which I'm sure you're familiar with, shorter than violet, shorter waves, you see. Then the X-rays, very short waves, which have the power of penetrating materials which are not transparent. Then these mysterious cosmic rays that come to us out of space and whose nature we do not yet fully understand. At the other side, at the long end, we have the infrared, below the red, longer than the red. That's heat. We can feel those waves. We can't see them. Then we have the waves a little bit longer that we use in radar and in television, and still longer waves in broadcasting, and longer ones for sound. There is the whole story. Now, as man began to study these spectra, he began to find out strange things about them. The light that was produced gave him different pictures according to what was producing the light. Here is a diagram showing several varieties of these spectra, these ghosts. Here is one that comes from an incandescent solid, a solid band of colors merging beautifully into one another without distinct borders, just blending, do you see? Now, man found that if he heated a certain substance to incandescence and then passed the light from that incandescent object through a spectroscope, he didn't get this broad band, but he got a definite set of bright lines. This, for example, is light from sodium. And light from sodium always occurs in the same place in front of the same yellow color at any time. So that when these particular lines are seen, anybody who knows the spectrum will say that's sodium, and the material can be identified. Now, in stars, there are dark lines that cross the spectra of stars. And these dark lines fall in the same places, the same locations, in the same colors, and the same distance from the ends and all the rest of it, as the bright lines that are produced in the laboratory. What does that mean? It means that stars which have an envelope of cool gases around their hot centers where this incandescence is born are absorbing energy in that same wavelength, that their atoms are vibrating in the same way, and picking it up and reversing these bright lines, making the bright lines dark, but that dark line identifies the same elements. Therefore, we know by the positions of these dark lines, as we see them in the spectra of stars, just what materials are in those stars. And various other indications, their width and their position and so on, will tell us what the temperatures are, how much radiation is exciting these lines. And given a temperature, we have a star's brightness. Given a star's real brightness, we know its distance. You see how valuable this information begins to become, that we get through these little faint lines, this ghost of light. Now, we've set up an experiment over here in the studio. We have several incandescent materials, several materials rather, which we have made incandescent, and we're going to try to show you the lines they produce. Here are four materials. This is mercury, this is helium, or hydrogen rather, this is neon, and this is helium. The light is being passed through a little slit, through a lens which smooths it out, through the prism and to this screen. These first lines you see come from glowing mercury vapor, which produce two bright lines in the yellow and green regions of the spectrum. You can see the short wave and long wave. The short wave is the V for violet and the long for R. Now we'll change to a hydrogen gas. And see, this should give us a line, very faint line, near the red end of the spectrum. There it is. You can see it right under the R. Do you see it there? That's made by hydrogen gas. Now we have neon, that common vapor which is used in so many advertising signs. That will produce a series of rather broad lines just off the R, beginning to get into the orange field. And finally, we have helium, that rather inert gas which is found in the sun. That produces a line, too, you see, in the orange and yellow sections of the spectrum. Now, these lines, which were found in the stars, the different arrangement of lines in the stars, gave man a basis for a classification of stars by their spectral lines, a spectral classification. And he seized upon it immediately. At first, there were a great many different classes of stars, and they were lettered and numbered according to the alphabet, from A to Z. But it was found that there was a great deal of duplication there, and this was finally boiled down to 10 different classifications: O, B, A, F, G, K, M, R, N, and W. Now, if you want to remember those, there's a very good way of doing it, a little sentence, which astronomers use when they're studying their science. O, B, A, fine girl, kiss me right now, wow. So if you pick that up, if you want, it may come in handy sometime. These dark lines can also tell us a number of other things about the stars. In addition to their temperature, we have noticed that we know that stars move, and these lines tell us how they move. If a star is moving away from us, its motion spreads out and lengthens. The wave, remember the wavelengths, it lengthens it. And the whole system of lines in the spectrum of that star would be shifted toward the red end of the spectrum. You may have heard of the red shift. Well, this is what it is. Conversely, if the star is coming toward us, it is compressing, squeezing those waves. They become shorter, same shape, same speed, but shorter. And the system of lines is shifted toward the blue end of the spectrum. Now, this is very valuable because it tells us which way a star is moving, and by the amount of that shift in one direction or the other, we can tell the speed at which that star is moving down to 1/4 of a mile a second. This effect was first discovered and analyzed by a German scientist named Christian Doppler, and is known, therefore, as the Doppler effect. You've probably had an experience with the Doppler effect. If you've ever listened to it, listen. Do you hear how that train whistle that you just heard and saw, do you hear how it dropped in pitch? That's the Doppler effect, the same thing, sound waves, you see. The motion of that train away from you lengthened out the sound waves and lowered their pitch. So it is with light. They lengthen the light waves and shift them toward the red. This is the famous red shift, and gives us the speed of recession, the speed at which objects are moving away from us in space. So with many other things, we have learned through a study of the spectra of stars. Now, this other window that we spoke about earlier, this is the window that is open to wavelengths considerably longer than those we can see. And these wavelengths we can study and analyze by the very newest branch of astronomy, radio astronomy. These waves can be picked up by what we call radio telescopes, which are really very complicated and tremendous radio receivers. Here is one of them, a great bowl-shaped affair, and you can see it there. Now, these are usually arranged so that they can be pointed at any part of the sky. And one of the biggest of these, the very largest one that's so far been built, is built in England at the Jodrell Bank. Here it is, look at it. And you can see, if you watch it closely, that it's moving slightly. Well, these can be moved. This is 250 feet in diameter. Now, the information that we are getting from the short waves of energy received through these tremendous radio telescopes is changing the whole picture out there for us, giving us new outlines to the stars, to the great families of stars, to the galaxies, bringing us news of things which are hidden from us behind clouds of dust, because that dust stops the short waves that we can see, but lets these long ones come through, the ones we can hear. And we have even heard messages from one of our own sun's family in space, Jupiter, the biggest planet in the solar system, and one which has a temperature of 150 below zero. You'd think it couldn't radiate, has. And that sound that Jupiter made, invisible waves, but audible waves, has been heard. Listen. Listen to Jupiter now. You'll hear a rough grating background noise. That's the overall radiation. But Jupiter should produce occasionally a high, clear, bell-like note. That's Jupiter speaking to you from 500 million miles. Now, let's back for a minute over what we've talked about today. Man has looked at the stars with his eyes, done wonders, learned an amazing number of things about them just through watching and thinking about them. Then came the telescope, and man's horizon, his sky horizon, was pushed back. Untold millions of miles, more things that he never dreamed of, were made visible up there. Then he could take pictures of them and record these wonders for future study, pictures that would last forever and which could be duplicated. We've got astronomy in our photographic cabinets. Then the spectroscope. There we unlock the secrets. We know as much about the star as though we had it in our two hands at a library table, putting thermometers in it, analyzing it, tearing it apart, finding out what it's made of. And now the last window that we have opened is radio astronomy. The whole universe is taking on a new dimension, a new shape. We are hearing more, learning more. We can't say we are seeing, but we are finding out more about it. And who knows what great boundaries will be discovered in this last development.
This is National Educational Television.
Looking at the stars for thousands of years. Long ago, he saw that the stars formed patterns in the skies, patterns that he named out of his primitive imagination. Man has been looking at the skies for thousands and thousands of years. And in all his experience, in all the time he's lived upon the earth and watched these skies, I'm sure there has never been another spectacle so awe-inspiring, so filled with true grandeur. The patterns of the stars, those patterns that we call constellations, and that word simply means a grouping of stars, are made up, of course, of the various positions of the stars within them, and of their stars' varying brightness. Professional astronomers must all have started as amateurs who were never able to shake off the fascination of these skies and who kept on with that work throughout all their professional lives. In addition to the beauty that there is in the sky, there is also a large measure of utility there, for man has used the stars to guide him when he has traveled across the trackless wastes of deserts and oceans in navigation. And in recent years, we have been able to use the stars as vast laboratories, giving us conditions of temperature, for example, that we could never duplicate in any laboratory here on Earth. Thousands of years ago, man considered that the stars were tiny points of light fastened to the inside of a tremendous hollow sphere, and the Earth was in the middle of this sphere. Now, we know that isn't true. But in astronomy, we still use the convention of the celestial sphere, for that is what we call the sky as we see it over our heads. It's something like this. Here's a celestial sphere, you see, with the Earth inside it, turning and making the infinite variety of the skies as it does turn. We know that isn't true. We know that the stars in any given constellation are definitely not on the same plane, that is, not all at the same distance from us. The constellations are infinite in depth. And in most cases, the stars in any constellation which are bright to us are those which are near to us. And the fainter stars are the more distant ones, as in this picture, which is one taken through one of the great telescopes. Here are 4 pictures of the same part of the sky. And in this one, with the longest exposure, we can see this apparently tremendous bright star with a background of much dimmer stars. Actually, this star is bright principally because it's near to us. And there are probably many stars in that background which are really much brighter and much hotter than this one, but which are made faint by distance alone. We are going to try today in this program to give you an opportunity to look at the stars with some understanding of the constellations, how to find them. We're going to try to teach you something about using a star chart, for example, and perhaps a little bit about using a telescope. Now, it was, 2,000 years ago, I guess, more or less, that man first began to formalize the constellations, to give them names, and to roughly define their boundaries. The names of the constellations, incidentally, have been drawn from the vivid imaginations of very primitive people. I'm sure that all of us can recall the names of some of the more prominent and brighter constellations, such as the Greater Bear, for example. Now, we don't know whether the stars in this constellation were so named because they happened to look like a bear to these people, or whether they were named in memory of a bear which held a prominent place in the mythology of the people, or whether the name came down as a mistranslation of an earlier language and was adopted by these people. Actually, the constellations are areas in the sky, places. You might better consider them as states in a sort of a United States of the sky. They are used for locating objects which lie within the boundaries of the constellation, just as the states locate cities and towns within them, a city in New Jersey or Connecticut or Kansas or wherever. Most of the constellations are far too big to be photographed on any one photographic plate, so that to see what a constellation looks like, we have to turn to charts, and there are charts of all kinds, as we shall see in a little while. Actually, the easiest way, the most simple way, for you to find out about the stars and begin to get acquainted with a friend who knows his way around among them. In this program, I am going to be your friend. We shall go out together and look at the stars. But first, let's recall that the same stars are not visible in the sky at every night in the year. Now, here is why. Here we have made a representation of the sky, of the celestial sphere, or the celestial half-sphere, of course, which is what we can see from the Earth on any night. We not only have this much of stars, but all out here, too, is stars. It goes completely around us, over our head, from horizon to horizon. Now, where we are on the Earth, we can see, here is the sun lighting up this side of the Earth. So, although there are stars here, beyond the sun, the overwhelming brilliance of the sun quenches out those stars. We just can't see them. However, if we get into the great cone of shadow of the Earth, which we call night, then we can see the stars. Now, as the Earth moves around the sun through the year, we can see that these stars are apparently going to move in the opposite direction, from east to west, because the Earth's motion is from west to east, and the stars will seem to slide by us here, slide by the Earth in this way, rising a little bit earlier, setting a little bit later every night, until finally the whole pattern will change. And as we go through the year, in the summertime, we shall find the stars that we were able to see in the night sky in the winter are now hidden beyond the sun, and we can't see them. And those stars which in the winter were behind the sun in the daytime are now on the dark side of the Earth, away from the sun, and are visible to us. This is the ever-changing pattern of the skies. Now, as we go out to look at the sky, we shall pick a night in late summer. It's a little bit more comfortable before it gets too cold. We shall also select a time when there isn't any moon, for the moon's light quenches the light of all but the very brightest of the stars. We try to find a place where there are not too many trees and houses to obscure our horizon, and we try to get at least 50 miles from any big city, so that the haze of city light and the dust that cities always throw up into the skies will not bother us. In order to begin our exploration of the skies, in fact, begin exploration of anything, you've got to have a starting point, a reference point. And we will try to find one which will always be available, no matter what time of the year or what night you go out. For our purposes, that starting point will be the North Star, the star called Polaris. Now, We're going to go out, but we've got to, where is north? Which way shall we look? Well, if your astronomical friend doesn't happen to know the north, it's easy for you to find if you want to try it alone. Take a compass. You don't have to be deadly accurate. Just give yourself a general idea of where north is. Now, let us go out then and take a look at the north and see what we can see. As we go out, and we shall face north for the moment, although that is astronomically unconventional, as we shall see, we shall face north. And high up to our left, or to the west, we will see 4 fairly bright stars that mark the corners of an irregular rectangle of stars. From the lower right-hand star, 3 more stars go down, forming a curved line in the sky. This group of 7 stars make up the very familiar figure of the Big Dipper. It is a part of the constellation of Ursa Major, the Greater Bear. The names of all the constellations are given in Latin, because Latin is the nearest thing that we have to a universal language. Astronomers come from all countries and speak all languages, but most of them have a smattering of Latin, enough to talk about the constellations anyway. These 7 stars make up then the figure that we call the Big Dipper. 4 stars make its bowl, 3 stars its handle. Now let's consider these 2 stars, the stars that form the side of the bowl of the Dipper farthest from the handle. They seem to lay out a line in the sky to mark a direction. Let us follow that direction, and we shall go to our right about 5 times as far as the distance between these stars. And as we do, the first bright star we will come to, almost on that line, is the star we are looking for. This is our reference point. This is Polaris, the North Star. These 2 stars in the bowl of the Dipper have pointed the way to Polaris, and for that reason they are called the pointers. Polaris is the brightest star in the constellation of Ursa Minor, the smaller bear, and it is also the end star in the handle of the Little Dipper. Now here's where we're going to meet our first astronomical disillusionment. The stars that make up the Little Dipper are, many of them, very faint, and it is only under the most unusual circumstances that we are able to see the whole figure of the Little Dipper. Ordinarily, we can see Polaris, and we can see the 2 stars that form the front of the bowl of the Little Dipper. The Little Dipper, you see, is made up of 7 stars, 4 stars making the bowl of the Little Dipper, and 3 stars making its handle. These 2 stars, which are bright enough to be seen ordinarily, are called the guardians of the pole. Now, Ursa Minor is not a very big constellation, and its importance lies almost entirely in its location and in the fact that it does contain the North Star, Polaris, the prime navigational star. And Polaris, as we shall see in a few minutes, will always be there, and we can always use it as a starting point for our exploration. Now let's see how we can use it. Let us go back again to the Big Dipper, to these same 2 pointers, the stars that form the front of the Dipper's bowl. We'll follow that line, come to Polaris, the focal point of our exploration, and keep on going past it, just about as far to our right, or to the east in this case, as the Dipper is to the west. And we shall run into another group of stars which make roughly a rather crooked M-shaped figure in the sky. This is the constellation of Cassiopeia. At this time of the year, it does look something like a rough M. If we wait some months until the motion of the Earth around the sun has brought Cassiopeia around in the sky until it is where the Dipper is now, that M will look more like a W. And after all, a W is simply an M upside down anyway. Now, we have been looking to the north. And, of course, most of our sky is to the south. We shall turn our backs now on Polaris and look to the south. And as we do that, we shall find that the Big Dipper is then high over our right shoulder, and Cassiopeia high over our left shoulder. And the southern part of the sky lies before us there. Now we're going to back to the Dipper again and use this time the handle of the Dipper as our guide to our next star. That handle, you see, these three stars strike a curve in the sky. They form a part of the circumference of a circle. Now we'll continue on that curve past the last star in the handle, keep right on going, and on that same line, quite far to the south, we will run into a very bright, definitely red star. This is Arcturus, one of the most important stars in the sky. Arcturus is actually the fourth brightest star of all the stars that we can see from the Earth. And it is the second brightest star that we can see from our position in the northern part of the Earth. Arcturus is the brightest star in the constellation of Boötes, the herdsman. Now, don't look for a man in this group of stars. Look for a kite such as might be flown by any small boy. And Arcturus will be at the place in this kite where the tail is usually fastened. Above Arcturus, the fainter stars draw your eye up to the much wider angled point at the top of the constellation of Arcturus. Now, we're not through yet. We can keep right on going. Follow the same curve, you see, down through Arcturus and down very close to the southern horizon, quite far to your west or to our right now that we are looking southward. We'll see another very bright and much whiter star than Arcturus. This is Spica. Spica is the brightest star in the rambling and rather faint constellation of Virgo, the maiden, whose fainter stars outline a roughly rectangular figure that lies east and west, almost on our southern horizon at this time of the year. Now, there is a little memory-jogging phrase which will help you to remember how to find these two new stars whose acquaintance we have just made. Remember the curve of the handle of the Big Dipper. It strikes out a portion of the circumference of a circle, the arc of a circle. All right, follow the arc to Arcturus and speed to Spica. And there you have it. Now, this is just a tiny sampling of the stars which can be seen at one time on one night of one season of the year. I hope it will give us a means of getting further acquainted. Remember that every clear night, all through the year, there are wonders to be seen up there, even without a telescope, just the stars and those constellations. Actually, there are 88 constellations which fill the entire celestial sphere without any vacancies whatever. Remember, too, this reference point of ours, Polaris. I told you that it would always be there, always be faithful and on the job and never move. And here again is the reason for that. Now notice that our Earth here, its pole is pointing in a given direction. And as the Earth turns and goes around the sun through the year, notice that the direction in which the pole of the Earth points does not change. Polaris is located in the sky almost directly above the North Pole of the Earth. As the motion of the Earth through the day makes the Earth spin upon its axis, moving the stars across the sky apparently from east to west during the night, the permanence of that pole keeps it pointing at Polaris, and Polaris does not move. Polaris you will find in the same place all night, every night, all through the year. You can use it very definitely as a starting place. Now, I told you that there were charts to enable you to find your way around the sky. There are a great many of them. Some of them are small and relatively simple and inexpensive, and most of them are good. Here is a typical star chart. The opening cut here will give you a sight of the sky as you see it on any given night at one time. Now, as time goes on, by turning the chart, you can see the stars wheeling across the chart as they wheel across the sky from left to right, from east to west. Now remember this, too, and you'll find one peculiarity about star charts. They are oriented differently from Earth maps or charts. When you are looking at a map of the Earth, you are on the outside looking in. North is at the top of the map, the east is at your right, and west is to your left. When you are looking at a chart of the sky, you are on the inside of this celestial sphere of ours looking out. North is still at the top. but east is at your left and west at your right, and the stars move across your sky from left to right, from east to west. Now, you will learn as you go along that the best way to use a star chart is to go out and hold it over your head and then look up and see what you see. Perhaps shine a flashlight on the chart. It may work, but if you do use a flashlight, it will take you about 10 minutes before your eyes get accustomed to the dark again and you can really see the stars. And if you do very much holding of the chart over your head, you'll learn why astronomy can become a pain in the neck. Now, there are elaborate star charts, much more elaborate ones. Here is one here. Quite a good one and quite a big one, and it has the same features. I'm just going to arrange it so that what the sky we just looked at a few minutes ago is up before us. And here it is. Here, for example, is Polaris, the North Star, right in the center, the focal point about which the whole sky seems to turn because the Earth turns about Polaris. Over here are the 4 stars that make the bowl of our Dipper, and here are the pointer stars. Here is the handle of the Dipper. Follow the arc to Arcturus and speed to Spica. You see that same curve goes right on around. Follow the pointers to Polaris, keep right on going, and here is our crooked M of Cassiopeia. And in this opening, as in the smaller chart, are the stars which we can see from horizon to horizon at any one time and any one night. And as the Earth turns, turn the chart. Follow the stars across the sky. Meet the new ones rising in the east as the hours go by, and say farewell to the old ones setting in the west as time marches on. Now, we have drawn upon maps, upon globes of the Earth and on maps of the Earth, imaginary lines to help us to measure distances upon the Earth and to find our way about on it. On this little globe here, we see some of those principal lines. The most important one, perhaps, on the Earth is the equator, which goes right around the Earth, halfway between the North Pole and the South Pole. Parallel to the equator, there are other lines, and a few of them are shown here. These lines are parallel to the equator, are called latitude lines, and measure distance north of the equator to the North Pole and south of the equator to the South Pole. Crisscrossing these lines, there are other lines, a set of lines which converge at the poles of the Earth, and which are widest apart at the Earth's equator. These are the longitude lines and help us to measure distance east and west. Now, on the Earth, an arbitrary starting point has been chosen for the measurement of longitude, and that, of course, is on one of these lines which passes through Greenwich, England. We have done very much the same thing in the sky, on charts of the sky. We have drawn lines up there, imaginary lines, of course, which correspond roughly, and in most cases, to the lines that we find on the Earth. We have the celestial equator, the equator of the sky, which goes right around the sky and lies midway between the celestial poles, which lie over the poles of the Earth. Parallel to the celestial equator, we have drawn lines which correspond to the latitude lines, but we don't call them latitude. In astronomy, these are called declination lines, and measure distance in north declination from the equator to the North Pole, the celestial equator, to the celestial pole, and south declination from the celestial equator to the South Pole. Crisscrossing these lines again, we have drawn other imaginary lines in the sky, which converge at the poles of the sky and are widest apart at the equator of the sky. These lines correspond to earthly longitude, but are not called longitude lines. They are called our lines of right ascension and measure distance east or west in the sky. And as in the case with the Earth, we have chosen an arbitrary starting point, a 0 point in the sky, to begin this east and west measurement. That point is the place where the sun seems to stand on the first day of spring, right over the equator, on the 0 line. Now, these lines are given on our charts here. You can see on this chart, where man has drawn by convention the lines of right ascension, which measure distance east and west. Here are some of the more prominent ones, and a finer division of this same system can be found around the edge of the chart. Here is the equator, the celestial equator, And here is the point where these two cross. And you can see indicated on this chart other lines of declination, measuring distance from the equator to the celestial pole and in both directions. Now, just as every city in the country can be located by its position where two of these lines, latitude or longitude, meet, so can every object in the sky be located from its position where two of these lines of right ascension or declination meet. And you can find them by consulting there. They're given on all charts, in all star catalogs. Now, what have we got so far? We have gone out and we have taken a look at the sky on a given night in autumn and had a very, very small glimpse of it. We have studied a chart. We have learned of the general motion of the stars and something of what they look like. Now, up to now, we have only used the equipment that nature gave us, just our two eyes. With a telescope, even a very small telescope, the wonders that you can see in the sky are magnified thousands of times. There are telescopes of all varieties, and frankly, the smallest telescope, which will give you any real satisfaction in looking at the sky, is one whose primary lens or mirror is at least 3 inches in diameter. This is a very popular type of telescope for the amateur. It has a mirror 6 inches in diameter, and it will give you a wonderful view of the sky. Most of the larger telescopes of this kind have apparatus upon them which will enable you to find objects by means of their coordinates which you cannot see without a telescope. But there is another way of doing that, a way which will give you perhaps an even better working knowledge of the sky and the things you can see there. You use the chart. Now, you look at the chart and you will find the faint object you want to see fairly close, as a rule, to a bright star which you can easily see without a telescope. And go in and study the chart. And incidentally, that's the best way to do it, even if you're not looking through a telescope. Don't stand there with a chart over your head. Go in and look at it. Memorize a little bit of it and then come out again. Find your bright star. Find out where it is. Come out to your telescope. Now, there are a number of things you should know about your own individual telescope. How much of the sky can you see with the various eyepieces? What is your field of view? Your telescope should also have a finder, a small auxiliary telescope with a wide field of view, which will give you a picture of the same part of the sky with a much greater extent than your telescope. Find the bright star, remember, that is near to the faint object you want to see. Go out and point your telescope at that bright star. It won't be hard. It'll be right there. Then move the telescope in the direction and at the angle from you that that faint object is. Move it slowly, and you'll be looking through it at the same time. Don't miss that object, and don't miss the parade of wonders that will go across the field of view. If you're lucky, you may hit it. If not, sweep back and forth, raising the telescope a little bit between each sweep, so. And in a very few minutes, your object should slide into the field of view. Amateurs can perform very valuable service to professional astronomers, particularly in the field of the observation of variable stars. They can also observe comets, and many an amateur has gained fame through the discovery of a comet. The observation of meteors and meteor showers and of the aurora are all of great value to the professional and can be done by the amateur. In any event, there is the sky. Go out and look at it. The stars are there for you. And in all your life, you will never see a sight as awe-inspiring and as wonderful as the stars.
This is National Educational Television.
This is an atom at work. Inside the star's incredibly complicated atomic-wide energy to send radiation through thousands of light years to our eyes. A star is a self-luminous body in space. It creates, by some complicated processes within the star, its own light and heat, that energy which we receive from. Contrast this self-made light with the reflected light that we get from the sun, from the moon rather, and the other planets, not from the sun, because the sun is a star. In fact, the sun is the only star whose surface we can see, because the sun is the only star that is near enough to us. All the other stars, no matter how big and how bright they may be, and we shall meet some strange ones later on, are so far away that all we can get from them is a single point of light which has just one dimension, distance, the distance that the light travels in getting to the star from us. Now, stars come in a tremendous variety. There are enormous stars. There are tiny stars. There are hot stars, and there are cool stars. And there are stars of almost every conceivable color. They are of such infinite variety that the task of cataloging them and classifying them would seem to be almost impossible. And yet it has been done, and done very well too, by two astronomers, Einar Hertzsprung and Henry Norris Russell. Now, they have made a diagram in which they are able to show every kind of star there is. And this diagram, of course, is called the Hertzsprung-Russell diagram. They set up this form by making a vertical scale which had to do with the star's brightness. Now, this vertical scale runs from brighter to fainter, down through the scale of the star's brightness, which are called magnitudes. Now, in order to simplify the comparison of the brightness of a star, the comparison of magnitudes, astronomy has theoretically placed all the stars at the same distance from us, a distance of 32.6 light years. And the star's brightness at that distance, it's called its absolute magnitude. And it is the absolute magnitude scale that Hertzsprung and Russell used, from the very brightest of the stars down to those which are extremely faint at the bottom of the scale. The horizontal scale, which Hertzsprung and Russell used, was based upon the spectral classifications of the stars, and which also means that it was based upon the star's color and the temperature. For here at the left, the stars are the hottest stars, blue stars, and they range from that point down the scale of temperature and color through all the variations of color until we get the fairly cool red star at the other end of the scale. Now, Hertzsprung and Russell spotted their stars. Wherever the characteristics of a star, for example, in magnitude corresponded to a point on this scale, they moved in which the star fell as far as its spectral classification and temperature were concerned, and there they put a dot. Now, let's take this sample star of ours, the sun, and see how it works. The sun, we know, has an absolute magnitude of 4.5, a little fainter than fourth magnitude. Now let's follow that line out until we come to the sun's spectral classification, which is the G, the fairly cool star. Surface temperature, incidentally, these are surface temperatures of 10,000 degrees Fahrenheit, not centigrade, Fahrenheit. So, put a dot where that temperature corresponds with that brightness, and there is the location of the sun in the Hertzsprung-Russell diagram. Now, as Hertzsprung and Russell placed these stars on their diagram, they found that the vast majority of the stars fell in this rather wide belt that curves across the diagram from upper left to lower right. So, since that did contain the majority of the stars, they called this the main sequence. And the stars that fall in this belt are called main sequence stars, and our sun is a main sequence star. Now, the main sequence stars, of course, range in size considerably. There are stars here which are 100 times as big as the sun, and stars which are 1/10 of the diameter of the sun. So we have this range of stars from about 100 million miles, or 10 million miles, 10 times that, 10 million miles to about 100,000 miles in the main sequence. And these stars vary, of course, in brightness according to their temperature and their size. Now, normally, a star is easiest to see when it is hottest. As an example, let's take a piece of metal, ordinary metal, anything will do, and put it in a dark room. It's cold. In a dark room, you can't see it. But if you heat that metal till it begins to glow, then you can see it, even though the room is dark. And the hotter that metal gets, the brighter it will be. It will go from red up through orange and yellow to white, and of course, by that time it would have melted, but nevertheless, the hotter it is, the brighter it is. So it is with the stars. The hotter the star is, the brighter it is if the size is the same. Now remember this too, that each square unit of surface of a star is giving out energy. Now, the more square units of surface there are, in other words, the bigger the star is, the more energy it gives out, the more light it produces. So if we have a hot, big star, it is going to be very much brighter than a small star of the same temperature. That is what happens. And this is the main sequence, from the hot blue giant stars down to the red dwarf stars. You might call these normal stars. Now, there are other kinds of stars. There are many offshoots to this. Remember what we have said about the unit of surface giving off energy. Now, we know that there are stars whose spectral analysis tells us that they are cool. They're not very hot. And yet they are bright. Now, what does that mean? Stop and think a minute. That means that there must be a great many units of surface working to produce the star's light. They're big stars. They are the giants. They are not in the main sequence. They are off the beaten track. They are bright, but they are cool. They must be big. Now, technically, a giant star is a star whose diameter runs from 10 times the diameter of the sun to 100 times the diameter of the sun. The sun's big. The sun's diameter is 864,000 miles, say 1,000,000 miles in round figures. All right, here's a star whose diameters start at 10 million miles and run up to 100 million miles. Think what that must mean. These are big. This is enormous. But wait, there are other stars, even cooler, intensely. These must be enormous, tremendous surface area. Here they are, these supergiants, whose diameters are more than 100 times the diameter of the sun. Now, we have a very good example of such a star, and we have a diagram which will show us such a star in relation to some other units which we know about. We have a picture here of a very famous supergiant star. This is the great red star Betelgeuse, the star in the upper left-hand corner of the rather irregular quadrangle of the constellation of Orion. Here is Betelgeuse. Now, what have we got inside of it? Well, a good part of the solar system. Here's the sun. Here is the orbit of Mercury, the nearest planet to the sun. Here is Venus. Here is the Earth. And here is Mars. Now, we know that the Mars is at an average distance from the sun of 141 million miles. And the diameter of Betelgeuse is very nearly 500 times the diameter of the sun, 500 million miles. That's big. That's enormous. And yet there are bigger stars. There is one star, we believe it to be the biggest star we know about, which is in the constellation of Hercules. Its diameter has been estimated at 6,000 times the diameter of the sun. That's 6 billion miles. Now, the diameter of our whole solar system is only about 7 billion miles at best. Here is a star which would almost fill the whole solar system if the sun were placed at the center of that star. And we've got one other very interesting star here. This is one we can't even see. It is so cool. It doesn't give off enough radiation to reach our eye. And the only way we know of its presence and of its size is because it has a very bright companion star going around it in an orbit. It takes this star 27 years to complete its path around the big star. And at times, it passes behind the big star. Now, the gases that make up this enormous star are so tenuous that they're almost transparent. And we can see this smaller star, which is quite bright, passing behind the big one. We know how long it takes, and we know just exactly how big that star is. We can get an accurate measurement here. This is 3,000 times the diameter of the sun, 3 billion miles in diameter. Those are the big fellows. They're tremendous things. They are tremendously distended, too. The masses of stars, that is the amount of material they contain. Incidentally, mass is what weight is on the Earth. Your weight is the pull of the Earth upon the mass of your body. So the masses of stars don't vary very much. There are few, if any, stars which have a mass which is more than 100 times the mass of the sun. Now imagine a star with 100 times the mass of the sun, but 1,000 times the diameter of the sun. What's happened to that material? It's distended, it's blown way up. This is a bubble, this is nothing. Here is a red-hot vacuum. And only by contrast with the utter emptiness of space around it can we see such a star at all. These are the supergiants, tremendous, unbelievable stars, and yet there they are. You can't get away from the evidence. Now, on the other end of the scale, there are extremely hot stars, but faint. Now, what does that mean? Think of that again. Faint stars, but hot, should be bright, but there are very few square units of space working. These are tiny fellows, little bits of things, and they are in the hot category spectrally, but in the faint category by magnitudes, and they are down here, and these are the white dwarf stars. And if you thought the big ones were unbelievable, think of these. Remember, the mass of a star does not vary too much. Here we have a star which must have the mass of the sun the size of the Earth. Squeeze the sun down until you get it to the size of the Earth. It still weighs the same. Its mass is the same. How terribly condensed it must be. The first of these stars to be discovered had such a density that a cubic inch of it, a little bit of a cube, an inch on a side, weighed a ton. And the champion of these stars, of this class of stars, is one which has a density 36 million times the density of water. It would weigh 36 million times as much as the same amount of water. It weighs 620 tons per cubic inch. Now, how can this happen? Well, in order to find out about that, we've got to go back to the basic unit of matter, the atom. The atom which once was believed to be indivisible. We know better now. We know that the atom has an extremely complicated structure which is divided into two regions. Here is the nucleus, the center of the atom, made up of particles called protons and neutrons mainly, with a few other particles between. The outer regions of the atom are made up of electrons. Now, all the mass, all the weight, if you will, of the atom is in the nucleus. There is none in these electrons. And the atom, the electrons move about the atom in orbits, very much as planets move about the sun, but these orbits go in every direction, whereas the planets of the solar system move in practically one plane. Now, it doesn't take very much energy to detract, to tear off an electron from the rest of the atom. The energy in the center of the stars is ample for that. For in the interiors of stars, we have temperatures which run into the millions of degrees. That's plenty to do this. Now, most of the atoms inside the stars have lost most of their electrons. In the white dwarf stars, they've lost all of them. Now, normally, two atoms cannot get closer together than the limits of the orbits of their electrons, like this. You see how much empty space there is there. With the electrons gone, the nuclei of the atoms can get close together. You've lost volume, you've lost space, but you haven't lost weight. That is these terribly dense, heavy stars, these white dwarfs. Now, the Hertzsprung-Russell diagram again. The position of the stars on it and the way they are placed gives us a hint as to the possible evolution of a star. Certainly, the human race hasn't been here long enough to see a star go through its birth processes, its coming of age, its maturity, and its death. But we think we can see young stars and middle-aged stars and old stars. And while we can't see dead stars, they may be there. And we believe we can reconstruct the processes of evolution from this evidence. Now, we also find that all of the stars, all of which can be placed on the Hertzsprung-Russell diagram, can also be divided into two enormous overall classifications, which we call population 1 stars and population 2 stars. Population 2 stars are generally the hot blue or white stars and are found in the upper section of the main sequence. Population 2 stars are found everywhere else. The red stars, the cool stars, the white dwarfs, and all the rest of them. And there is a reason, a definite reason, for the difference between these two stellar populations. Population 1 stars are found in the regions of the great star organizations in which they lie in a certain specific place. Now, we know that these great organizations of stars, these galaxies, we live in one of them, the great Milky Way system is a galaxy, are not only made up of stars, but there is a great deal of dust and gas in the space between the stars. This dust and gas is not evenly distributed over these galaxies. It lies mainly in the outer regions of the galaxy and in a central plane. Let's look at a picture of such a galaxy for a minute. This is a typical galaxy seen edge on, and we can see this dark line cutting across the galaxy. There are stars there too, but there is also a great deal of dust and gas making this line. Now, in the central part of the galaxy, in what we call the nucleus, it's bright. There are no dark obscuring matter there, and there are stars without much dust and gas. Here's another view of a galaxy. This one we are seeing in plane, flat, you see, almost. And here is the nucleus, bright, stars. You can begin to see a little bit of darkening there, but out here in the disk where the arms are, there is lots of dust and gas scattered in among the stars. And here is where the population 1 stars are found. Now, these population 1 stars have a normal growth. They start small and red, and they go up through all the colors and get hot and blue, a very even and fairly prosperous existence, because they are in the region in which their vital fuel is found, and this fuel is hydrogen, the most abundant element in the universe and the simplest of all atoms. The hydrogen atom has one proton in its nucleus and one electron orbiting about that proton, and a proton is the nucleus of the hydrogen atom. Now, where these stars travel, in the regions of dust and gas, there is an abundance of material, and these stars move through that dust, sweeping it up, replenishing their vital forces. Great celestial filling stations we have here. These are the population 2 stars, the stars that live a normal, straightforward growth. Population 1 stars don't have as easy a time of it. They start out in the normal way. And when about 15% of their own hydrogen is used up, they're stuck. There is no dust and gas where they are. They can't replenish their supplies. They have to live on their own fat, as it were, eating up their own hydrogen. This is fine until about 15% of it is gone. Then the process speeds up, and the star begins to change. It swells, it grows in an effort to maintain its energy and its heat. And it gets big and red and cool. And then when about 60% of it is gone, comes the critical time in the star's existence. It may collapse suddenly. And in collapsing, a tremendous heat is generated. And the star sometimes explodes and blows itself to pieces. Sometimes that collapse continues, and the star winds up as one of these terribly dense white dwarf stars. Now, I spoke a little while ago of our sun as a sample star. We are pretty well aware of the processes that are going on in the sun, a series of complicated thermonuclear reactions. And we have worked up a little graphic sketch here to show in a measure what happens there. Now, there are in this reaction involved, first of all, one normal carbon atom and 4 protons, the nuclei of hydrogen atoms. Here we have the normal carbon atom. It is struck with terrific force, force enough to bang that proton into the center of the atom by a proton, the nucleus of a hydrogen atom. That affects a terrific transformation in this carbon atom, changes it into a variety of nitrogen. Not the common variety that we know that is in our air, but an unstable variety, which has a lifetime of the minutest fraction of a second, and that changes of itself into a variety of carbon again. A different variety, but a stable variety of carbon. And this fellow is struck again by the second of the 4 hydrogen protons involved in this process. This affects another transformation, changes our carbon atom into another variety of nitrogen. This time it's a stable variety. It remains as it is until it is struck by the third of these protons and is changed then into a variety of oxygen, which is an unstable variety of oxygen. So it changes of its own accord in a minute fraction of a second into another type of nitrogen. And along comes the 4th proton, which smashes into this last pure abused nitrogen atom, and what have we got left? We've got the original carbon atom that started the whole thing and went along for the ride and is ready to start it over again. We have a new element, helium. And what has happened to the rest of it? It's being carried away. The mass has been lost. You see, here goes the ghost, we might say, of these 4 protons. Now, in the sun, this is going on all the time. When I speak of 4 hydrogen atoms, you can multiply that by anything you like, because here is what happens. Every second, in the interior of the sun, the temperature between 30 and 50 million degrees, 564 million tons of hydrogen are transformed by this process into 560 million tons of hydrogen. Now, that's a loss of 4 million tons of the sun's mass. That mass is converted into energy. And up till a short while ago, we didn't realize that mass and energy were interchangeable. And the formula for this interchange was given to us by one of the greatest scientific minds that ever lived, Albert Einstein. His formula is E equals mc squared, as you see here. Now, the E is the energy, the production of this transformation. The M is that loss of mass, that 4 million tons a second, those 4 little hydrogen protons. C is the symbol for the speed of light, the speed of energy. We square that C, and we multiply that tremendous figure of the square of the speed of light. Light travels 186,000 miles a second by the loss of mass, and we get the resulting energy. This is that terrific energy produced by the sun and in the same measure by all of the stars. Now, there you have the 2 general populations. We've got the main sequence, the normal star. We've got several strange offshoots, but there are still other strange stars to come, too. There are stars whose light is not constant, variable stars, because their light does vary. And these stars vary through some interior convulsion of their own that we do not understand. And there are types of variable stars which change with extreme regularity. They are small and faint. They swell and get bright and cool, and they shrink small and faint again. And they pulsate up there like great hearts in the sky. Some of them do this with extreme regularity. And these regularly pulsating variable stars have given us an invaluable means of measuring the distance in space. For there is a direct relationship between the length of time it takes these regular stars to go through their cycle of pulsations and of light changes and their absolute magnitude, that intrinsic brightness of a star. And if we know the absolute magnitude, we know the light we see, the distance is the result. And these intrinsic regular variables are yardsticks of distance. There are irregular variable stars which remain faint for a long, long time and then suddenly blossom into brightness for a little while and go back to faintness again. There are stars whose cycle is the opposite, which remain bright for a long time and drop for a short while and are bright again. There are irregular variable stars, all kinds of variable stars, and they are still a puzzle. We are still working to find out what they are. Then there are stars which have reached this critical stage in their development. Remember when 60% of their hydrogen was gone and almost anything could happen? Such stars have sometimes met with a celestial catastrophe. They have exploded. Now, in the days long gone by, such a star, of course, at its normal brilliance, was not visible without a telescope. When they did explode, rising sometimes to hundreds of thousands of times their normal temperatures, the star became bright. You remember, hot stars, bright stars became much brighter. And people saw them then in that stage for the first time and called them new stars. Now, we know they weren't new stars. They were old stars, been there all along, but which had met with this terrific celestial catastrophe. Now, that's still going on. There are about 20-odd such stars which happen every year. And they are recorded on astronomical cameras and so on. Very few of them are bright enough even for us to see. I mean, we still use the ancient term for such stars. Here is a working photograph of such a sequence. This is the kind of a picture an astronomer uses. He doesn't deal in the positive pictures. Astronomy works from the negatives. This is a nova. For nova is the Latin word for new, and they're still called new stars even though we know they're not. Now, here is a picture taken of this star way back 75 years ago. This is the way it's been. It's a normal, apparently peaceful star. Then on the 3rd of June, 1918, something began to happen. Here's a picture of the same star taken that night. On the 7th of June, 4 days later, the same star had increased in brightness about 1,000 times, probably in temperature. On the 8th of June, it really let go. This must be 100,000 times as bright as it was then. These are the novae, strange stars. We don't know what's happened to them. They've exploded. There have been 3 cases in the history of mankind when a nova has become so bright that it casts a shadow at night. And these are the supernovae. We have one about every 500 years. We're overdue for another one right now. Now, let's sum up a little bit. What have we found out about the stars, this tremendous variety of stars? Here is a chart which gives us a kind of a run-through of what we've talked about today. Sizes, all sizes, from supergiants, unbelievably big, to the white dwarfs, unbelievably small. In colors, from red, orange, blue, white. Then again, the red dwarfs and the white dwarfs. White, really white. And temperatures, big ones, cool, giants, warm. Main sequence from hot to warm. Red dwarfs, fairly cool. White dwarfs, hot but faint because they are so small. The 2 populations, the hot blue stars in population 1, the well-fed stars, all the others in the starving population 2. That is just a fraction that we know about the stars. If we all that we know, they'd still be 99% mystery.
This is National Educational Television.
Hidden among the stars are some of the strangest and most magnificent objects in nature, objects known to us in detail only during the last 100 years. We live in a house of stars that we call a galaxy. Our efforts to judge the appearance and size of this galaxy of ours have been rather severely handicapped by the fact that we are always inside of it. We can't get out of it. It's just as though we were eternally locked up in a small room inside of a house, a normal dwelling place, and asked to describe the appearance of that house. We can't do it, but we can look out of the windows of our little room, just as we can look out of our galaxy and see other houses around us and see other galaxies in space around us. And because of a rather general resemblance of these galaxies, most of them at least, to each other, we feel that we're pretty safe in assuming that our galaxy looks like the rest of it. From that and from other bits of knowledge, we find that our galaxy is a great disk of stars and dust and gas, shaped very much like a vast wheel. It is big. The diameter of our galaxy is at least 100,000 light years from side to side. Now, a light year is not a measure of time. It's a measure of distance. It is the distance that light travels in a year at the rate of 186,000 miles every second, so that you can see that this galaxy of ours is big. We also think that it is rather flat, disc-shaped, with a thickening in the center, a thickening which may extend perhaps as much as 10 or 15,000 light years. In this galaxy, there are stars and dust and gas. The star population we estimate to be at least 200 billion stars, and our sun is just one of these stars. Now, from our position in this galaxy, a position which we shall discuss a little bit later on, we can see on any one night from any one place on the Earth about 4,000 of these more than 200 billion stars. And we also can see through telescopes other things than stars up there. Clouds, bright glowing clouds of gas, clouds of strange dark material, and of course the stars. And all of these things belong to our galaxy. They are in this great house of stars in which we live. Now, the stars themselves, we find, have a frequent tendency to congregate, to get together. In fact, if we were to take as a sampling of these stars the 20 brightest stars that we can see from the Earth, and each one of these stars looks to us from our eyes only as a single point of light, we find that out of these 20 stars, 7 are actually double stars. There are 2 stars up there contributing to the light that we see. And an 8th is a more complicated system, a system of 3 stars. Now, 8 out of 20 is about 40%. And we believe that this percentage of duplication holds pretty true in the region of the galaxy that we can see. About 40% of the stars are doubles or better, which puts our sun, you see, on the side of a very small majority in being a single star. In other regions of the galaxy, which we cannot see and do not know as well, the percentage may be even greater. Now, as typical of some of these duplicated stars, let's take as first a simple double star. There is a beautiful double star in the constellation of Cygnus, the Swan, a summer constellation. This star is Albireo, and it is one of the loveliest things we can see in a small telescope. It doesn't take very much of a telescope to show this as a double star. One of the 2 stars up there is a brilliant, deep, rich royal blue, and the other is pure gold. It's a wonderful sight to see. A little more complicated system of stars is found in a constellation not too far from Cygnus, again in the small summer constellation of Lyra. One of the stars up there is, to our eye, a single star. If we put a small telescope on it, that single star breaks down into 2 rather widely separated stars. And then if we increase the power of this telescope, each of these 2 in turn breaks down into 2 more stars. So we have 4 stars, all in the same system, moving about each other. This is the famous double-double in Lyra. Its astronomical designation is Epsilon Lyrae. In the winter constellation of Gemini, one of the 2 very bright stars which give that constellation its name, Gemini means the twins, is a very complicated structure indeed. Now, we see this star, Castor, as a single point of light. A telescope, no matter how powerful, will only bring us 3 stars. But the spectroscope, with its betraying system of dark lines, tells us that 2 of the 3 stars we can see with a telescope are in themselves double. And this is a diagram of the Castor system. We have the central star going around a tiny orbit, probably impelled by the gravitational influences of the other stars around it. The second star is double, and its 2 components are going around each other, and the whole business is circling around the central star. So with the 3rd member of the system, two components going around each other, and the whole business circling around the center. This is the very complicated Castor system. Now, these three, the simple double, the double-double, and the more complicated Castor system, are typical of the hundreds of thousands of double stars that we know exist in our galaxy. And the stars congregate even more thickly, for we have what we call clusters. Now, there are galactic clusters. They're called galactic clusters because they belong to our galaxy, and all the stars in them partake of the general motion of all the stars in the galaxy. This vast wheel is turning, you see. And the first type of galactic cluster is the open cluster, or the coarse cluster. They're called that because the stars in them seem to be fairly widely separated. Now, one of the best known of these open clusters is in the constellation of Taurus, a winter constellation. And here you can see it. Now, the little grouping of stars high up in the right-hand corner of your screen is the famous cluster of the Pleiades. Now, the Pleiades we can see quite easily as 6 fairly bright stars. Actually, a small telescope will show you about 60 stars. But a photograph such as you see here indicates that there are about 300 stars that belong to this cluster. The Pleiades is about 350 light years away from it, and the stars that compose it are all big, bright, hot blue stars. Now, in the same cluster, in the same constellation, rather, of Taurus, there is another cluster, even more open, the Hyades, which looked in the picture you saw a minute ago like that letter V lying on its side. The Hyades doesn't have as many stars in as does the Pleiades, but it looks bigger and more widely separated to us because the stars are nearer, about half as far away as the Pleiades. And again, in the late fall and winter sky, we find another cluster, which seems to give us an indication that even the clusters themselves cluster. This is the famous double cluster in the constellation of Perseus. 2 clusters of stars, so close together that they can be brought into view at one time in the field of a small telescope. These coarse clusters are typical of 300-odd that we know of in our region of space. Now, all the stars in a single cluster seem to have a common motion in space. They're all moving together in the same direction. They are the same kind of star. An analysis of their light tells us that. And they probably had a common origin. Now, in addition to these coarse clusters, to these open clusters, there is another type of star grouping which is even stranger and more fascinating, and that is the globular cluster. These look like tremendous, closely packed spheres of stars. We know of about 90-odd of these, which are within our view. And like the coarse clusters, a great many more of them are probably hidden from us by the dust and gas and countless other stars which are in the Milky Way. This particular cluster that we are looking at now is in the constellation of Hercules. Again, a great, rather dim grouping of summer stars. And you'll find it in this picture in that line of stars which seems to slant from near the center of the picture up toward the upper right-hand corner. These clusters, those that we know of, range in distance from us from about 18,000 light years for the very nearest to about 10 times that distance for the most distant ones. The great cluster in Hercules is about 35,000 light years away. It has a diameter of about 30 light years. And of course, it looks almost impossible to count the number of stars in it. Estimates of the stellar population of this cluster range from about 50,000 stars up to about 100,000. And these are all tremendously big red and yellow stars. They have to be big and bright to cast their light to us from this tremendous distance. And our sun, if it were up where the Hercules cluster is, would never even register its presence on a photographic plate. It isn't that much of a star. Now, these globular clusters and their distribution have played a large part in our estimate of the shape and size of this star house of ours, the galaxy in which we live. Dr. Harlow Shapley, a number of years ago, made a very careful survey and an examination of these clusters, the 90-odd that we could see. And he found that more than half of them seemed to be concentrated in one region of the sky, in our summer southern skies near the constellations of Sagittarius and Scorpius, which we believed held the hub of our galaxy, of this wheel of stars in which we live. Now, that concentration there indicated that something was off-center, either the galaxy or that we were. And it is far easier for us to be off-center than for the galaxy. So Shapley figured that our position was not anywhere near the center of the galaxy where it had been supposed to be for a number of years, but near one edge of it, about a third of the way in from the one edge toward the center in one of the arm structures of our galaxy. And that these globular clusters were placed around the edge, either top or bottom or sides of our galaxy, so that we could see them there, standing somewhat like great sentinels. Now, this has been confirmed to a large extent by our ability in recent years to photograph stars in other galaxies outside of our own and other great houses of stars. Some of the nearer and brighter ones we are able to resolve into stars. Here is the edge, for example, of one of the biggest and brightest of these galaxies. This is the great galaxy in Andromeda. And we can see in this picture the globular clusters spaced around the edge of this wheel of stars, which confirms Dr. Shapley's theory and which really confirms our conception of the size and shape of our galaxy. You can see there the importance of this evidence that we are getting from the stars. Now, those we can see from our galaxy, from our position in it, rather, inside of it, we can look out, of course, the sides of it and see relatively few stars. If we look toward the center of it or toward the edge of it, we see a tremendous condensation of the stars. That makes that lane of light that we see in our summer and winter skies and call the Milky Way, because that is our view of the edge of this galaxy from our position inside of it, as though we were looking up along one of the spokes of the wheel. Now, here is a picture of a small portion of the southern Milky Way, and we can see how the stars concentrate as we move from the top toward the center and from the bottom toward the center, and here is the Milky Way. Here is the light from those billions of stars concentrated in this region of the sky. To show you a better example of this star concentration, let's take a look now at one of the great star clouds in the constellation of Sagittarius, toward which we believe the hub of our galaxy lies. Look at this picture. Here are stars, just stars, so closely packed apparently, so lined up as we see them that there is hardly room for another one there. Just millions upon millions of stars lying in that direction in space. These are the stars, their clustering, their concentration, their various distributions. Now, up among the stars, there are other things. We spoke of them before. The first explorers of the sky, with their fairly crude telescopes, saw up there, in addition to the stars, little faint, wispy patches of light. Looked like little bits of fog, and they called them little fogs. The word for that is nebula, and these are the nebulae. There are thousands of these clouds of bright gas up there. Bright because they are excited into brilliance by the radiation of stars which are in the clouds or which lie fairly close to them. This light that we see when we look at a bright nebula is partly reflected light from dust and other things up there, and it is partly light which is absorbed by the gases of the cloud and re-emitted. They're excited, you see, and they give out this light. Now, there is one bright nebula which we can see as a rather vague star without a telescope, one of the very few that are visible to us. And this nebula is in the great winter constellation of Orion. Here is an outline of the stars in Orion. You can recognize the famous belt of three stars that crosses it from the upper right to the lower left. And from the left-hand star of the belt hangs another little arrangement of stars, which is spoken of as Orion's sword. Well, the center object in the Orion sword, which looks like, as I said, a vague star to us, is not a star at all. It is the great nebula in Orion, a magnificent cloud of gases, a very tenuous cloud. It's big. It measures about 6 light years in diameter. Through a very small telescope, it looks something like the flame, a green blowtorch flame. And it is only in a long-period photograph like this one that we can see the tremendous and wonderful detail in that cloud. This is about 600 light years away from it. And it is one of the finest of the bright nebulae that we know. There are others, of course. Here is one that is in the constellation, again, of Sagittarius, where so many stellar wonders are concentrated. This is the Trifid Nebula, called because it seems to have 3 distinct divisions. And in our summer skies, we can, again, in the great constellation of Cygnus the Swan, we find another very interesting cloud. This one is another bright nebula excited into brilliance by a great star in Cygnus, which lies fairly close to it. And I wonder if you can see anything vaguely familiar about the shape of this bright cloud. This is the North America Nebula. And with a little imagination, you can probably picture this as Florida with the Gulf, with the Caribbean Sea and Mexico and Central America. This is a very interesting example of the tricks that the clouds of dust and gas in space can play upon us. Now, there is another group of bright nebulae which almost fall into a class by themselves because they have a similarity of shape which is not possessed by those that we have just been talking about. These are called the planetary nebulae. They were christened again by William Herschel, who first began to study them, and they are called planetary not because they have anything to do with planets, but because they look like little planets when they're seen through a telescope. They show a disk. They are mostly circular in cross-section. And here is a typical planetary nebula. This is the Dumbbell Nebula in the constellation of Ursa Major, the Great Bear. It is a spherical cloud of gas, and it is about the same diameter as our whole solar system, about 7 billion light years. And like so many of these planetary nebulae, it has a very hot, bright star at its center. Now, we don't know why these things occur this way. It may be that the gases have been emitted from the star over a period of years by unusual activity. The star may be absorbing them. The star's radiation is certainly making them visible. But there are a number of planetary nebulae very similar in shape to this one. They all seem to have that central star. Now, another one of them, up in our summer skies again, in that same constellation of Lyra, for example, where we saw the famous double-double, is the Ring Nebula in Lyra. Here we have that same cloud, circular in cross-section, the same hot, bright star at the center. But this one looks like a luminous donut. Now, actually, it isn't. What we're looking at is a semi-transparent sphere, a globe, if you will, of gases. And it looks more dense to us around the edges because here we are looking through a great deal more gas than when we look directly down through the center. Now, there are a couple more of these planetaries which are most unusual and famous in their own rights. One of them is found in the constellation of Taurus again, and this is the Crab Nebula. It was first seen by a famous Irish astronomer, Lord Rosse, who called upon his imagination somewhat vividly, I think, to christen it the Crab Nebula. But this is a strange affair. It is a cloud of dust and gas and debris. Now, one theory as to the origin of many of these planetary nebulae is that they are the ruins, if you will, of a star which blew itself up. Now, in the old days, such things did happen occasionally. There suddenly appeared in the sky a very bright star where there was evidently no star seen before. And because they were new to these people, they called them new stars, and we use the Latin word nova for these stars. This cloud may be the result of such a star. It is expanding. In the 100-odd years man has been observing it, its rate of expansion has been very carefully measured and is about 600 miles a second. Now, if we figure back at that same rate of expansion, we can find out just about what time the whole thing started to spread out, and it was about 900 years ago. Now, if such a cloud came from the explosion of a great star, that star should have been bright enough at that time to make some record upon history. The Western astronomical annals don't show any such star, but in the Japanese and Chinese annals, there is a record of a very bright star. They called it a guest star. It appeared suddenly, stayed for a little while, and disappeared again. And that was in the year 1054. And just about in this same place, we can see the Crab Nebula. There is still another very interesting nebula, which is also in that same constellation of Cygnus where we found the North American Nebula. This is in the lower region of Cygnus, and we see this beautiful, delicate, lacy cloud of bright gases made to glow again by the radiation of stars near them. Now, this is just a portion of a much larger region in the sky. And if we look at that larger region, we can see perhaps the result of an accident that happened billions of years ago. Taking the whole field in which this particular nebula lies, we see that there are several clouds of gas whose general outline may be considered to form a great circle. Perhaps this, like the Crab Nebula, is the ruins of a star that blew itself to bits billions of years ago. We don't know, but that seems feasible. Now, in examining the skies, astronomers of some 100 years ago were puzzled by the fact that there were places where there didn't seem to be any stars up there in the sky. William Herschel, again, whose study of the skies was very intense, called these things holes in the sky. Now, we know that isn't possible. There are no places in the sky in which there are no stars. There are stars, they may be more, there may be fewer, but there are always stars. We know now that these places that Herschel called holes in the sky are actually clouds of dust obscuring the light of stars beyond them. Here again is our region of the Milky Way. This is the region which lies about the Southern Cross. Here is the Southern Cross, these 4 stars. And just below that is one of these so-called holes in the sky. This is the coal sack. It was seen hundreds of years ago and is visible and apparent as a dark spot without a telescope. And it is impossible that the stars of the Milky Way should come up so thickly clustered to the edge of it, then stop and resume as it went beyond. There is gas and dust obscuring in this place the light of the stars beyond. Now, let's go back again to our North American nebula for a moment. And here we can see this North American nebula. And just to the right of it in the picture is another nebula called the Pelican Nebula, seeming to be 2 separate and distinct clouds. Actually, we believe that this is one continuous cloud, overlaid, masked by this dust, this dense cosmic dust, which gives it the shape that looks so strange up there in the sky. One of the most famous such clouds of dust that we can find is again in that treasure house of astronomical wonders, the constellation of Orion. This is the Horsehead Nebula, again discovered by Lord Rosse and named by him, and perhaps looking to a vivid imagination, something like the arch, neck, and head of a horse looking out of a stall. But look at this picture. Look at the right side of it and see how bright it is and how many stars there are visible on that side of the picture. Now look at the left side and see how few the stars are. And see the edge of this great cloud cutting across the picture from top to bottom, just about in the middle. We are looking at a vast cloud of cosmic dust. Now this dust is everywhere. We find it scattered through our galaxy. We can find it in other galaxies whose pictures we can take from ours, looking out the windows of this house. Here is one of them edge on, and we can see like a streak around the edge of that galaxy, the dust. Here is another picture of another galaxy, taken this time so that we can see it almost in plane from top to or bottom, depending on your point of view. This definitely shows the arm structure of galaxies. And the dark streakings in there are not open places in the stars, but they are obscuring dust and up there. Now, this is cosmic dust. This is a very important part of our universe. We believe that this dust is the building blocks of the universe, the stuff out of which everything is made. And out of the almost universal presence of such dust has come a very interesting theory of the formation of stars themselves. Now here, of course, are few of these grains of dust, tremendously large. Actually, we believe that these dust grains are microscopic, maybe 200,000 to the inch. But they are out there in space, and they are near stars. And they are receiving the radiation, the energy, the light, and everything else from these stars. So that half of each grain of dust would be lighted by a star near to it. The other half would be dark and would cast a cone of shadow out in the direction away from the star. Now, there are so many of these. They're so thickly crowded, as you saw in some of the pictures we've showed you, that it must be that at times one of these will be right behind the other. Frequently happens. Now, that means that this star is receiving all the radiation. It's being pushed in that direction by that force, the radiant force of the stars, so that this one, for example, would be pushed into this one. The two of them would clump together. Now, that starts something. These two then have a greater mass, more gravitation than the rest, and they begin immediately to draw other grains to them. The clump builds and builds and builds until it becomes tremendous, and gravity pulls the particles together. Pressure inside the thing increases, and with pressure comes an increase in temperature. And when that temperature rises to the millions of degrees necessary to trigger the atomic processes that give light to the stars, we have another star. That is what happens. Now, there is evidence of this clumping which we can see. And we know that in our galaxy and in most of the average galaxies there is a great deal of dust. We believe that 10% at least of the mass of any galaxy is dust and gas. The rest is stars. And in our galaxy, as in probably a typical galaxy, this 10% of dust is not evenly distributed. Most of it lies in the outer regions, in the disk and in the arms of the galaxy. And about 50% of the arm structure of the galaxy is dust and gas. That is where this process may happen, which we believe may be producing new stars. Now, you remember the Trifid Nebula that we saw a little while ago. If we look closely at that, we can find in 2 or 3 places. Here is one. A very small, looks small to us, but remember this is a long way away, a very tiny clumping together of dark. And these dark regions are dust and gas. This may be a star being born. We don't know. Our whole lifetime, in fact, man's whole history, is so infinitesimal compared to the vast expanse of time in astronomy that we shall probably never be able to see a star come into being. But we may be witnessing it here. Now, let's sum up. We've had the stars. We've had their clustering. And we have seen the importance of these clusters of stars to us in determining some of the facts that we believe to be true about our galaxy. We've had these bright but beautiful clouds which are lovely to see. And we have this all-important cosmic dust, the stuff of which everything is made. These are the things which we find in this house of ours, lying inside of our galaxy.
Television.
This is our conception of the house of stars in which we live. If you had spent your entire life locked up inside of one room in a house, you would have only the vaguest idea of what that house looked like from the outside. That is the way we are in our house of stars, which we call the Milky Way Galaxy. In this program, we're going to try to trace man's changing conception of the general dimensions and appearance of his house of stars as the windows in his little room out of which he was able to look became more and more clear. Now, if you look up in the sky in the summer and in the winter, you will see stretching across the sky a rather faint but very beautiful arc of misty light. You have to be at least 50 miles from the extraneous light of any big city, and this, of course, is the Milky Way. Now, we know what this is now, but man didn't always know. And some of the early conceptions, which we're going to try to tell you about, are quite interesting. The ancient Norse people, for example, said that the Milky Way was the road to Valhalla, and the few bright stars that stood out against the general background of this glowing cloud were the souls of the Vikings who had died honorably in battle as they mounted to this Norse heaven. The American Indians had a remarkably similar conception. They said that the Milky Way was the trail to the happy hunting grounds. But it was the more practical Greeks who gave us a rather down-to-earth idea of the Milky Way. They said that in the celestial stables at the top of the sky there was a cow. And one day this cow, as she was being milked, became restive, kicked over the milk bucket, and the milk ran down the sides of the sky. This was then the Milky Way. And the Greek word for it, the Galaxy, is best translated as the Milky Way, and that's what we call it now, the Galaxy. It was a puzzle to man. It was a luminous cloud which did not seem to change its shape under any circumstances, and it wasn't until about 1609 that we got an idea of exactly what it was, but not why. Then Galileo looked at it through one of his very crude telescopes. And crude as this telescope was, it succeeded in resolving this luminous cloud into countless stars, stars which were too far away for them to be seen individually, but whose light reached us from obviously a tremendous distance. There it was. The Milky Way was made up of stars. But why they were concentrated in this rather narrow lane in the skies, we did not know. Then, in the late 18th century, sometime in the 1780s, one of the great astronomers of all time, Sir William Herschel, was engaged in a tremendous survey of the skies. Herschel used a telescope which was large even by our standards, and one which he built himself. And in his survey, of course, he noticed what had been more or less apparent to everyone, that the distribution of the stars in the skies was not constant. Now, as Herschel started his exploration across the heavens, he found there were places where the stars were fairly thinly distributed. Then, as he went on, he came to places where the distribution was much closer, where the stars were literally packed into the space up there. This, of course, was the stream of the Milky Way. And as Herschel crossed it in his celestial journey, he came again to places where the stars were very thinly distributed. Now, in this survey, in this great star count, Herschel came across more than 5,000 little tiny cloud-like objects up there, which were obviously not single stars. Many of these, not many, say a few of these, had been known to mankind through earlier telescopes, and one or two even can be seen without telescopes. They looked like little clouds, and they were given the name Nebula, which means a little cloud. Now, Herschel found a great many of them that were obviously clouds of gas with a few stars scattered in between them, no standard shape, any old shape, but cloudy. Then, as he began to pick up more and more of them through his more powerful telescopes, he ran into more and more which seemed to follow a pattern. Now, this pattern showed that these things they looked in some cases elliptical, in some cases they were circular in cross-section, and in some cases they were spindle-shaped. Now, here is one of the elliptical kinds. And you can see, if you look closely, that there are faint traces of what look like arms on the side of them. There are others whose arms are more definitely shown. We are looking at it perhaps more directly. And there are others, as I said, which have a sort of a spindle appearance, as though we were looking at them edge-on. There were a great many of these, and they all seem to form into this general pattern, seen in various angles. And to differentiate them from the true nebulae, the real clouds, which were obviously clouds, these were called spiral nebulae. And as discovery went on and as telescopes became better, they vastly outnumbered all of the other kinds. Now, there was one of these spiral nebulae in particular which was big and bright and obviously fairly close to the sun. And that we shall come to in a moment. But another result, and perhaps the most important result of Herschel's survey of the stars, was this. He came up with the first definite conception of this vast universe of stars in which we live. Herschel said that this is an irregular disk shaped like a vast wheel with an irregular edge, and that it is made up of millions and millions of stars, that it contains these little clouds of dust and gas, both the real nebulae and the spiral nebulae, and that our sun is a star rather close to the center of this great disk. This was the universe. It embraced everything, everything that man could see or could hope to see, according to Herschel, by whatever means that might come to his command. Now, among these spiral nebulae, which occupied a place in this wheel of stars, there was one which was very prominent. It was particularly bright and evidently fairly large and seemed to be quite near to the sun. And this is in the constellation of Andromeda, and was known as the Great Spiral Nebula in Andromeda. We can see it, of course, now, and it looks to us like an oval, an ellipse, rather. We know that its elliptical appearance comes from the fact that it is tilted away from us, that it is actually circular in cross-section. It seems to follow the pattern of so many of these spiral nebulae. Now, something like this, perhaps. Here is a model of a spiral nebula running true to form. You can see that it is circular in cross-section. But if we see it tilted at an angle, you see, it assumes an elliptical form. And it seems to have the definite arm structure that we can see in so many of these, which, according to Herschel, again, were included in our great overall universe. The Andromeda Spiral Nebula, of course, fascinated mankind because of its appearance, its mystery, and it has been one of the most studied objects in astronomy. The first historical record we have of the Andromeda Nebula is dated 925 A.D., when it appears an account of, rather, of its being seen. It can be seen without a telescope if you know just when and where to look. It's in the account written by Al-Sufi, a Persian astronomer. And from that time on, as man's methods of observation became better and better, the Andromeda Nebula was the one which was always concentrated upon. In 1916, the great telescope, then the biggest telescope of its kind, the 100-inch Hooker telescope at Mount Wilson in California, came into use. And Edwin Hubble, an American astronomer, pursued his studies of the Andromeda Nebula, which had been going on for some time, by means of this instrument. Hubble was able to resolve much of the Andromeda Nebula into stars, and the presence of stars had been suspected in what was generally considered to be a cloud of gas before that. Hubble noticed on many occasions that there would suddenly appear in that nebula a bright star. Now, this was interesting, but not very world-shaking, because such bright stars have appeared in many places in the sky. In fact, in the olden times, a star would suddenly appear where no star had been seen before, and men regarded them as new stars and called them new stars. And we still use the Latin name for new, the word nova, to describe such stars. Although now we know that they are not new stars. They are stars which have been there all the time, but which have been too faint to be seen easily. Then, due to some atomic imbalance, which we do not fully understand, the star explodes. Sometimes blows itself to pieces, more often blows off thousands of miles of its outermost atmosphere, and becomes almost overnight 100,000 times as bright and hot as it was before, and is extremely easy to see. These are the classical novae. They stay bright for a little while and then fade back into insignificance again. In 1885, one occurred in the Andromeda Nebula, which became so bright that man could almost see it without a telescope as an individual star from the Earth. Hubble saw several of these novae in the Andromeda Galaxy, and then something happened. Hubble, in his studies of the nebula, saw that the same star became bright very shortly after it had been bright on a previous occasion. Now, there have been recurring novae, but they do not happen very close together. An interval of 50, 60 years, perhaps, separates those few that we know, which have twice undergone this celestial catastrophe. But Hubble's bright stars were coming back at intervals of a few weeks, and he knew that he had made a most important discovery. Here were variable stars in the nebula in Andromeda, and they were variable stars of a particularly valuable type. Stars that we call Cepheid variable stars, because that the prototype of this star was found in the constellation of Cephus. Now, a Cepheid variable is a giant red or yellow star, and its light varies in a regular cycle from bright through faint and back to bright again in a regular period of time that can be measured down to the fraction of a second. And the one valuable thing about this type of star is this, that the length of time it takes that star to go through its cycle of variation is directly related to the intrinsic brightness of the star, its real brightness. Now, if we know the real brightness of a star, we can, by comparing its real brightness with its brightness as we see it, its visual brightness, get a very excellent idea of that star's distance, for we know exactly how distance affects light, whether it be the light of a star or light of a candle. It affects light by what we call the law of inverse squares. Now, that means if we are twice as far away from an object which produces the light, that light looks only a quarter as bright to us, not a half as bright. So, when Hubble saw these Cepheid variable stars, these giant red and yellow stars in the Andromeda Galaxy, of the type with which he was very familiar, he knew that the Andromeda Galaxy lay at a certain specific distance, a distance which we had never been able to measure before. Now, here's a remarkable thing. In Herschel's early concept of this universe of ours, he said this universe is big, it's tremendous. It must be at least 100,000 light years in diameter. Now, a light year, remember, is not a measure of time, it's a measure of distance. It's the distance that light travels in a year at the rate of 186,000 miles a second. So that this universe of Herschel's was tremendous. But the Cepheid variables in the nebula in Andromeda told Hubble that the nebula in Andromeda was 750,000 light years away. And it must, therefore, be outside of Herschel's conception of the universe. And if that, as a typical spiral nebula, were outside, then all the other spiral nebulae might very well be outside. Here is our universe. Here is what Hubble found out about, that it was not the all-embracing disk of stars that Herschel pictured, that there was space outside of it, space which was populated by other disks of stars, other spiral galaxies. Now, see what's happening. We're getting a better look out of the windows of this room in the house in which we are. We are seeing other houses out there. And since we see other houses, all more or less of a pattern, it's only reasonable to believe that our house must conform to a certain extent to this pattern, too. Now, if the Andromeda Galaxy is at a distance of 750,000 light years, we can then tell a great deal about its size. It covers a certain specific amount of the sky. And at that distance of 750,000 light years, the Andromeda Nebula, and we had better stop calling them nebulae now, they are galaxies as ours is a galaxy. The Andromeda Nebula probably forms one of this class of spiral nebulae or galaxies. Like this, has arm structure. We are seeing it tilted at a considerable angle so that it does look elliptical to us. But the arm structure is there, very definite. And as I said, at Hubble's distance from this, we have a pretty good idea of its size. Hubble said that at that distance, it must measure about 50,000 light years in diameter, say about half the size of our own galaxy, and have correspondingly about half the stellar population, 50 billion stars, as ours had 100 billion stars. And since all the other galaxies were outside, this led to a very interesting conclusion. We know that if we pass the light from any incandescent object, be it a star or a galaxy or anything else, through a spectroscope, an instrument built around a prism, there will be certain dark lines crossing the spectrum, that is, the band of colors that is produced by that instrument. The position and the arrangement of these dark lines tell us a great many things about the object producing the light. And one of the things it tells us is this, that if these dark lines are shifted a little bit toward the red end of the spectrum from their normal position, it means that the object is moving away from us, or that we, the observer, and the object are moving apart. It works the same both ways. Now, here are several diagrams showing spectra of galaxies, and they shift toward the red end of certain definite lines. These are the lines. Now, see where they are in this first picture. They are a little bit toward your right, or toward the red. That means the position of these lines can tell us the velocity of that galaxy. In this case, it is 125 miles a second. And as we go out more and more distant galaxies, we find them moving more and more rapidly. Here is one in which the lines have been moved way up here, almost to the middle of this picture, which indicates a velocity of 14,300 miles a second. We did find that the nearer the galaxies were to us, the slower they were moving. The more distant they were, the faster they were moving. And the most distant galaxies, with which we were able to see and whose light we were able to see and analyze, moved at a speed sufficient to bring them to their positions in about 2 billion years. Now, here was a puzzle. Geologists know very definitely from various evidences that they can pick up on the Earth that the age of our Earth is between 4 and 5 billion years old, and yet the universe seemed to be only 2 billion years old. What happened? Was the Earth out there alone in space waiting for the universe to be built around it? That didn't seem to be conceivable at all. However, that's the way things were for quite a while. Now, as far as the appearance, general shape and size of our own galaxy is concerned, there were several other important clues which gradually came to light. And one of these clues deals with a tremendous formation of stars, the great globular clusters. Now, we know of about 90-odd of these clusters, which are visible from our position here on the Earth. These are tremendous aggregations of stars. They measure about 30 light years in diameter and contain up to 100,000 stars. And they seem to be located on the very outskirts of our galaxy, of this wheel of stars, of our house, the stars in which we live. Now, Dr. Harlow Shapley, formerly of Harvard College Observatory, analyzed the positions and distribution of this group of clusters and said that they undoubtedly stood like sentinels around the edge of our galaxy. And this view of his was confirmed by our being able to see in other nearby galaxies that there were globular clusters situated on the outskirts of such galaxies, and we can see them here in their distribution. From their arrangement, Shapley said that the size of our galaxy was probably correct as we had known it, that it was a wheel of stars, perhaps 100,000 light years in diameter, that it had a definite arm structure, and that it had a stellar population of about 100 billion stars, perhaps more, and of course various real nebulae, clouds of dust and gas within it. Shapley also said that we did not live in the center of this galaxy as Herschel had supposed, but that our position was off-center. When we look at the Milky Way in the summertime, it is extremely bright and very vivid. And Shapley said we are then looking in the direction of the nucleus, the center of this wheel of stars, the hub of it. And Shapley was able to give us a very definite idea. He said, here we have a diameter of the thing, 100,000 light years, this flat disk whose edge we are seeing. Here is the nucleus of it. Now, the nucleus is thick, perhaps 10,000 light years in depth from top to bottom. And from the varied appearance of the Milky Way as we see it, we can get an idea of our location in it. We live about 1/3 of the way in, from one edge toward the center, in one of the arms. When we see this summer Milky Way, we are looking from our position toward the center of that, which we cannot see because of the tremendous number of stars in it. In the wintertime, we are looking out toward the edge of this wheel when the Milky Way is considerably less vivid. However, in the spring and in the fall, the appearance of the stars doesn't vary too much. Their scattering is just about the same, so that we probably live right about the center of the disk of the Milky Way, right in the central planet. This is what Shapley believed, that we were located about a third of the way in from one edge of our Milky Way toward the nucleus, say 30,000 light years from it, and just about in the center from top to bottom of the great system of the Milky Way. That is the way things stood until 1952, when an entirely new conception and new estimate came about. The agency responsible for this change was the great 200-inch Hale reflector at Mount Palomar, the biggest telescope in the world. Walter Body, an astronomer, took up a study of the Andromeda Galaxy with this telescope, hoping, at its distance of 750,000 light years, to be able to see a great deal of detail which hadn't hitherto been disclosed in that galaxy. Body was bitterly disappointed. The Hale telescope did not reveal what he had hoped. And he began to make a study of the clues which Hubble had used to estimate the distance of that. Now remember what Hubble had said. Hubble saw in the Andromeda Galaxy Cepheid variable stars, great red and yellow giant stars, with a regular cycle of variation. And this cycle led Hubble to believe that the distance of the Andromeda Galaxy was 750,000 light years. At that distance, its size, its diameter was 50,000 light years, and on that scale, the universe was perhaps 2 billion years old. Now, Body analyzed these stars and found the answer. These were not the red giant stars that Hubble had believed they were. They were, on the contrary, tremendously bright, hot blue stars, blue-white, at least 4 times as bright, perhaps more, than Hubble had thought they were. Now, that meant that if they were 4 times as bright, they were twice as far away, and that the distance of the Andromeda Galaxy, instead of 750,000 light years, was 2 million light years at least. That its size was about 3 times what we had supposed it to be, because it didn't look any smaller to us just because we knew it was farther away. It must be 150,000 light years in diameter and have a correspondingly larger stellar population, and that the universe on this new scale was about 5 billion years old. Now, you see, the Earth falls right into place. The Earth belongs now and was not out there waiting for everything to happen long before the rest of the universe was built around it. To summarize the evidence we have, we live in a house of stars, and we have been able to see other houses which we believe are very much like ours outside. So, as I said before, we are justified, we think, in assuming that ours fits more or less into the general pattern. This house of stars is our Milky Way Galaxy, a vast disk of stars and dust and gas. This disk measures at least 100,000 light years in diameter. It has a stellar population of between 100 billion and 200 billion stars. It has an amount of dust and gas, and the dust and gas mainly concentrated in the outer regions of it, the arm structure. Our sun is just one of these billions of stars, and we, of course, are attached to our sun gravitationally. We go along with it. Our galaxy has a definite arm structure, and our sun is located, we believe, in one of the arms about 1/3 of the way in from one edge toward the center. The center, again, is the Milky Way, that part of the Milky Way which we see in the summer as we look toward the edge, toward the middle of this wheel, down one of its spokes, as it were, from our position about halfway between the top and bottom of it. In the wintertime, we see the Milky Way looking toward the edge, looking up the spoke, in the constellation of Taurus in the winter sky. The summer Milky Way, the hub of our galaxy, lies, we believe, in the direction of the summer constellation of Sagittarius. Now, this galaxy of ours is rotating. rotating in this direction, so that the arms trail back along the direction of rotation. And of course, like all celestial groups of things, its rotation is not like that of a wheel. It is rotating most rapidly in the center, and the different components are rotating more slowly as we go up. At our sun's distance, about a third of the way in, our sun is traveling at a speed of about 175 miles a second. Yet at that speed, so vast is this galaxy of ours, that it takes about 200 million years for the sun to make one rotation, carrying with it, of course, its little family of planets, which include our Earth. This is our present conception of our house of stars in which we live. And to me, it is a tremendous tribute to man's ingenuity, to his thinking power, that he has gotten from his position as a prisoner inside of one room of this little house, this marvelous view of the great house of stars in which we live, our Milky Way Galaxy.
This is National Educational Television.
For centuries, men believed that a motionless, enormous Earth was the center. Now we know that our tiny Earth spins on an endless journey through a universe vast beyond our comprehension. The greatest of all telescopes has a range which is about 2 billion times the distance that light travels in a year. It puts us into a visual bubble in space which has a diameter of about 4 billion light years. Now, a light year is not a measure of time, it's a measure of distance. It is the distance that light travels in 1 year at the rate of 186,000 miles every second of that year. That is the part of the universe that we can see, that we know. Now, in photographs taken with this tremendous telescope, using the telescope as the eyepiece of a camera, exposed for hours so that we can reach out to the very end of this telescope's range, we can see some very strange things. Here is one of those pictures. Notice in it that there are some objects which are obviously not stars, little wispy ghosts of light right at the edge of this bubble in space that we know of, little spindle-shaped affairs. Do you see them there? Actually, there are about 300 of those strange objects in these pictures. Now, these are not stars. These are galaxies, really vast organizations of stars and dust and gas. And here, for contrast, is a galaxy which is rather near to us and in which we can see in some detail. We can see the complicated structure, the arms, the nucleus, and the arrangement of this galaxy. This one we can see head-on, as it were. Here is another one which is at a different angle. This one is taken edge-on, and it gives us a view of the general construction of these galaxies, a disc-shaped affair of stars and dust and gas. These things are tremendous and are made tiny only by distance. We live in a galaxy. All the stars that we can see belong to our own local Milky Way Galaxy. And in this bubble of space that the telescope brings to us, we can see enough galaxies so that we have a pretty good idea of the average galaxy. Now here is a model of a normal average galaxy. As you can see, it is roughly circular in cross-section. It has a diameter of about 100,000 light years. It has a stellar population of at least 100 billion stars. There is a vast quantity of dust and gas in between the stars, enough dust and gas to make up about 10% of the mass of the entire galaxy. And this dust and gas is concentrated largely in the outer regions of the galaxy, where we see the arm formation, which seems to be normal in the majority of the galaxies. These arms trail backward against the direction of rotation of a galaxy. This one, for example, is rotating in this direction. And in the center is a nucleus, a hub, the brightest part of the galaxy, with rather less of the dust and gas there. We see these at all angles. Some of them we see face on, as it were, from either the top or the bottom, depending upon your point of view. Others are at an angle which makes them look elliptical or oval to us. And still others we see edge on, so that they look as that picture did, which we just saw a little while back. Now, there are a great many of these, and they all seem to have a general family resemblance. And as is the case with mankind, he has a propensity to try to classify things, to put them into little pigeonholes where he's got a lot of them which have a general resemblance together, which fall into classes. And that has been done rather successfully with the galaxies. One of the greatest astronomers, Edwin Hubble, classified galaxies. He put them into 4 general groups. The first one he called the elliptical galaxies, which had little or no arm structure and were in varying degrees of circularity, the most circular down to those which were elliptical either because of the angle at which they were tilted from us or elliptical in fact, were elliptical in shape. In Hubble's second group, we have the normal armed spiral galaxies. And again, they were classified according to the preponderance of arm structure. In his third group, there were galaxies which seemed to have a bar rather than a circular or an oval nucleus. And the arms came out from the edge of the bar. The fourth class, which isn't shown here, was really not a class at all. Into it was thrown every galaxy which didn't conform. There are a few, a rather small group, which have no standard of shape. Now, Hubble classified these again, in each group according to their shape. In the ellipticals, the more nearly circular ones were this first group. Then the other classes were more oval or more elliptical. In the arm spirals, the classification was according to arms. Those with the least prominent arm structure were in his first classification. And as the arm structure became more prominent, they were put in a different class. So were the barred spirals. Those with the least arm structure were in the first class, and an increasing amount of arm structure put them into a subsequent higher group. Now here are some wonderful pictures of these various galaxies, close enough to us so that we can see perhaps the various kinds. Here is one, for example, which has a preponderance of arm structure with a very small nucleus, and the arms are scattered and irregular. Here is one of the classics of astronomical photography. It shows a normal armed spiral face on, as it were. We can see the arms, the rotation of them. This one is moving around this way, clockwise, as you look at it on your screen. It, too, has a very condensed nucleus and a rather widespread arm structure. Here is a picture of one taken edge on. If it has arm structure, it isn't apparent to us because the arms lie in our line of sight. But we can see the disk formation with the rather deeper nucleus and the concentrated brightness in there where the stars are. This fourth picture is not a galaxy. This is a nebula, and we put it in here by contrast. The galaxies were called spiral nebulae when they were first discovered. This is a real nebula, an amorphous cloud of gas within our own galaxy, part of our own household, as it were. This is the great nebula in Orion. Now, we live in a galaxy, and the galaxy we live in, we believe, is a normal spiral galaxy, not barred, a spiral galaxy with two definite arms, and it is a little bit larger than the average. Now, this average galaxy, we believe, looks very much like ours, except that ours is slightly bigger, has perhaps a slightly larger than average stellar population. There is one very bright galaxy quite near to us, bright enough, in fact, so that we can see it without a telescope under favorable conditions, and that is the great galaxy in Andromeda. We believe that our galaxy resembles this one very closely in form, in shape, but is only about 2/3 of the size of the Andromeda Galaxy. Here is a picture of the Andromeda Galaxy. It is actually circular in cross-section. Its shape, as we see it, is due to the fact that it's tilted away from us. It has a definite arm structure, two great arm portions. It has a very condensed, bright nucleus. It is perhaps 150,000 light years in diameter and has a population of somewhere between 200 billion and 300 billion stars. This, as I said, is one that we believe looks very much like ours, although it is larger than our galaxy. Now, the Andromeda Galaxy and all the other spiral galaxies lie outside of our galaxy in what is called intergalactic space, in space between the galaxies. Now, here's a diagram which shows, let us say, our own galaxy, looking something like this, a normal armed galaxy. Our position in that galaxy is about 1/3 of the way in from one edge toward the center, where our sun is one of the billions of stars, and a rather small star at that. And of course, about our sun are clustered its family of planets, on one of which we live. Now, contrast this picture with the picture man originally had of the universe, where an enormous Earth was the center of everything. Now, man, through his own ingenuity, has lessened his important position a little bit and finds that he belongs on an appendage of a rather average star in a slightly larger than average galaxy in a terrific bubble of space inhabited by countless billions of other galaxies. Now, our galaxy belongs to what we call the local group. That is a group of galaxies within a fairly small space range, relatively small, rather. Here's a diagram of our local group showing our galaxy and, among others, its two nearest neighbors, the Magellanic Clouds. Now, these clouds are fairly bright, and you can see them easily if you're far enough south on the Earth. They lie in the southern sky and were first reported to civilization by the crew of that ship of Magellan's, which made the historic first voyage around the Earth more than 400 years ago. Here's a photograph of the larger of the two clouds, the large Magellanic Clouds. Now, this is an irregular galaxy. You see, it doesn't take on any elliptical or spiral form. It's an irregular galaxy, an irregular little cloud of stars. This is about 200,000 light years away. Now, just stop and think of that a minute. If this thing had been destroyed in some overwhelming celestial catastrophe 100,000 years ago, we'd still be seeing it. We'd still be looking at the light which left it before then. We wouldn't know of this destruction for another 100,000 years. This one, as I say, and its little companion are the two members of the local group of galaxies to which our own galaxy, our own Milky Way Galaxy, belongs. Here it is. Here is our galaxy, and here are the two Magellanic Clouds. Now, so situated that we can see them in the southern skies are 3 or 4 more small elliptical galaxies, really rather small galaxies. And in the northern part of our sky, there are 2 more rather small ones. Now, within the total distance of about 3 million light years is the rest of the local group, several small ones, and dominated by the great Andromeda Galaxy, which is the largest one of the lot. This is our local group. This is the group of galaxies to which ours belongs. Now, that Andromeda Galaxy, again, as I say, dominates this local group. It can be seen without a telescope, the most distant object that the human eye can see. You can find it on a clear, sparkling, dark fall night if you know where to look for it. You don't see anything like this tremendous photograph, however. But notice in this picture of it again that the streaking in the arms, the dark places, now those are not gaps in the galaxy. Those dark spots are caused by obscuring matter, dust which overlies the pattern of stars behind it. And we find that dust in many of the galaxies. We can see it in the arm pattern. Now here is a photograph of a normal armed spiral galaxy. See the arms, the small nucleus, the rather widespread arms, and notice again the streaking in dark places which are caused by that obscuring cosmic dust. Now it occurs in varying quantities. Here is another photograph which shows a galaxy, an elliptical galaxy, with a much less quantity of dust, still some traces of arm structure you see here, but you can see dust in there too, but not nearly to the extent that we saw it in the first picture and in the Andromeda Galaxy, nor is there as much dust in this one as there is in our own. We know that there is a great quantity of this cosmic dust in our galaxy, and the patterns that it makes in the clouds that it forms in the sky are intensely interesting and make some of the most beautiful objects that we can see. Here is one of the very famous clouds of cosmic dust. This is the Horsehead Nebula, again in the constellation of Orion. In the imagination of the man who discovered this, it did perhaps look like a horse with its arched neck and head looking out of the barn door. But it actually is a vast cloud of dust. You can see the edge of that cloud going across here. This is a bay protruding from that edge. Notice how many more stars and how much more light is visible out here to the right beyond the edge of the cloud than over here. Here we can see a few isolated stars. And just stop and think now the size of this cloud. These isolated stars, let's say that they're average stars, like our sun, about 1,000,000 miles in diameter. This is enormous. There's a lot of dust up there. Another very famous such cloud lies in the southern skies, in the constellation of the Southern Cross, and is called the Coal Sack. Now here's a picture of that. Here's the Southern Cross, the smallest constellation in the sky, incidentally, and these four stars make the cross. And just below it is the Coal Sack, that vast dark region caused by dust accumulated and overlying the stars. Now, in many a galaxy, we can see this dust. Look at this one, for example, that we saw before. This galaxy seen edge on. See that dark line through it? Makes it look like a sandwich of light with a dark filling. That's dust, scattered and concentrated in the edges, the disk of the galaxy. That is where most of the dust lies. Now, we find, as I told you, we find dust in varying amounts in the galaxies. And we're going to look at a picture now of a galaxy which has very little dust in it. It's quite clean. This is this one. Do you see how nearly circular it is? How reduced and how insignificant the arm structure is. And we can just make out perhaps just a modicum of dust in there. Now, this is very interesting. It gives us a great range of differentiation, and it has led to some quite interesting speculation. As is man's habit, as I said, when he gets a number of objects, he not only tries to put them in classes, but he tries to find a beginning and an end to them, trace a theoretical process of evolution, and that has been done in the case of the galaxies. At first it was said that the elliptical galaxies, those which were circular in cross-section or slightly oval, but without any trace of arms, were the young ones. They began the thing. Then from this point, they branched out in two parallel branches. We had first those with a minimum of arm structure, more arm structure, mostly arm structure. And the same way with the barred spirals. You remember this other classification that we looked at. A minimum of arm structure, more arm structure, and a maximum of arm structure. This was supposed to be the progress of evolution of galaxies. But we have learned something in the last 30 years that may change all that. We have seen galaxies colliding, two galaxies hitting each other. Now that sounds like a terrific celestial catastrophe, but actually it isn't so bad. You see, the stars in any galaxy are so widely separated that one galaxy can pass right through another without the stars in one galaxy touching at all or affecting in any way the stars in the other galaxy. But the dust and the gas, this dark material, is blown out of each galaxy with terrific turmoil. And here is a photograph of the edge of two galaxies which are colliding. You can see that something is going on up there. This dark material is being forced out of the galaxy. Now, That makes for a little revision, perhaps, in our theoretical evolution of the stars. If the galaxies without dust have been through collisions, perhaps they should come later than they did before. You see, galaxies do collide. There are a lot of them up there, and in spite of the vast amount of space, there are enough galaxies in any one area so that at least 10 galactic collisions are going on all the time. This is in the average region of space. There are regions in which the galaxies are more crowded. And in these crowded regions, we know that a single galaxy can endure, or has endured rather, anywhere from 5 to 30 different collisions in the 5 billion years which we say is the lifetime of the universe. So the process of evolution may be reversed. These may be the young ones, full of dust and gas, but having undergone a series of collisions, they lose that dust and gas. The arms are absorbed, and they become, and you might say, all nucleus. There is no dust. The arms are gone. These may be the old ones. We don't know that yet, but that may be the way it works. Now, here is a picture of a region of the sky in which there are a number of galaxies. Look at them. There are very few with obvious arms. Some of these which we see edgeways may have arms in our line of sight. These are clean galaxies. And in the regions of space where the galaxies do seem to be clustered, the clean galaxies predominate. They have apparently gone through a number of collisions, and we find that intergalactic space is also filled with free oxygen. Both of these things are indications that the galaxies have life. So, you see, we may reverse our whole concept of it. Now, what have we got up to this point? Here we have a bubble in space, 4 billion light years in diameter. Now, we have no reason to believe that this is not a typical section of space, that what we see going on in here is not being repeated throughout all of the extent of space. Galaxies of all sizes, at all angles, but enough of them so that we can form an average galaxy. And remember the average galaxy? About 100,000 light years in diameter, containing at least 100 billion stars and, of course, vast quantities of dust and gas in the shape of clouds within it. Now, what are these galaxies all doing? Well, they're moving. And where are they moving? Away from each other. We analyze the light from the galaxies through a spectroscope. The telltale dark lines in the spectrum, the resulting image of the light that we see, are all shifted a little bit toward the red end of that spectrum. Now, that means that these objects are moving away. That's the famous red shift, the Doppler effect, the lengthening of the waves of light by the recession of the object giving it. They're moving apart. And the most distant galaxies that we can see are moving much more rapidly than the intermediate ones, which are moving again more rapidly than those which are nearest to us. So it would seem as though everything started at one point, billions and billions of years ago, and began to move out. It seems that way. But let's stop a minute. We are looking at light, in the case of those at an extreme distance, which is 2 billion years old. Is it safe for us to assume that light then behaved in the same way as light created last year or yesterday? Or does the journey affect light? A travel through space of 2 billion years. We are looking, maybe, at fossil light or at tired light. We don't know. Astronomy must stop and ask itself these questions once in a while, just to be sure that it isn't rushing in, let us say, where angels fear to tread. Now again, in this bubble of space, we seem to trace the framework of an organization of galaxies, a galaxy of galaxies, a flat disk-like arrangement of the galaxies, perhaps like our galaxy, except with galaxies where these are stars. Again, we are one, our galaxy, when I say we this time, of a great disk of galaxies. It looks that way. We haven't been able to definitely outline it, but the clustering, the arrangement, the distribution of these gives it that appearance. It's the old Chinese puzzle, a big box, a little box, a little box, a little box, until we get all the way down to our tiny Earth around its sun. how many galaxies are there? Well, we don't know, of course. There is an estimated 4 galaxies in our bubble of space that we know. 4 billion average galaxies, each with a population of 100 billion stars. Think, how many stars are there in space? Sir James Jeans, the great British astronomer, perhaps has the best answer for that. He says there are as many stars in space as there are grains of sand on all the beaches of all the oceans of the world. That's the picture that astronomy has built up of its universe. A picture begun at times with intervals of hundreds of years between each new acquisition of knowledge. Astronomy has called upon other sciences, mathematics, physics, chemistry, biology, statistics, and all the rest, to supplement its own findings. And this is our picture now. Still 99% mystery. Here we are, living on a little planet around the sun, a sun which is a very average star, one of billions of stars in our galaxy, and ours is just one of billions of galaxies. Now, this is a vast organization, too vast, it seems, to have been created solely for people living on one little speck, lost in it somewhere. Is it possible that there may be other inhabited planets? Since our sun is a very common type of star, we know that there are millions of stars like our sun right in our galaxy alone. Our sun is the only star who we know of, though, that has a family of planets on one of which we live. There may be others. Even if there were planets around the nearest of stars, we would never be able to know of them visually. They'd be too close to the star and too far away. But if we only knew how our sun got its family, is that unique or is it a common experience? We believe that it is a common experience. Now, biology comes into the picture. In all our investigations of light from the most distant galaxies, we have never been able to find any trace of any except the standard classic 92 elements. There are, of course, about a dozen more which we have created through our atomic experiments. But there are no other elements. And we know, biologists tell us, that 13 of these elements, worth incidentally about $1 in the common market, combine to make the human body. And therefore, if life does exist anywhere else in the universe, it must be precisely as we know it here on Earth. We know that life requires certain standards for its existence. These are, of course, a temperature range, a very narrow temperature range, from about 40 below zero to 120 above zero. That is very narrow in a universe in which the low point is 459 below zero, and the high point are the millions of degrees that we find in the interiors of stars. Life needs oxygen. Our atmosphere on Earth has 20% oxygen in it. Life needs water. 60% of our bodies are water. Life needs energy, radiation from the sun. We get that either directly or indirectly from vegetation. We either eat the vegetation ourselves or eat animals that have fed upon it. These we need for life. It can't be found in our sun. There is only one other possibility in our solar system, and that is Mars. And if life exists upon Mars, it can only be in the form of a very primitive vegetation, such as moss or lichens. Now, our sun is a common star. There are millions like it. Let us be conservative and say that 1% of the stars in our galaxy have planetary systems. That leaves us 1 billion planetary systems. 1% of those systems have planets so situated that life is possible upon them. That is 10 million inhabited worlds in our galaxy. In our bubble of space, there are an estimated 4 billion galaxies. That gives us a possible 4 billion million inhabited worlds. Believe me, we are not alone.
This is National Educational Television.